So good morning, everyone. I think we should get started. I know that it was a hard morning for some people. I can hear myself speak. Can you mute it for me, please? Okay, so I think we should get started because of time. I know that we don't have, two people are missing, the co-host from this, and also I think the first plenary speaker, but what we'll do is we'll just push the program a bit up. The people are here can start, and mainly because it's the opening ceremony. And I know that Professor Ingrid Rewiski, who is our head of School for Mathematics, is here. And then she also needs to go for other meetings. So I think we should do at least the opening ceremony part. And then when the other colleagues come, we can catch up in terms of the talks, yeah? Because the traffic sometimes can be quite a bit here as well. But in any case, yeah, so my name is Sibusiso Moyo. I'm the co-host from Stellenbosch University. So this spring school on symmetries of differential equations and difference equations and the applications is being co-hosted by WITS, the Center of Excellence in Mathematics, as well as ourselves, the School for Data Science and Computational Thinking at Stellenbosch, the Department of Maths, I think I should say mathematical sciences, because we've got colleagues also who've contributed, as well as from the math structures group, which is myself, Professor Kanhui, Professor Zurabu's behind you as well. He's also going to speak later. And then there are other colleagues, Karen, I have not seen Karen. Karen also is busy, but she'll join us later. So I just want to thank all of those. And you can see on your tags, of course, our main sponsor, Nifex, who have sponsored us for the meals. We thank them in advance. And also for the, it will be the meals and some of the activities that take place over the next 3 days. So I just want to take this time to welcome you. And I hope that, I know that some people had challenges finding where to come and also how to get to Stellenbosch. So, but finally, we are happy that everybody managed to arrive, right? Eventually. So yeah, and I hope you'll get rest maybe tomorrow. I'll go through the program a bit later because I really want to start talking about, to invite the head of school to speak to us for a few minutes. But as you know, the purpose of the school, what was the purpose? So we know that, there are many ways in which differential equations in general, whether they are ordinary or partial differential equations, arise from many systems that you can model, physical models with many applications in different fields, whether it's physics, maths, astronomy, cosmology, the ecologists, people are doing medicine in the health sciences, and so forth. There are engineering as well. So there are many applications. So we know that there are many methods, but we believe that, you know, the group theoretic methods and also symmetry methods actually have been, okay, thank you. I was competing with the GPS here. So we know that, of course, symmetries of differential equations and group theoretic methods give us tools to solve systems of equations and equations in general, and also give us insight into the properties of those systems that can help us. So we are going to have a series of talks, and I will give just a little bit of remarks in detail later. But for now, I want to ask for the official opening to ask Professor Ingrid Rewiski, who's our head of school for mathematics, and also she's our dean for teaching and learning for the Faculty of Science. The university has 10 faculties. I'll not name all of them. What is important for this meeting is that there is a science faculty, and we have the dean, and then we have our vice dean for learning and teaching who's going to speak to us. So can I ask Ingrid to come? Thank you. Can you give her a hand? I know the maths people are a bit, yes, thank you. So
there's a second one. There we go.
All right, good. So welcome to everybody. Some familiar faces, some that I'm not familiar with. This is not my research field at all. But I've always been fascinated with symmetry. So that caught my attention in your description. And I think most mathematicians are love that symmetry. So whenever I'm in a room, everything has to be really nicely aligned. And I really do look out for symmetries in much of the stuff. So I read a little bit about the field, and I think there's some lessons from the history of this, the development of the theory of symmetry that we could perhaps also reflect on today. So going back, the main protagonists in the historical development of the theory of symmetry that are used today are Sophus Lee, who introduced the Lie groups in order to study solutions of differential equations. There's Felix Klein, whose field was geometry, and he classified geometries on the basis of symmetric groups or symmetry groups. And then Emily Noether, who was in mathematical physics, most important woman in the history of mathematics, and she proved Noether's theorem, which explains the connection between symmetry and conservation laws. And looking at the description here, you have a strong focus on Lie point symmetry. And I was fascinated to see that it's used to reduce systems of differential equations, find equivalent systems, so that you can simplify the analysis of your physical problems that are governed by the equations, and then also to classify different symmetry classes of solutions. And you see some kinds of things like that. We always like to reduce things and make things simpler so that the analysis is easier and get more insights into it. So who knows what lies ahead in the context of machine learning and data science, since I see that the School of Data Science and Computational Thinking is also involved here. And I understand there's something called neural partial differential equations. So who knows where this might still lead. So to really understand the theory of symmetry and its language, it's important to understand a bit of the history, and I'm not going to bore you with all the details because I guess you know this. But the late 19th century, the early 20th century was an exciting time in the history of maths and physics and in intellectual atmosphere, mathematical atmosphere of the time. And what really fostered that? It was the free exchange of scholars and ideas across national boundaries. And even more so is the remarkable coincidence of how Lie and Klein, as mathematicians from different backgrounds, became friends, and how their careers both diverged and remained intertwined throughout their lives. And it's also impressive how Klein, and together with Hilbert, invited Emmy Noether to join the mathematics department at the University of Göttingen at a time when women were largely excluded from academic positions. And this is perhaps a message at this time for us too. Through more exchange of ideas and researchers across artificial boundaries of disciplines, demographics, institutions, and countries, our mathematics and its applications will surely be enriched, and our researchers and students will be inspired. And this spring school on symmetries of differential and difference equations and the applications provides the perfect setting for this exchange of ideas. And we're delighted to see that this is happening in Stellenbosch under the sponsorship of NITHX and COE Mass. And just looking at the participants, there is certainly a crossing of the disciplinary boundaries as well. And it's great to see that we'll be crossing the disciplinary boundary from maths into chemistry this evening when you attend the Nobel in Africa Chancellor's public lecture on a chemistry's eye on the future of TB chemotherapy. So I wish you an inspiring and productive 3-day spring summer school with the opportunity to connect in this more formal setting, but then also more formally in our beautiful town of Stellenbosch. So enjoy, and sorry that I'm not able to stay more. All right, thanks.
All right, I just want to check, are you able to give us a few minutes for a photo? Okay.
Yeah, that's fine. You carry on till 9 is fine, yeah.
So can I, and welcome to the other colleagues who have arrived. I just want to, sorry. Okay, welcome to the other colleagues who have arrived. So at this moment, I just want to call upon our co-host as well to come and make a few remarks. Thank you and welcome. Would you want to come over, Professor Kara?
Me?
Yes.
Oh, yeah.
Okay. Sorry, the mic is. No, I'll give you this one.
Oh. I was always told you got a big mouth, so I never needed a mic.
No, but you do need it for the people online. So thank you. just a few remarks and then.
Okay, good morning, everyone. First of all, thank you for attending. I'm sorry we were late. In fact, I had a call from one of my colleagues who was out at the mathematics department area thinking, so where am I supposed to be? And told him, no, the things have been changed. So first of all, we'd like to thank whoever it is that organized this place for the conference as a venue, which is quite nice. I want to thank
That's Nifex and Rene.
Nifex and Rene. Okay. So I'd like to thank
Sibu.
and Sibu, Surab from Nifex and so on for getting involved in the organizing of this conference. Initially, I had spoken to the COE. At the time, I was assistant director, which is now done. I'm no longer, so please don't ask me for money. I'm no longer the assistant director of the COE. So I'd like to thank the COE and NISEX for organizing the conference. The initial idea when I had the discussion with Sibu in January already about organizing this conference was around two or three ideas. The one was, recently there's a lot of these discussions about how do we deal with, say, newly emerging academics, those that have just finished PhD, for example, right? And sometimes they are lost. And I've sort of got involved in this because I'm sort of involved in organizing, say, interviews or maybe looking at probationary reports of young lecturers, about promotion and so on. And the kind of issues that come up is, why haven't they progressed through the PhD, after the PhD? And of course, it's about getting collaboration going. There's things like, how do they now step into the next world? So these ideas about how to move on is one of the reasons why I thought this was a good idea. Two, we want to promote the idea, continue the research in symmetries and so on. It grew quite a lot in South Africa through a number of people. Initially started by Peter Leach, your supervisor, and through Faisal Mohammed, who was, I think, Peter Leach's first student in a sense. And
you forgot about Ibrahim.
We're coming there. I'm not done. And then later, of course, with Peter Leach after the Catania conference, I've never been to Catania. Peter Leach brought Nail to our first encounter. And I'd like to say that on that occasion, for those of you that know Indian food, he had his first biryani in my house. Anyway, so it was interesting. So it just grew from there. And then later, Nail was employed at Wits and moved on to Northwest University and so on. So, and we had the first Mogran conference way back in 94 and then 96. I think you participated.
No, not me. I said
you were not there?
No.
Oh, no. Zanikov certainly was there. I mean, he was looking for coconuts. And I had to take him to a city center. And it's like, they didn't know the English word and they described it. And then we worked it out. Oh, it's coconut. So we had a nice
They talked about, the gold stone, something.
Oh, so we have this interesting history, but the idea was to continue. And then, of course, it spread when Peter Leach went to Durban. The ideas, the KZN also took up the this whole symmetry impetus and so on. So the idea is to continue that. There are a number of conferences that take place internationally and so on. So hopefully in that spirit, we're having this conference, and I don't see, and the idea was to invite established international people, amongst others, Sergey and Stephen Enko. I think he's not here. I brought him last night, so he should be around soon. So hopefully that the younger people and other people, is an opportunity to not only present your ideas, but to interact and ask questions and see if you can promote new collaborations and so on. So thank you for attending.
Okay, so you may clap. Our audience is a bit tired this morning. Thank you. I'll use this one. Okay. I think I just want to make some special acknowledgements, and then what we'll do now is, according to the program, we have to maybe just stop a bit to take a photo to allow our head of school to then go. We need the official photograph for the report. And then what we need to do is, I should also acknowledge our special speakers today, Professor Stephen Anko when he comes in. I'm sure he's not in the room because I've not seen him yet, but I know he should be around. And then there's Professor Thege Meleshko from Thailand, who's also joining us. Do you want to raise your hand so people know who you are? Okay. And then I've got Professor Zurab Janlitse. Yeah, thank you. And then Professor David Mason. Professor Mason, welcome. I just saw you come in now. So for people who work in, Professor Mason has been there for many generations and has trained a lot of people and does quite a lot of interesting work, also applying symmetries as well to some of the work he does. And then I think I'm just trying to see that we have all our guest speakers. Sorry, just a minute. I also want to check Professor Kan Hui. Okay, Professor Hui is from Stellenbosch University. He's also a plenary speaker. So if you can just watch out in terms of, he's going to talk about mathematical biology using differential and difference equations. And he's a researcher at the university as well. And then Professor Abdul Kara, you've met just now. And I think, yeah, I think I should observe all other protocols if I've forgotten. And then, of course, all of you for participating as our special guests. So may I ask that for now, we just pause for the photograph. Is that possible to do it? And where can we do it from? If I may ask. Yes, with Professor Ingrid before she leaves. Where do we do it, inside or us? Yes, a group photo.
I need to go and have a look outside.
Okay. So may I ask for a few minutes to stretch your legs, because thereafter it will be a marathon. So if you can just stretch and by the passageway. And then the people are sitting here. Some of you can sit on the other side. I'm sorry the spaces are small, but it's meant to keep us awake. The venue, I think. So yeah, so if you can just go to the outside. Thank you. Sorry, Ali, I know that you're online. I forgot to acknowledge you, but we are coming back just now. We are just taking a photo, okay? Ali, can you hear me?
Yes, Professor Moyo, I can hear you. Yes. Yes, I can hear you.
Hi, Ali, can you hear me? Hi, Ali, can you hear me?
Yes, I can. Professor Moyo,
Oh,
I can hear
okay.
you.
So just so just wait for us. We're just coming back. We
It's
just want
okay.
to do a photo first.
It's okay, no problem. Take your time.
Right? No, Steve, which department are you in? Okay.
I can go and get costs because the stream will just run. Sure, I can do that. Yeah.
Because it's just, you know. You can sit somewhere in front.
Yeah, like you said.
Yeah. So probably, have you said, do you need to set up anything? I think you're the first. Or are you going to, yeah, you want, you have a memory stick or something? Okay. I think we can use this one. I don't know if it allows us to share. It's a Zoom one. So this is the Zoom we are using, and then joining the link unless you have email, or if you can also use your laptop and share on your laptop.
No, just like this.
Okay, Zurab, yeah.
Oh, yeah.
That's the table they could give us.
There's somebody must have put their notes down here. But I haven't. Let me check in.
Yeah. It's a very strange place. I thought that there would be a table in front. Because you know, if you have a laptop, then you have to. Anyway. Yeah. Oh, yes, yes. So we're going to have announcements from Sibusiso Lukele is one of the also co-organizers, organizing committee on our side. So he has some announcements to make while we do the technical part.
Oh, do I need this? Good morning, colleagues. If anyone needs the bathroom, can you please go to the reception area? There's bathrooms there. We're just trying to avoid these two bathrooms here, so that we don't disturb the presenters. So please, I know it's a bit far, but if you need the bathroom, it's at reception. And for the facilities visit on Friday, if you'd like to come to our BMRI facility at the Tigerberg campus, please let me know during the tea break so that I can put your name for the visit. Thank you. Tonight. Oh. And then for tonight's lecture, the shuttle is coming to pick us up at around 5 o'clock. It's going to take us to the main campus at Stellenbosch University. And then afterwards, the shuttle will drop you off at the different places where you're staying.
All right. Okay. Thank you very much. So for this session, can I ask our chairperson, where's our co-organizer? Professor Kara, you'll be our chairperson for this session, but I'll call you I make a few remarks before we start as well. So we are going, just a slight change maybe in the program. I will make a few remarks, then I want to introduce Professor Stephen Uncle, who's just joined us as now. We had welcomed you in the first session, and so welcome again, and we look forward to your presentation as well. I was going to talk about symmetries and their applications. So maybe what I'll do is that, so I have some slides, but I'll not share them at this moment. I think what I can do is just make a few remarks in terms of the context. And I know that Professor Ingrid, maybe this might work. Let me just try to do this because it defeats the purpose on the other hand. Do you think it's possible to have my laptop connected and then I can see what my slides? I can't get into the room. No.
You're connected to the internet.
Doesn't allow it. Sorry, it's better if I just show 1 or 2 slides and then we'll get started. Sorry about that. So maybe while that is going on, I can still speak.
So are you going to use slides?
Yeah, it's fine because we just use the same, his will go up because it's on the memory stick. So we use the laptop.
Okay.
Yeah.
Yeah.
Yeah, so but you will do the introduction of the speakers. I've introduced myself. So you have to introduce the next speaker. Yeah, you want to still introduce her? Oh, you've already done, it's fine. Can you see my memory stick?
Yes.
Okay, now you have to go to spring school. No,
This
no,
one?
no, 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 the
No.
next one. That
This
will,
one.
yeah,
And this one.
yeah. I'll just do it for you. Okay. This is the problem of not being at the university. Is it still compatible?
Yes.
I think so. Okay, slideshow. So where's the slideshow already?
Oh, sorry.
Oh gosh, and I use my fingers.
No worries.
I just do a few from the beginning. No, it's this one.
Okay. Slideshow.
From the beginning. Okay. Okay. Yeah, just that's fine. So the technical challenge is that I think the lights also, but never mind, we'll get it right. I think it's very bright. So again, welcome to the Spring School on Differential Equations and Differential Equations, which we have today. I'm sorry, this can't move. So many technical issues. Don't we have like a pointer for it? How do I move this?
Let's see.
Okay, just there, yeah. Oh, go back. One, yeah. So if I can use the arrow, okay, cool. All right, so we are started, yeah. So welcome again. Normally we should have been at the university, but this week has been very hard for us because unfortunately we have, or fortunately there are two events happening. This Spring School and also the Nobel in Africa seminars. Which means that the venues generally, the venue that we use was not available, so we had to come here. So if you can bear with us, but we'll get used to it with time. So for Stellenbosch University, of course, we are a research-intensive university. We have over 33,000 students, and I just wanted to show you a little bit of information about the university. You can see here we host a number of chairs, and today, of course, we are glad to have Professor Khan, who is with us today, who does work in ecological modeling as well. And then there are about 46 of them that are sponsored by the National Research Foundation. We have about 504 people are rated. We value NRF ratings. And one of the purposes for this workshop, as Professor Kara said in the first meeting, is that we really want to help to build capacity for young researchers as well, to build opportunities for networking. But of course, in this area, what's important is also the skills that are needed. So we thought it was important to have a spring school where people can reconnect again, also use this platform for networking and collaborations. There are a number of things that we do, but these are just for information. So for example, we host a lot of postdocs, about 341, but our idea is to grow that number to about 600 in the next few years. And then we also do a lot of work between research and translation in terms of commercialization and trying to translate your research. For mathematicians, it's very hard. So one of the discussions we've been having with a lot of colleagues is around how do I apply my maths to the other fields which are emerging, and how can we apply this? So we've got people are interested in using Lie groups and understanding how do I use Lie groups in different settings. So the idea was to also try and show some applications. I'll just give one or two examples because we've got a very good plenary speaker who's also going to give us some examples of how we use Lie symmetries in solving some of the equations that we come across. So this is just an analysis, analytics tool, which is online for those of you who use Scopus and so forth. So just to say that one of the areas where we see that as a university, we want to increase collaboration. So amongst the South African universities and internationally as well. So far, this percentage here of publications that are co-authored with international people are quite low on our side. It's 54%, but the target is to have that at 80%, ideally for a research-intensive university. So I'm hoping that through this network, this meeting, that you can find also new collaborators. And also if you want to collaborate with us, at Stellenbosch, wherever you are coming from, we are also interested in collaboration and building those networks. So make use of the opportunity as well. And while I speak, it's also the same. I think it applies to WITS and other universities because we all meet and we have similar aspirations as well. So in the Faculty of Science, I did say that we have about, in this case, 8 departments. But the main department is the mathematical sciences, but this mathematical sciences department is broken up into 3 areas. There's applied maths, which I'm affiliated to. And then there is the computer science department and the mathematics department. So it's that one which makes the 8. Otherwise, if you count, there'll be more than 8. But you see that there are other departments which are there. So today, the Nobel in Africa, so if you, the Nobel lectures normally take place in Sweden, but this time we managed to get into an arrangement with STIAS, which is this, the Institute for Advanced Studies, Stellenbosch Institute for Advanced Studies, to host these lectures here. So we get a chance to get some of the people coming and also working with the young scholars. But you hear about STIAS later, because if you check on our online link as well, that also allows you, if you want to take time out to write, to do some research, you can actually, it's open to everyone in the continent and everyone in the world, actually. You can spend time there writing. And we've had at least one person who won the Nobel Prize who spent a year here doing literature on sabbatical for about a year. And they won the Nobel Prize later. So it's a good way to spend time. So I think we must see it before you leave, actually, if you can. I would encourage you to do that. Then, these are the areas. So I thought that you might be interested in what areas are we involved in. So in applied maths, we've got those ones on your far left. And Professor Hui, where's your area here? And then I've got on this side is the maths people. I'm trying to see Professor Kang, who is here, mathematical and theoretical physical biosciences. And then Professor Zurab, where are you? In the maths department. Yeah, here. Okay, over there. So we've got some people here. So if you are interested in these areas, they'll all speak. So I think that you should just reach out, because we want to also, we are interested in collaboration, like I said. And then the aim of the school, of course, you all came because you had seen this, but of course, just to remind you, it's bringing you together as researchers and students, working in Lie symmetries and related methods. This is just one of the methods. There are many methods and applications in differential and difference equations. And difference equations, that's important. Topics include, but are not limited to, invariant solutions, optimal systems, Noether symmetries, conservation laws, as you have heard, and then recent developments in the area also help to provide, opportunities for future directions, because also we want to build the area. We want to understand how can we apply this also to other emerging fields. And of course, the topics you can see from the program will range from, symmetries. You hear this quite a lot. So there are certain assumptions made about what is known, but I'll just highlight those quickly. And then we also wanted to make sure we acknowledge all our sponsors. That was NISEX. There's Renee. I don't know Renee if she's here. Maybe she's gone already. Sibu, who just spoke. And then online, there's Ali, who he can hear me, but we can't hear him. And then who's worked very hard to just make sure we put the program together. He couldn't come because of visa issues. So we hope that he will be able to make it next time around. And then, of course, acknowledgements of the plenary speakers, participants, and the colleagues who have helped to do this. And then the other part, I thought that it might be interesting to, because you hear this, and usually when the talks are given, there are many assumptions made that you understand the basics in the area. So I thought that we should just maybe remember, Sophus Lee, who was the first person, and Professor Meleshko. I didn't mention all the people who have made contributions, so I'll just stick to Lee, the Sophus Lee for now. And then so that we'll get the history later. So he was a Norwegian mathematician, born of course in 1842. He's the founder of the theory of continuous groups and their applications to the theory of differential equations. And I think this is where it all starts from. His investigations, of course, have led to major branches of 20th century mathematics in the terms of the theory of Lie groups and, of course, and their applications. And then I thought this point was interesting. He was arrested in 1870. And I thought, yo, what did he do? How does a mathematician get arrested? So this was during the Franco-Prussian War, and he decided to walk, actually. He had decided to walk to Milan and hike home across Germany during this time. But he was mistaken, actually, for, what do you call? Wrote north as well. Yeah, so he was like, he was suspected of being a spy. Okay, and then he was arrested. So he spent some time in prison. But I like this quote. So while he was in prison, he said that, you know, he was able to complete his PhD in prison, actually. So this quotation, which is quite famous, where he says, "I've taken things truly philosophically." I think it's a very interesting quote. Truly, I've taken things truly philosophically. I think that a mathematician is well suited to be in prison, okay? That doesn't mean, but he says, that doesn't mean that I accepted freedom philosophically. In truth, okay, the sun has never seemed to shine so brightly. The trees have never seemed so green, okay, as they did yesterday when as a free man, I walked to the railway station in I should get that name right. It's Fontainebleau. It's a French word. Anyway, so yeah, so I thought that was interesting. I didn't know that this quotation was by him. I thought it was by somebody else, but anyway, so that was interesting. I think what it just means is that usually, of course, you can make use of some quiet time, not feeling lonely, but you can actually solve something. But in any case, and then you heard about Amy Noether as well, and you will be hearing about Amy Noether because my co-host, for example, so I spent a lot of time Noether's theorem and the invariance and so forth. So we will also hear about that. But Amy Noether, of course, was born in 1882. She's also a German mathematician who made many important contributions to abstract algebra. She's discovered, well, not discovered, she's responsible for the first and second theorems, which are fundamental, of course, in mathematical physics. And then during her time, she had a lot of difficulties because in her time, women were not allowed actually to attend these lectures. So she audited lectures and finally completed her PhD. Taught by, of course, David Hilbert, Felix Klein, Hermann Minkowski, and Karl Schwarzschild as well. So I thought that was interesting. And then I was thinking about how do we bring this to Africa because we are in the Nobel in Africa and maybe we are still waiting for the next Nobel Prize from Africa in mathematics, hopefully, some field. But how many of you have watched Hidden Figures? Only one. Okay, but I'll recommend it this weekend. You must watch it because it's free. Anyway, there's rugby after rugby. Okay, you can watch it after rugby. Yeah, so anyway, yeah, so if we win, it would be nice to watch, but you can watch. So you know that, so this is about, you know, the three African-American women who made a big contribution to mathematics, of course. But they worked as, I think they are quoted as human computers at this research center. Of course, NASA in 1943 through to 1958. So I thought that I should just flag them here because, I mean, we still look at, in terms of the continent and also South Africa, there's a big challenge around trying to encourage women as well to be, you know, to do some great things as well in mathematics and not just be passengers. So I thought I should flag that. Then I will start here and then I will pass on later on. I thought that's just some basic definitions. So these are taken for granted as well as known already. So when you talk about a group, the usual definitions of a group is a set of elements, of course, which you describe with a composition law so that you have the first part is the closure property, which is important when you're defining any group. So for any elements that you pick from that group X and Y, you want to make sure that that composition law, when it acts on those elements, they still stay in that set. Then the associative property as well, which makes sure that you have for all the elements that you pick X, Y, Z in G, that they also behave in that manner. And then finally, the identity element, that for every unique element, you can find an element within the set, so that you have that as part of the laws that you have. So those are basic assumptions that are made. And then the other part is, of course, the inverse for that group. You should be able to find the inverse element in the group, so that when you have that operation again, you can get the same identity element. And then ideas around subgroup and abelian group, which we also apply to the same definitions as well. So those are taken as things that you know. And then, of course, a typical example here is that if you have a group and you have a subgroup in that group, H, which is a subgroup of G, we call that a subgroup. If and only if for two elements that you pick, if you take an element in H, H and K, those also, and the inverse of H is also part of the stays in that group. So we say that H is a group, okay? So H is a normal subgroup if you have that condition as well, which should hold for elements G in the group itself. And then what else do we have? So if H is a normal subgroup, the family of courses, that one can be made into a group denoted by that, which is a factor group by the product definition, which is given in that part as well. So this, I take that, so I would jump because there are many assumptions that are made. Who doesn't work in this area, who's in this room today, just to have a sense of who has never done Lie groups in this group? Can you just raise your hand? Just raise your hand so that we have an idea. Okay. 1, 2, 3, 4. Okay, so the majority have. Okay, so there are many assumptions which are made. So the other assumption is that you know what Lie group of transformations is, but you can read this stuff. It's usually available. You can find many sources of it. Again, one parameter Lie group in two variables will be given by those transformations where I've got the functions f and g defined like that. So where you have S here as a scalar, which whose value, of course, defines a one-to-one invertible map and from your domain to the target space. And then the functions f and g are smooth analytic functions, so of the group, of course, and therefore expandable in terms of a Taylor series. And that means you can also differentiate them a number of times. So the transformation reduces to an identity, which is given in that form. And then what else do we need to know? Then we also need these ideas about what is a linear group. How do you define the linear group? The real general linear map, linear group as well. And then what we call the real general linear group, which is a subgroup of the complex complex general linear group, which we denote by GLNC, but this is usually basic definitions which you can get. And then ideas around the rotation group and so forth. So the group theory has to be there. Then finally, the definition of Lie algebra, which is defined as a vector space. And that vector space has to be equipped with a Lie bracket, which also behaves like that, like an abelian sort of behavior like we do for matrices. And then the last part, of course, what's important there is the commutator analogy, which is similar to the operator of theory of matrices, and also bilinear antisymmetric and making sure that it satisfies the Jacobi identity. So what is the remark here? What's important? So Lie algebra usually is defined over the real field and complex field. And then we know that a differential equation that admits the operators X and Y, I'm treating these as operators, not variables X and Y, also admits their Lie bracket, of course. Which is known. And then the other part is that a continuous Lie group can be assigned the corresponding Lie algebra. And then a Lie algebra can also be assigned the corresponding Lie group according to Lie's main result, which you can find also in the literature. So the special linear group, for example, has the corresponding Lie algebra, which is given by SLN. So the other part, here I wanted to talk about mainly the symmetries of differential equations, the types and methods that we have. So there are quite a number of things here. So I did say that you do get, we know that equations arise from different applications. And of course, you can get many types of equations, whether they're ODEs. Some of the work we've done has really been on ODEs, PDEs, delayed differential equations, and stochastic differential equations, which are still waiting for Tembi to finish off. There's a lot of work which has been undone. She's been away for a year. She had a terrible accident, but she's recovering. So we are glad to have her back because there's a lot of unfinished work there. And also amongst delayed differential equations and difference equations again, I think that is also an important area where there's quite a bit of work that still needs to be done again. So the methods, so what methods are there? There are many methods that you can use. Analytical methods, okay? So separation of variables. So when you go for lectures, this is stuff that you learn, how to find the solution, okay? You can use dimension analysis, group analysis, which are focusing on in these 3 days, method of differential constraints. And I know Professor Meleshko is gonna do something at some point. I know your talk changed later on, but today is differential constraints. Yes, okay. And then there is transformation of a simple equation, then Sumudu transforms and other transforms. Then you can also use numerical methods. And then what is important to note is that I had some students who were asking me, how do I find symmetries? So there are many tools that you can use. The important thing is to try to do something manually so that you understand. And then you can use a number of tools, reduce, for example, or even Mathematica, which has you can write, well, if you can write, it helps to be able to program as well. And then Mapo, sorry. You recommend reduce, that's his favorite, some people, yeah. So you can use whichever you like, but reduce helps because you can write what you want, you know, rather than just this fixed. Well, but it depends on what you're doing. And then applications of computer symbolic calculations, which can be used, of course, in group analysis and in transformation of equations to simple equations. So you can do this, there are tools. So those tools, you need to know which tools can I actually use. Right, okay, so let's look at one example. Then I'll stop here so that I don't know, how much time do I have? Where's our chairperson? Our chairperson has.
You have 5 minutes. In fact, if you're going to go to the end.
Wait. 5 minutes for 9:30.
5 minutes for 9:30.
Oh, okay. All right, so let's do just one example, right? So this one, again, well-known heat equation. So here you can use, so if you just try to use maybe separation of variables, so you can assume, you make certain assumptions that h is given by those functions, f of t, g of x. And then when you do the you replace h by that in the first one, you can write it in this form. And then you can see that if f is in that form, that's your g takes this form here. So I've put my c, and that's the g. And then you get, also the second case is that if you assume c is that, you get your g there. So that means you can find what your h is. So separation of variables is very easy. But now if you ask yourself, you can ask yourself, there are many questions which arise, but why? How do I know that's what would take it to that form? So here's another example, the KdV equation. Again, here, you can assume these traveling wave solutions. So you can assume u is that form. And then your 3k ut f of u is given by that second term. And again, you can do your substitution. So you start from here. So I've got my fu, I've got my beta and d, and then you can see that my u will take that form. But the question you can ask yourself is, why? How do I know what u to take? So, because I believe that, you know, when you look at the methods for differential equations, they help you to know what transformations you can use from A to B in a systematic way, rather than just guessing, right? So that helps you. And so in general, what we do is that if you look maybe at ODEs again, if you have an equation which is given by that, the definition is that you can find a one parameter Lie group of point transformations, and you can represent the generator like that, which is the infinitesimal generator, and then you take the nth extension of that generator, operate on that equation, equate it to 0 in order to get what the symmetries look like. Sorry for, yeah. So you, sorry, have I moved? Or did I have the same slide? So my slide is not moving, okay. So anyway, so you can apply that to a number of equations. My slides are not moving. Okay, interesting. Okay, I think it's time to finish. So you can apply you apply the definition to some equations, and a typical example is, oh, all right, that's fine. It's connecting. Yeah, but it's okay. I will stop just now, but maybe the meeting is being recorded. It stopped. Oh, I see. Okay, so that's fine. It stopped anyway. So you can then apply that to operate on particular equation. I don't see what you see. Okay, yeah. I think what happened is the Zoom meeting finished. Yeah. But maybe you can put a stock, it's fine.
Did you close the program that you're using?
No.
Let's try again. Share.
But it's okay. Anyway, so while that is going on, let me go this way. So anyway, so you have to then use, okay, I don't know how we reached this. So we jumped a page. Okay. Yeah, I will stop just now, sorry. So you can use your program to find the symmetries just for the benefit of those who might not be able to. So if you look at that example, for example, using the definitions we had, this is going to be an interesting day because of all those coming up. Okay, so you find that the Lie symmetries for this equation will look like that, and you can show that the Lie algebra is given by that. So the question I used to ask myself is, how do you know? So there's some pre-required information that one needs. This comes from representation theory. You have to know how to do the classifications. There is tables which show you, once you calculate your generators and the relationships that you have, you can work out what group they belong to. The determining equation, this one is found from the relationship. You take your nth extension of your generator operating on your equation, gives you that. And then this also assumes something else, that you're assuming that the solutions are polynomials, because in the background, there's this theory of polynomials, which which is sort of some equivalence when you're talking about equations and their symmetry. So here you can assume polynomial solutions, and then because you know that the C and eta here, it's a point symmetry, depends on X and Y only. So you can separate by the derivatives, find what your coefficients are, and then replace them in the equations that you get as part of your determining equations. And eventually you can find what your symmetries are. And you can show that those symmetries are given by that. So I will stop here for now and then ask if you can introduce the speaker for the next session. Can you clap for me at least? It was the introduction. Okay, that's part one. Okay, thank you. It was a B, not an A, okay.
So I was going to ask speaker, but
Part one,
we'll have discussions there.
yeah.
Now, I hope we're not going to have, like Sibu, you said, an interesting day with this whole link thing.
Yeah, thank you very much.
It's an interesting little mic.
You need to stick it on your shirt.
I think Stephen will have to.
It's
Yeah.
really good.
Okay, so thank you very much, Sibu. So Stephen Enko is, I think, well known to most of you. A lot of his work has been done in the area of multipliers, and so in the application for constructing conservation laws and so on. Stephen has worked a lot with George Blumen, whom of course you also know a lot about. Stephen is from the University of Brock University in St. Catharines in Canada. I think this is your second trip to Cape Town, actually. Stephen has visited Ames, and he'll tell you a little more about himself as we go along. And I'm sure you'll have interesting discussions with Stephen during the tea break and maybe during lunchtime and so on. We are honored to have you here, and thanks for taking the time, for coming a long way across the world. Stephen?
Thank you very much, Abdul. It's a privilege to be invited here to give this talk.
Yes.
How does paging work? Okay, this with there, okay.
Put this on the shirt.
Yeah.
Is it changing here? No, it's not.
The maps, you know, the maps are not the best.
There's some other.
Can you check what's in the slides are not changing from the, just where this.
I think it also share on Zoom. Are you sharing?
Yeah,
on Zoom?
it goes to Zoom, that's fine.
Oh, Zoom, we can share on Zoom. Oh, they are.
No, it's because of the internet connection.
Here.
It's going down, yeah.
I suspect we'll have to abandon this if it's going to keep doing that. It's a bit disturbing.
Okay.
There we go. It works. Just takes a while. Sorry. Takes
Yeah.
a little bit.
Okay, very good. All right, so I'm going to talk on symmetry, multi-reduction of order for PDEs with conservation laws. So this is another analytic method. It was not on the slides, so this will be of some interest to everyone. Yeah, the level is, I'm assuming everyone understands the basic concept of symmetry. But yeah, feel free to stop me if you have questions as we go along. So I'll introduce the basic ideas, and I'll talk about conservation laws, and then some technicalities on symmetries and their relation to conservation laws, then state the main theorems. And the main part of the talk is to show you some examples. And all of these, each example will be an application to a physical problem. Okay, so in general, as we've heard, Lie symmetries give us a very powerful way to find solutions to differential equations. The idea is we'll have a group of symmetries and we look for solutions which are invariant under that group. And what happens is that the solutions will satisfy a reduced differential equation in fewer variables. So that's the essence of the technique. And the more symmetry you have, the fewer variables there are in the final reduced differential equation. So that's very good. But in the end, you're still left with a differential equation that has to be solved. And that equation that remains can still be difficult if it has no symmetry. So this is very common in applications. The typical situation that we might want to have, partial differential equation in two variables, maybe time and a space variable. And then if we have a one-dimensional Lie symmetry group, the symmetry reduction for group invariant solutions will give us an ODE. It'll have the same differential order as the original PDE, but we're now an ODE. Of course, we still have to solve that ODE, and so that's the essence of the final obstacle to using the Lie symmetry method to get exact solutions. So if your equation is of order n, differential order n, and if after application of the symmetry reduction, the ODE, if you find it has no symmetry itself, then what do? How do you find solutions of that ODE? To do the integration, you're going to need first integrals, and in particular, a total of n-1, where n is the order. So the purpose of this work I'm going to describe is to find a way around this issue. In particular, we're going to show that first integrals of this ODE can be inherited from conservation laws of the PDE. And if we can find all the conservation laws that will be inherited by the ODE, then each of those can give us a reduction of order, which takes us closer to complete integration of the problem. Okay, so just a little bit of history. And is there a clock somewhere so I can keep track of my time?
I'll keep track.
Okay.
It's fine, we'll give you a notification when it's 5 minutes before.
Yeah, that's a problem for an hour talk. Maybe just clue me in every 15 minutes. Yeah. Okay. All right. So the history of this basic idea, it's called a double reduction in the literature on symmetries. And so it goes way back. So the first reference I could find was 1937 by Whittaker and his famous treatise. And the idea is if you have a variational formulation, this is the setting where Noether's theorem applies. So if you have a variational symmetry, that's the symmetry of a Lagrangian for your problem or an action principle for your problem. Then the symmetry can be used in two different ways. One way is to look for group invariant solutions. The other way through Noether's theorem is that you get a conservation law. And these two aspects are related because the conservation law you get from Noether's theorem will be inherited under the symmetry reduction. Okay, so that way you not only get a reduction from the group invariance, but then you get a further reduction because you have an automatic first integral from Noether's theorem. So 2 for 1, double reduction. What happens if there's no variational formulation? So there was some very interesting work by Soberg from Wits?
Originally from Johannesburg.
Johannesburg, yeah, in 2007, showing that we don't actually need a variational principle. All we need is a conservation law, which is invariant under the symmetry that you're interested in for the group invariant solutions. So if you have a PDE, it has a conservation law, which I'll explain technically what that is later. And if that conservation law is invariant under the symmetry, then again, you get a double reduction. So you have the reduction using the symmetry to describe your group invariant solutions, and there's an ODE there. That ODE will inherit a first integral from the conservation law. Okay, so the work I was involved with is to try to generalize this as far as possible. So I'm going to present a systematic method that will allow us to find all inherited conserved integrals of the reduced ODE for group invariant solutions. Okay, so that way we're maximizing all the information that's available in the original PDE in order to get as close as we can to the complete integration of the ODE for group invariant solutions. And in the examples, assuming we can get through all this in time, you'll see that it's possible to have multi-reduction in the sense that a single symmetry can give triple, quadruple, and even higher reductions. So you can get 3 for 1, 4 for 1, et cetera, from a single symmetry. So this is a very powerful extension of the method. So the basic ideas were written down by myself and my collaborator, Maria Gondarias from Cádiz University in Spain a few years ago. Yeah.
It's changed, I guess.
Yep, it's changed. It's good. Okay. So how do we find the conservation laws, which are going to be invariant under the symmetries that we want to use for symmetry reduction? So first thing is, how do we find conservation laws? So let me just mention a few general things, because sometimes it's often not clear to people what the status is for finding conservation laws. So we all know how to find symmetries. There's Lee's method, which was explained, summarized very nicely. There is a very similar method using determining equations that finds all conservation laws. And so some actual history on this is it was first worked out in the abstract setting by the Russian school, Vinogradov and so on. Almost at the same time, this is in the 1980s, a concrete version was summarized in Ulber's book. And then it was further developed independently by myself and George Blumen into an algorithmic method. So all steps become fully algorithmic in a simple way. And we also showed the connection to adjoint symmetries. The multiplier method is complete. It yields all conservation laws. There's no need for any special methods, okay? Unfortunately, there's still some misunderstanding in the literature and people trying to use special methods when it's completely unnecessary. It would be like saying, oh, we're going to find symmetries by some special method, just ignoring the fact that Lee's method gives us the general way to find all symmetries. So I want to at least point that out as something to take away if you get nothing else out of the talk. So the multiplier method is complete. It gives us a way to find all conservation laws. And the way we're going to use this is an extension of this method so that we find the conservation laws that are going to be invariant under the symmetry that we're interested in for finding group invariant solutions. And again, the method will be complete. We'll be able to find all such conservation laws. So the basic ideas from myself and also in joint work with Professor Kara, where we looked at this kind of idea. And what we'll show is that in general, each invariant conservation law of the PDE is inherited by the reduced ODE for group invariant solutions. The method's fully algorithmic, so it can be implemented in reduced if you like, although I use Maple. Okay, so let me just talk about what do we mean by conservation laws and what are the steps in the method for finding conservation laws. Okay, so we'll assume we have could be a single PDE, or here I'm doing it on the slides in general for a system of PDEs. So we have some independent variables, T, and spatial variables X, and a number of dependent variables U. So what's a conservation law? It's a local continuity equation. So if you're familiar with any physics, that's a basic idea. Local continuity equation says that you have a conserved density and its time derivative is equal to a spatial divergence. So the phis here, this is the conserved density. This is the components in the spatial divergence. And this holds on all solutions of the PDE. The conserved density phi t and the components in the spatial divergence phi, it's called the spatial flux. They're allowed to be functions of our independent variables, our dependent variables, and derivatives of the dependent variables. Okay, the capital D's here are total derivatives. That just means partial derivatives acting by chain rule. Now, there are some expressions that will satisfy this kind of local continuity equation, but will contain no information about solutions. Those are called trivial conservation laws. And what we do is we mod out by those. So we're only interested in conservation laws that are non-trivial and hence contain useful information about solutions. Okay, so what's the connection between these local continuity equations and multipliers? Well, we could show that for almost all PDEs of interest in applications, that if we have a local continuity equation, then off of solutions, that expression can be written as a sum of some multiplier expressions times your PDEs in the system. So if it's just a single PDE, this is just a simple product. There's no summation. So this is holding off of the space of solutions, and the Q is called the multiplier. Or in the case of a system, the set of the Q's is called a multiplier. And the importance of the method is that there's this one-to-one correspondence, which can be proven, between non-zero multipliers off of solutions and non-trivial conservation laws. And so where we're modding out by all the trivial ones. Okay, so this is the essence of the method. There's no special assumptions being made. This is just a different representation for a conservation law. The multiplier is a very useful way to represent the conservation law because it automatically mods out by all the trivial conservation laws. And there's a very simple way to find these multipliers. So we use the concept of the Euler-Lagrange operator or the variational derivative. And if we apply this operator to the left-hand side, it's going to be equal to the operator applied to the right-hand side. This operator has the property that it annihilates space-time divergences. So therefore, we're just left with the operator applied to this multiplier product equals 0. This is holding off of solutions. And there's a very simple way to expand this using a product rule. So I won't go through all the details here, but it uses the Frechet derivative and the adjoint Frechet derivative. Okay, good. And so this is equal to 0. The unknown here is the Q. We know the equations from our PDE system. And then it turns out this system splits with derivatives, just like we heard about for symmetries. And then it's straightforward to solve. Okay, so this method is fully algorithmic, gives you the same kinds of equations. In fact, connect this up to the symmetry determining equations on the next slide. Once you've found the Q's, then for each multiplier that you have, you can reconstruct the components of the conserved density and the spatial flux by several different explicit methods. Okay, so that was one of the contributions in the work with George Blumen, is we had a very simple homotopy formula for doing this, and we discussed some other methods as well. If you're interested in a modern review of all of this topics, you can find it in my 2017 paper. Okay, so some remarks. So in the previous determining system, it was, in contrast to symmetries, it was holding off of solutions. If you specialize it to solutions, then one of the terms drops out, and you're left with this equation. This is exactly the adjoint of the determining equations for symmetries. So in my sort of fancy notation, the symmetry determining equation would just be remove this star, and this would be the characteristic of the symmetry. So this is just the adjoint, and it can be solved exactly the same way as the symmetry determining equations. Of course, that's only half the system. You still have the other half of the system, which has to hold off of solutions as well. But I just want to point out the similarity with symmetries. And the connection in notations here is that this Frechet derivative applied to the characteristic function of a symmetry is exactly this prolongation that we heard about. But that's a technical point. It's just much simpler. So we're using symmetries, the generators of symmetries, in what's called evolutionary form, which technically is much, much simpler than the canonical form that's traditionally used, which requires complicated prolongation formulas. Here, those are just gone. We're dealing with everything in evolutionary form. So you can think of the multipliers as analogs of the evolutionary form of symmetry generators. And so I've already emphasized this point. So this system for multipliers can be solved in the same algorithmic way that we solve the symmetry determining equations. And in particular, for example, in Maple, there's built-in packages that do this, or it's easy enough to program something for yourself. Now, we heard about Lie point symmetries in the introduction. So the way they fit into this formalism here that I'm talking about is instead of working in canonical form, we work in evolutionary form, and then the P would just be the characteristic constructed from the components of the symmetry generator in canonical form. So that allows some technical simplifications, and one main point that we'll use later on, which is maybe not so well known in the literature. So this is this symmetry determining equation. It's on solutions. What does this look like off solutions? Because when we're formulating multipliers, we're off solutions. You can equally well formulate this off solutions. And then there's this very simple relation between how the symmetry acts on the equation off of solutions. There'll just be some matrix function times the equations in the system whenever you're dealing with Lie point symmetries. So that's not so well known in the literature, but it makes the proof of everything very simple for our main results. Okay, so we now have a general idea of if I have a PDE or a PDE system, how do I find its conservation loss? So we just run this multiplier method. But what we're interested in are finding only the conservation laws, which are going to be invariant under symmetries that we're interested in for getting group invariant solutions. And it would be nice if we could find just those and not the other ones, which we're not going to need. So here's how the method is going to work for that. So the first thing is this proposition that says, if we have a conservation law, how does the symmetry act on it? So the technical details are not important, but there's this explicit formula involving the symmetry generator and prolongation and some other expressions. So here I'm restricting always now for the rest of the talk to Lie point symmetries for simplicity. Okay, so and this is formulated at the level of the local continuity equation. The corresponding statement at the level of multipliers looks like this. So it's fairly simple. Again, just involves prolongations, and it involves this adjoint of the matrix function, which comes from the way symmetries act on the equations off of solutions. So one of the themes here is that traditionally, we're always working on the space of solutions, but we're actually throwing away information when we do that. There's a lot of information going on in symmetry theory when you move off of the solution space. And in particular, this function, which normally you don't ever see because you're always working on solutions, actually plays a key role in the results here. All right, so what does it mean for a conservation law to be symmetry invariant? What it means is if you apply the symmetry action to the components of the local continuity equation, then invariance is that the infinitesimal change is just 0. Okay, and here we're taking into account by modding out by trivial conservation laws. So we're allowing for the possibility that a symmetry can take a conservation law and move it or map it into something trivial. That was not taken into account in the original work by Soberg, but it's essential if we want to have the most general formulation of the method. So the way to do that, to mod out by all of the trivial conservation laws, is just to work at the level of multipliers and work with this formulation because of this one-to-one correspondence, which automatically mods out by everything trivial. So symmetry invariance at the level of the multipliers is very simple. It's just this expression has to vanish. Okay, so now we're ready to talk about how we use this in the context of symmetry reduction. So we'll assume that we have some lead point symmetry group, and we're interested in finding exact solutions which are invariant under this group. Okay, so so I won't try to explain all the details, but I'll just summarize quickly what's in the literature. So the way we can write down the expression to find group invariant solutions is we first look at, this is the evolutionary form of the symmetry acting on our dependent variables u, and we put this to 0. So that's the condition that the symmetry doesn't change the form of the solution. That's called the invariant surface condition. That's just a first order equation, and it can be solved, and it will give us the form of u in terms of the invariance of the symmetry action. So I won't go through all the details there. I mean, hopefully that's familiar to people, and I'm sure we'll hear a lot more talks about this. So this is just the standard stuff. And the idea is after the symmetry reduction, our original PDE system has become a reduced equation in fewer variables. So it'll be formulated in terms of the invariance involving the independent variables, the invariance involving the dependent variables, and their invariant derivatives. And this will always have, for a Lie group, a one-parameter Lie group or a one-dimensional Lie group, will be a reduction of one independent variable. So this will have one fewer independent variables than the original PDE system. Okay. And there's an explicit relation, again, off of solutions. This is useful information, which is often just thrown away or ignored. But there's this explicit relation between the expressions for the reduced differential equation and the expressions for the original partial differential equation in terms of this function, which, remember, comes from how the symmetry acts on the equations off of solutions.
So then Rx is like the conformal factor.
Yeah. So the general statement is every Lie point symmetry acts on the expressions for your PDE system just as a conformal factor. It's not so well known, but very simple result. Okay, so where were we? Yeah, here. So the main theorem now, and how's the time?
Almost 30.
Pardon?
Almost half.
Half, okay. I thought you said 50. I thought, yeah, 30, okay. No, that's good, because I want the important part of the examples, and each of those takes some time. But just the main theorem. So you have a PDE system, and the conservation laws, which are invariant under a given symmetry group, will reduce to a corresponding conservation law of the reduced differential equation that describes the group invariant solutions. And so there's explicit formula for the components of the reduced conservation law. And we'll be in particular interested in the case where the reduced equation is an ODE. So this will only have one term, and this will just represent a first integral that we can easily integrate to get a quadrature. Okay, so I won't really talk in any detail about the proof. It uses all the ingredients that I've mentioned up till now. The main thing for computations is, so how do we find all of these conservation laws that are going to reduce to first integrals? The answer is through multipliers, and here's the full system. So this is the system just for multipliers. It's augmented by the condition that the multiplier gives an invariant conservation law. And it's the more equations you have, it may seem that this is more complicated, but in terms of Lee's method for splitting and solving this system, it's easier when you have more determining equations, because the system is more overdetermined, typically has less solutions, typically is easier to solve. Okay, so this is actually a good thing for computations. All right. Now, it's possible that when we run this method, we will find more than one conservation law, which is invariant. And conservation laws in general, they form a vector space after we've modded out by the trivial ones. And if this vector space has a dimension m, then each conservation law invariant under the symmetry will give rise to a reduction. And so if we have m-dimensional space of them, we'll get a reduction by order m. So m could be 1, but as we'll see, there's examples where m is 3 or even 4, et cetera. So we can get multi-reduction from a single symmetry. Okay. Often we're interested not just in looking for invariant solutions under a single symmetry, a one-dimensional group, but we might have, for example, an algebra of commuting symmetry, so the abelian situation that was discussed in the introduction. And everything I've said carries over there. We just use the joint invariance of the entire symmetry group. And the reduction is carried out in a single step rather than having to do successive reductions. More interesting is the case of a non-abelian symmetry algebra. Now, in ordinary symmetry reduction theory, it's well known, for example, in Blumen's book or Elver's book or Ovsyannikov's book, that the way you do the reduction is that, first of all, you need some condition on the symmetry algebra. It has to be solvable. The solvability then allows you to order the symmetry generator so that you carry out the sequence of successive reductions. What's interesting is that for this method that we're using here to get the first integrals, none of that is needed. So you don't need solvability, and you can do the reduction in a single step. So it's much easier to use than ordinary symmetry reduction in that sense. So I won't go through much details on this. What I will point out is just a technical thing. If anybody studied this before and they're wondering about it, the condition on the multipliers acquires an extra term which incorporates the structure constants in the symmetry commutators. So I won't give all the details of that and just point out that it's straightforward to do that. I have some recent work which explains the details. And the main point is that there's no need, without the need for successive reductions. So we can find all the conserved integrals in one step for a non-abelian symmetry algebra. Okay, so now the last part of the talk, I'll go through 4 interesting examples. So the first example, this comes from Soberg's paper. It's the linear heat equation, which we saw. And we're going to use the scaling symmetry. There's actually not a single symmetry because this is linear. There's 2 symmetries. There's a scaling in Tx, and then there's a scaling on U. So you can combine that into a single generator with a free parameter. Okay, so what Soberg did in her original paper was to just write down a specific conservation law. I couldn't see any motivation for it in her paper, but it turned out to be invariant under the scaling. What I want to point out is, in contrast here, with the multi-reduction method, we're going to see there's more than one conservation law, which is invariant, and we'll be able to get more reductions than what Soberg did in her original paper for the same problem. Here's the invariance under the scalings. And so if you're doing standard symmetry reduction, here is the reduced ODE in terms of the invariant variables. So notice we preserve the differential order. This is a second order PDE, so we have a second order ODE. We preserve linearity, linear PDE. This is a linear ODE. Okay, so we need to be able to integrate this in general if we want to find U. If we want to find the capital U, which in turn gives us the solution of the original PDE. So this, we call it the similarity solution, the scaling invariant solution. It's non-trivial to integrate this directly. So here's where the method comes in, that we're going to find quadratures of this just by finding invariant conservation laws of the original heat equation. Okay, so we write down the condition for multipliers that are invariant under the symmetry. So this is the general condition to find multipliers. This is the condition for the multiplier to be invariant under the symmetry. You can see it's straightforward to compute everything. And I'm happy to give the slides to anyone, so if you want to look at the details. And so we end up with this system, which is straightforward to solve, to find all of the multipliers which give scaling invariant conservation laws. Okay, so here's the general solution. And it involves a function which satisfies this differential equation. And so here is the set of all scaling invariant conservation laws, and they're all non-trivial. Notice that it looks like we have a single one, but actually it depends on this function which satisfies this linear second order ODE. The general solution will have two free parameters. So actually we have a two-dimensional vector space. And so we're going to be able to get two reductions, whereas Soberg only talked about getting one reduction. How do we get the first integrals? So I didn't try to explain in general the formula, but here's an example. You can write the formula explicitly for how the components of the conservation law, the local continuity equation, give you the first integral expression. So that's all done algorithmically. And so now we just plug in and evaluate. And so we end up with this first integral here. So a first integral has the property, its derivative is 0 on solution. So the first integral is just a constant. So you've got an automatic integration of the second order ODE. So now it's the second order ODE is reduced to this first order ODE. But we actually have two reductions, because if we can write down two solutions of this equation, we'll have two first integrals. Two first integrals is enough to completely integrate the second order ODE to quadrature. And so this is all done algebraically. There's no integrals here. So how do we find two solutions of this? It's not hard. So I won't talk about the details, but some of this is from Soberg's paper. But she missed the fact that there's actually two independent solutions. They're simple to find. And so if you use these, in particular, this case for Q is -1, it's easy to write down these solutions. You can do it for arbitrary Q. So I'm not showing you all the solutions, just one example here. So there's the expression for capital U. This is obtained algebraically just by combining the two first integrals, eliminating the first derivative. And then you plug back into little u and you get this. And this is a very interesting solution. If you study the heat equation, this will be instantly familiar to you. This is the fundamental propagator solution for the heat equation. It's just one example. There's many others we can get. So you can do a lot more with the method than what Soberg did in her original paper. Okay, second example. How are we doing on time?
We've got 25 minutes.
Great.
25.
Okay, so second example, compacton equation. So we heard about the soliton equations in the introduction. Solitons are solitary waves. So these are localized traveling waves. The famous example from the introduction was the tsunami solution for the Korteweg-de Vries equation. That's shallow water wave theory. It describes the shape of tsunamis propagating in the open ocean. Solitary waves and solitons have been well studied, but they do have these infinitely long, exponentially small tails, which maybe you could say that that's not really physical, what would be more interesting would be if we had a solution that has compact support. So it's say 0, and then it turns on and we have some wave profile, but in a compact spatial domain. So some equations were introduced in the literature to model this kind of thing. So here's a generalization of the KdV equation that we saw. The key part of it that's important is instead of just this linear dispersive term, there's a Q power on there. And it's exactly that Q power that allows the compact support solutions to exist as opposed to the tsunami type solutions, the solitary wave solutions. Okay, so let's say we wanted to do the traveling waves that we heard about in the introduction. So normally you get the ODE as we saw, and then you'd have to integrate that. The point here is I'm going to show you that we don't need to integrate. We're actually going to get a 4-fold reduction just by using the invariant conservation laws. And that's going to be enough to actually get some explicit solutions without any integration. So just all from algebra. So our algebra friends in the audience will like that, I hope. We don't need calculus anymore. Where are we here? Yes. Okay, so here's the ODE for traveling waves. So it's 3rd order. It looks complicated for this equation. But what we're going to do is, instead of trying to integrate this, we're going to use the inherited first integrals. Okay, so invariant conservation laws. Again, you can set up everything straightforwardly using the general results I described. And then you just solve for the Q's. Okay, there is some calculus, of course, in solving for the Q's. But here's all the solutions, and you can see they exist for different values of the powers in the original equation. So the P was this the nonlinearity power. The shallow water wave case, P is 1. The Q is the new parameter. So these two exist for arbitrary P, and then these two extra exist exactly in the case of most physical interest. Now, it's straightforward to write down the corresponding invariant conservation laws. And then the way you get the first integrals is through the simple algebraic formula. So you can take each of these 4, you'll get a first integral, which is an integration of the equation. So we can, in the first case, we can get 2 integrations here. We can get 2 integrations in the first case. In the second case, we have 1, 2, 3, 4 integrations. Okay, so in the first case, here's the 2 first integrals. You then just combine these to eliminate the to eliminate the second derivatives, and then you reduce. So you started with 3rd order nonlinear ODE. Algebraically, you're now down to a 1st order nonlinear ODE that's separable. So now it's straightforward then to reduce this to quadrature. Perhaps more interesting is the second case. With the physical nonlinearity, then you get 2 more. So it looks like you have 4. It turns out they're not all functionally independent. There is one relation between them, but you still have 3 that are functionally independent. The original differential equation's 3rd order, 3 first integrals is enough to algebraically get you the general solution. So here it is in this case. And then here's the corresponding compact-on solution.
The Q3 and Q4, you know, your terms on the slide.
Yeah.
Is the relationship with the Q3, Q4?
So each of the Q's gives rise to a corresponding conservation law. So this is for Q1, for Q2, for Q3, for Q4.
But I think we asked me why it used to 3. Because in your next slide. No, not that.
So in the first case, you only have the 2 because P is arbitrary. In the second case, when P is 1, you pick up the other 2, and now you have potentially 4, but only 3 of them are functionally independent.
That's your question.
I wanted to understand. Okay, maybe it's time.
It's more of a,
Why would you use 3? Because of that relationship.
yeah. I mean, obviously there's no theorem that says they're all going to be independent. So here's an example where they're not. but they are first integrals. I mean, each of these is a first integral, but
Just so happens that there's a relation.
happens to be a functional dependence between them. Okay, but anyways, you have enough. The point is you have enough. You only needed 3. And you have 3, and that's enough for an algebraic solution. So you get the compacton solution for free, which is very nice, very nice. Okay, so third example, I'm going to look at the KP equation. This is the shallow waterway tsunami equation that we heard, and now this is a 2 spatial dimensional generalization of that. So it describes shallow water waves in 2 spatial dimensions. Has many important physical applications besides water waves. Now, what's interesting for this equation is that you can have what are called line soliton solutions. So these are traveling waves in 2 independent variables. So they'll have a speed and they have an angle in the XY plane. Okay, and those are encoded in these 2 parameters, the mu and the nu, determine the speed and the angle. These are symmetry invariant solutions. The corresponding symmetries look like this. And so we're now going to show how we can get the line soliton solutions by this multiplier method combined with the invariance condition for conservation laws. Okay, so here's the system for finding all conservation laws, multipliers, and with the condition that we are invariant under the 2 symmetries. So in contrast to the previous examples, here we have a symmetry group. Did I say what the commutators are here? No, I guess I didn't, but it should be obvious. These symmetries commute. So this is abelian 2-dimensional symmetry algebra. Okay, so now we go ahead. We solve this system for the Q's. It's straightforward by Lee's method. So as I pointed out before, the more equations you have, the more overdetermined, the easier it is to solve. So here's 4 solutions, corresponding invariant conservation laws. And this is the differential equation for the line solitons. And this is the formula that tells you the first integral in terms of the components of the local continuity equation. So again, we just plug in and we get these 4. It turns out that 2 of these, so there's relations amongst these, 2 of them are functionally independent. And when we eliminate derivatives, so there's the 2 that are functionally independent. We eliminate derivatives. And if we're interested in having the usual asymptotic decay conditions for solitary wave solutions, then these constants from the first integrals are determined. They're just equal to 0. So then when we combine these 2, we get down to a first order ODE. So the original equation was 3rd order. And so through these invariant conservation laws, we're now down to first order. So we accomplished 2 integrations for free. This is separable. And so then we can get the general solution by quadrature. Yeah, good. Okay, so next example, again, is going to be 2 symmetries. This is a wave equation, again, in 2 spatial dimensions with a general nonlinear power. Okay, so there's lots of applications of this kind of wave equation. And we're going to look at solutions under the following symmetries. So the first is going to be a traveling wave symmetry. But instead of assuming a plane wave, so a plane wave would mean that you also have invariance in the planar direction orthogonal to the direction of travel. Instead of imposing invariance, as people usually do for plane waves, we're going to assume a scaling form in the transverse direction. So then we'll have this 2-dimensional algebra, non-abelian. We look at the joint invariants, so there they are. This is the usual traveling wave variable modified by the fact that we have scaling in the plane orthogonal to the direction of motion. Okay, so these are not going to be non-plane wave solutions. All right, so the ODE that describes these is this complicated second order ODE. You know, and the general form of this, if you can see you have a damping term here, and of course the nonlinear term. So this in general is hard to solve. We'll see how we can get integrations directly from invariant conservation laws. So we write down again the condition for invariance of multipliers. And here we have to take into account that we have non-trivial structure constants. So I'm not explaining any of the details, but that term does come into, it's hidden in one of the coefficients here in the condition for that scaling symmetry to give you an invariant multiplier. So this is the overdetermined system. It's straightforward to solve. And we end up with solutions. So they only exist for certain powers of p, but that's not surprising. So there's a -3 case and the 5 case. So in the first one, we have 3 multipliers. In the second one, we have the previous ones together with this new 4th one.
And each of those Qs is now associated with each of those symmetries.
Yes, with both, with the algebra.
Because you did it jointly.
Yes, because I did it jointly, exactly. So these Qs give rise to conservation laws that are invariant under the 2-dimensional symmetry group. So there they are. These have physical meaning. The first one is just energy, and the second one is X momentum. The third one is Y momentum. They're actually conserved for all P, but the only case in which they're going to reduce to first integrals is going to be in this special case here. Okay, and there's the 4th one for p equals 5. Here's the formula for how you get the conserved integrals from the components of the local continuity equation. So by the same steps as previous examples. In the first case, p is -3. Again, only 2 of them turn out to be functionally independent. Whoa.
It was changing there for a while. So
Okay.
it's fine.
At first I thought I was spacing out. Okay, so here's the 2 first integrals. So remember our ODE, it was a damped oscillator equation. It looked really horrible. You know, if I asked you to integrate that, you would probably just throw up your hands and give up. But here we get 2 integrations for free. And so 2 integrations means we have an algebraic solution. So this is the general solution in the case p is -3. So without any integrations, we have the general solution of that complicated damped oscillator equation. Yeah, that's cool, huh? So it's way better than just Lie reduction by itself. So again, to emphasize, if you were just doing straight Lie reduction, I mean, you would have gotten to, where did that OD? Yeah, you would have gotten here.
Yeah.
And what would you do? You know, what would you do with that? You know, look for symmetries. I mean, anyways, it looks complicated here. The point is for free, because this is all algorithmic, and we put in a Maple worksheet and just hit execute. And I can show you, if you're interested, I can show you, you know, and you get all the way down to here for free, which is the general solution. So we've integrated it. So of course it must have hidden structure, but the point is this is pulling out the structure automatically. All right, so there we go. And this is actually a physical solution. It doesn't have particularly bad behavior or anything. The p equals -3 case where it exists, it's actually an interesting power. It's the critical power for scaling invariance of the H3 Sobolev norm. So if anyone does analysis, I mean, that's a perfectly good function space to be in. The next case, p is 5. You do have that extra conserved integral, but sometimes it can turn out to be 0. That's what happens here. There's no guarantee that it has to be non-trivial under reduction. But you still have, you can still use the previous first integrals. P equals 5 is also a critical power. This is the critical power for the energy norm. And there's a typo here. It should be R2. So, you know, this is picking up interesting powers and so on. Okay, so how much time now?
You have
9 minutes.
I feel like I'm asymptotically slowing down here.
No, it is-
Okay, but there's enough time to do this last example and then some concluding remarks. So porous media equation, and here I'm in n dimensions. Porous media is a very important equation with lots of physical applications. So this is the Laplacian operator in n dimensions. P is an arbitrary power. We're going to now do the case of a non-solvable algebra. So this is a case that you couldn't even approach by a Lie symmetry reduction. And what we're going to do is look at rotation and scaling symmetries. So here are the rotation symmetries. So they're generated by rotations in two planes. They can be parameterized by this anti-symmetric matrix. And then we have a scaling family, just like we did for the heat equation, like this. And so here's the algebra for these. This is a non-solvable algebra because of this relation here. Okay, what we do is we look for the joint invariants. So there's one that involves r's the radius in n dimensions, and that's our dependent variable. Here's our independent variable. Here's our dependent variable. So the solutions will look like this form. And here's the corresponding ODE for them. And so again, that looks fairly complicated. You know, it looks, you really wouldn't want to have to solve that directly. So what we do is we set up the condition for conservation laws to be invariant under this whole symmetry algebra. So there's the conditions. And then it's straightforward to split and integrate this. And so here's the solutions that we get. So there's a conservation law. So Q is a power in the scaling. So this relates the scaling of the independent variables to how the dependent variable scales. So there's that case, and then there's this case. Okay, so we get two symmetry invariant conservation laws. Here's the formula that gives you the first integral in terms of the components of the conservation laws. Okay, so what do we get? It's very interesting. So in the first case, so we're getting, there's our first integral. So we've reduced that complicated second order ODE to this first order ODE. If we just put C1 equals 0, then this separates and it's a first order ODE. It's easy to integrate. There's the explicit solution. And this is very interesting because for when our nonlinear power in the original porous media equation is less than 1, this is the fundamental solution. So if you have a Dirac delta initial condition, so porous media would describe something, for example, like water flow through porous rock. And if your initial mass of water is concentrated in a Dirac delta spike, then this is the corresponding solution. So this represents the fundamental solution for that nonlinear PDE. So this is physically a very important solution. And so we got it here basically pulled out from this method very naturally. In the second case, this is what our solution looks like. There is our first integral. What's interesting here, again, this looks complicated to integrate. You could try the case C2 is 0, but actually it turns out this has a hidden scaling symmetry, which is just obvious by inspection. If you just look at this, well, if you're familiar with Lie group methods, you'll notice immediately by inspection this has a scaling symmetry. And so therefore we can just use the scaling symmetry to reduce this to quadrature. And so there's the explicit solution by quadrature. I'm not sure what the physical meaning is for this one. But anyways, the point is with this method, we're getting a lot more than just from what we would get from standard symmetry reduction. Okay, so I'll finish up with some conclusions and then we'll have, I guess, hopefully time for questions. So conclusions, all steps in this method are fully algorithmic. They have straightforward implementation in Maple. So we can apply this to PDE with any number of independent variables. A symmetry algebra of suitably large dimension will work for doing the reductions. We obtain all symmetry invariant conservation laws such that they reduce to first integrals for the ODE system, describing group invariant solutions. When the symmetry group has dimension larger than 1, the reduction here is carried out in one step. Or if we have, the space of symmetry invariant conservation laws is larger than one-dimensional, the reduction is again carried out in one step. So we don't need to do successive reductions. The symmetry algebra is not restricted to be solvable. So that's going beyond what you can do with just plain Lie symmetry reduction. We have some work in progress where sometimes, so here I've been assuming we have a symmetry of interest. What if you're just interested in any solutions without imposing any symmetry a priori? So it turns out you can generalize the method so that you're finding both the symmetry and the symmetry invariant conservation laws together at the same time. Okay.
So the symmetry is also the unknown.
Yeah. Yeah. So that's in some forthcoming work with Gundarius. All right, so let me stop there. Thank you very much.
So the statement I like to make it's not. It hasn't come a long way. It's going a long way. This whole notion of relationship between symmetry and conservation laws.
Yeah.
Luther was excited. So you know.
Yeah, Peter has heard this talk. He was excited.
Any questions from the audience? Sergey?
There's some examples like for God bending equations.
We're working out some examples, but I mean, in principle, you could do it for any system you want. So in terms of published examples, we have not published anything yet, but we are working on such examples in contact with this last point. So yeah, of course, I'll send it to you if you're interested once they're in preprint form.
Thank you for the wonderful talk. Conservation laws exist where the PDE is already ODE.
Yes.
We get the ODE, we reduce, let's say, from the PDE, and we can search for conservation laws.
Yes.
ODE.
Yes.
We get the same conservation law.
Well, potentially you could get more,
Or more, yes.
right? Because here we're finding the ones that are inherited.
Yes.
There can be hidden ones.
Yes.
Like in that last example, we had a hidden symmetry, right? This symmetry is not being inherited. It's a new symmetry that arises. In a similar way, we could have new first integrals for the reduced ODE, certainly possible.
So instead of searching conservation laws for those PDEs, since I can reduce it to the ODE,
Yeah, then you could,
and go directly.
you could.
But my question is there any example, that's why I'm interested, where we can get non-local conservation laws using that approach?
Sure. You just have to set things up.
And if this example, examples that we presented,
Yeah, they're all local.
yes, but can we construct non-local?
Yeah,
That will be.
Yeah. sure. You just introduce a potential at the beginning. So that would be a further extension, a non-local extension of the method. But the way I view it is, I mean, at the beginning, you set up the potential and then everything is again local after that.
Yeah.
So in my mind, it's not really anything new. It's just having a different formulation of your original problem.
But we can introduce constraints there.
You can. Yeah, sure you can.
Yeah, so just a comment about Astrid Schober, who was a favorite student, that when they left South Africa, she gave up mathematics for a dance studio in Australia.
Ah.
Well, so I kind of work on it. Double redundant. Actually, any more questions?
Thank you. Wonderful talk. Recently, some researchers working on by applying a least symmetric group of transformation method to finding an analytic solution. There are the varieties of analytic solution and as well as to show the conservation law in a physical quantity manner. So we have to show in the research paper to both conservation law and the analytic finding the analytic solution or the constant on the just conservation law.
Okay. If you want Analytic solutions for,
Because I'm working on the solid term theory.
Yeah.
Using the wave type of equation.
yeah,
So I am asking to you that we have to show the conservation law because it's some physical quantity.
yes,
And
like energy, momentum, etc. They're all physical quantities. Every conservation law has a physical meaning, even if it's not self-evident.
But we have constant for finding the conservation law. So we have a constant on some restrictions.
Not really.
Yes.
I would, my answer would be no, not really. I mean, all conservation laws are useful in analysis. It just depends on the function space that you're interested in. Yes, if you insist on being in some particular function space, then a constraint may arise on a conservation law, whether it makes sense in the context of that function space. But there's always a function space for which the conservation law makes sense and has important information about solutions. Okay.
And the last, so we have to show the both findings and analytical solutions as well as conservation in the result.
Well, that's what I do. I think it's good to provide readers of your paper with the maximum information you can get.
Thank you.
But we can talk more about that.
Okay, Saurabh?
There's a question from the online audience. It's a question from Jean de Dieu Marie Ragoha. For a class of differential equations which depends on arbitrary elements and derivatives, like Schrödinger equations, can this method be applied?
Yes, there's no restrictions.
Okay.
And in fact, it's better, the more arbitrary elements you have, the more you can find for it, because there'll be special values of those arbitrary elements for which extra structure exists.
And you've got Maple set up like this with these
Yeah,
joint
if anyone
calculations.
is interested in the actual calculations, I can show you on my laptop. It's very simple.
That'll be interesting. Yeah.
But as was pointed out in the beginning, it's very important that you know programming.
Yeah.
To utilize Lie symmetry methods and their extensions to the fullest possible extent, you really need to know some programming. Now, there are black boxes, like in Maple, there's a software called GEM, where you can literally just put in the equation and press a button and it tries to compute the symmetry group. The problem is sometimes the computation stalls or sometimes it misses solutions. So I never use that. I do everything myself, where at each step I can convince myself that the system has been solved correctly and no solutions have been lost. But if you're using GEM, you cannot use it for proving theorems because there's no guarantee of completeness. Maple has bugs. Maple.
Tomorrow, because in Maple, sometimes there is answer, but it is some particular answer. You
Yes,
don't know what
yes,
it is.
yes, yes. So do not use Maple to prove completeness theorems or classifications theorems. And yeah, reduce is better in that respect. I agree with that.
Because you know what they are doing.
Yeah, because you know what you're doing. But I use Maple like reduce.
I've actually seen you do that. So yeah.
So anyways, but the big point, as was mentioned, it's very important that you know programming if you want to exploit Lie symmetry methods to the maximum extent.
Stefan, thank you very much. Wonderful talk.
Thank you.
It's tea, coffee, I believe. Am I right?
You can announce, yes.
The online guys will not.
Yeah, you have to announce on that, and then we have to be back here, in the room, by 5 minutes. 5 minutes to 11, so that we start at 11 exactly. And the next speaker should have their talks ready.
Yeah. Have you heard that? Let's be by 5 to, I think is to the bathroom. Thank you very much. Okay, thank you.
Try to stretch your legs outside.
Stretch your brains.
Yeah.
What do I do with this? Why is it fluffy?
So we're also looking for chairs, sorry. If you want to chair a session, it's good for your CV. So just volunteer, then we'll slot you in. Ali, who's online, will just put you in. Thank you.
Thank you for very
It's good to meet you finally in person.
We are close several times.
Yes, I know. It's not the first in my career, but
Really gone a long way this way.
yeah.
Yeah.
Way of doing things.
I mean, in that Saudi presentation with us, because you were still a good few steps
Yeah.
behind.
Yeah.
Amazing.
Yeah.
So you're really going on. I mean, that is putting the unknown on the symmetry.
Yeah.
So you
Yeah,
get this
yeah,
whole
yeah,
thing just
yeah.
coming up. It's like you don't have to check.
Yeah. Exactly.
It just comes out.
It just
This
comes
is-
out.
So people that and
Yeah.
contributes.
Yep.
Wonderful.
That's good stuff.
I think that the teams on the veranda. I think
No, not the yellow one, it was the.
No, he's got it.
No, the one with us. And then we have to get the next one.
Sure. Yeah.
Where's Professor Mensah? Sorry.
Yeah. If you can find us any other people, we can have a session. Yeah. I'm happy to do that.
Sure.
Oh, you are.
Oh, yeah.
Are you going to announce about the?
Yeah. Okay, louder.
So what the heck about they come here, what? Yeah.
No, there's something else with the dinner.
So what is their rating?
Okay,
The bus,
yeah, leave it from here to there.
so a bus for everyone.
Yes, for everything we leave from here.
Okay, that's tomorrow.
Eventually.
Oh, even today, but what about tomorrow?
We leave it for the next time.
It's not 11 yet.
Uh,
It's not 11 yet.
It's 4 minutes before. Okay. So tonight it was, you said 5. It's 5.
Yeah, it's 5.
Okay.
And then
So the bus will be enough for everything. Okay, 5:15.
yes. Because we finish. It's cocktail at 7.
Okay.
So before usually take 45 minutes. But then finish them at 8.
8.
Yes. Yeah, depending what time you need, we're guessing
You
5:05.
I think you better announce as you're speaking. There you go. There are 2 things. You better do that now. Okay, so there's an announcement. Yeah, while we wait a few minutes, I give you 1 minute.
Giving me 1 minute.
Please don't take it from my time. I need
Oh.
my 30
No,
minutes.
it's just doing announcements before we start to allow the people to come in.
For-
Alright. Okay, for the people.
So for today,
You
the
have to
shuttle.
speak louder like
Oh.
it can. People can't hear you.
So for today, the shuttle will leave here at 5:15 to go to main campus. And then at main campus, the shuttle will pick you up at 8:15 to take you back to the different hotels. And then tomorrow night for the dinner, we'll leave here at 8:15 to take you to the restaurant.
What about +8?
Sorry, 5:15, sorry, because we start the dinner at 6 p.m. Sorry. So so today and tomorrow, 5:15, the shuttle will fetch you here, and then 8:15 tonight, we'll take you to the different hotels. If you haven't given me where you're staying, please let me know during lunch so that we can organize accordingly. And I'm hoping the dinner will finish at 8:15 to 8:30 tomorrow night.
Not midnight.
Yeah, not midnight, so that's but yeah, please 8:30 at least.
Is this tomorrow 8:30?
Yes, I don't know what time you want to finish your dinner tomorrow.
We don't know. It depends on how fast they.
But Chico told us that there's going to be some kind of dance party after that.
Yeah, it depends on you, so.
Yeah. He's arranging the music. Okay.
Who will be the chair?
I will keep it here.
Thank you.
Okay, colleagues, so it's 2 minutes before. I don't know if there's anyone outside left. So, but I think everybody is here. So welcome to the second session, and it gives me great pleasure to introduce Andronicus, who's with us today, who's visiting. Thank you so much for visiting Cape Town. He's based at Durban University of Technology, but he also has spent some time in the Cape visiting UCT and also Stellenbosch at this point. So he's going to talk about the mini superspace description in gravitational physics and the role of symmetries in quantum cosmology. So you have some time, leave some time for questions at least, and then I will show you according, we are keeping the time. I will show you when it's 5 minutes before. So can we give you the floor? Give him a hand, please clap for him. Thank you.
Am I the only physicist here?
No, is there anyone else from physics here with a physics background? Yeah, there are some of us halfway, not full. Yeah.
Okay, thank you. It's nice to be here. I would like to thank you, Abdul and Sibu, for organizing. I will give a talk, which I will try to explain and show how we apply symmetries in gravitational physics from the large scale to describe the universe until the very, very small scales of the universe in quantum cosmology. So the plan of my talk is initially I will talk about what we call Zekeres exact solution and inhomogeneous cosmological models. I will discuss about the dynamical evolution of the Zekeres system, how the universe evolved during its time evolution, the integrability properties of the Zekeres system, and finally, the quantization and semi-classical limit for the Zekeres system. In all cases, the symmetry play a significant role to describe the theory. So from cosmological observation, we know that in very large scales, the universe is isotropic and homogeneous, which means that if we see the sky in one direction and we count the density of the galaxies, we will get the same density in any direction we look. And if we start in any position, looking again, if we move, let's say, in another galaxy, we'll get also the same, we'll count the same density of galaxies. So that means the universe is inhomogeneous and isotropic, and the density of the galaxy does not depend on our position or where we look. And when we do cosmology, we start with something it's called the cosmological principle. And the cosmological principle is a set of statements that define the theory, the mathematical theory that we consider to describe the world. Initially, we believe that we consider general relativity, Einstein's general relativity. We assume that the space-time has a dimension 4, where the one dimension, where we decomposable in 1 plus 3 dimensions. The 1 dimension is what we call the time, and the 3 dimension is the context of the space. The subspace of dimension 1 is the time, okay, and the time, the dimension of the time is important to construct the observer. According to the cosmological principle, the observer is a comoving observer which is perpendicular to the space direction. Now, the 3-dimensional space describes the physical space, and in order to be homogeneous isotropic, it should be a space of maximal symmetry. Admits 6 isometries. It's a space of 3-dimensional. It means 6 isometries, and it means that it is the Euclidean space, or the sphere, or the hyperbolic sphere. That leads to the geometry to be what we call the Freeman-Lemaitre-Robes-Walker geometry. The matter, since we are in general relativity, is described by tensors, which inherits the symmetries of the local cosmological model. Since the space-time is isotropic and homogeneous, the same should exist and for the matter source. As you can see, the symmetry play a very important role on the description of the physical space. So now, however, while we consider that the universe is isotropic and homogeneous today in the very large scales, maybe that wasn't true in the very early stages of the universe. There is a proposal solution for this, inflation. So if you consider the universe as a balloon and the galaxies are, imagine that they are dots on the balloon, you put them randomly, homogeneously, and with an anisotropy, if the balloon explodes, increase very fast, then after a moment, everything will be isotropic almost. However, in the very early stage of the universe, before inflation, the universe, maybe it was inhomogeneous and anisotropic. So it's not necessary to set initial conditions for the original problem, which are isotropic and homogeneous. So we have a category of models which are called homogeneous space-time, and they are exact solutions of Einstein's general relativity, where in general there's no any symmetry for the physical space. Now, homogeneous cosmological models are those which does not satisfy the cosmological principle, but they provide the limit of the Freeman-Robes-Walker as an asymptotic case. And some non-homogeneous cosmologies are the ATB metric, the Zeker space-time that I will talk today, the Stefani metric, and the Barnes metric. There are many applications of the homogeneous space-times in cosmological evolution, and especially in the description of the very early universe. Also, they have been used and they can be used as analytical approaches for the description of the small homogeneities in the CFB spectrum. I'm sure you have seen the W map, which shows the heat, the radiation map of the universe measured by Planck. And that's also this way to describe the large-scale structure of the universe, the formation of the mass. Now, Zekeres, 1975, published his pioneer work by solving the Einstein field equations. The left part is the Einstein tensor, and the right-hand side is a matter source, where the matter source is considered to be that of a gas fluid source. It's a fluid which has no pressure. In the modern cosmology, a kind of fluid that has no pressure, we believe that is a baryonic matter, the matter that we are formed. It has a very small pressure, so it's negligible, and what we call the dark matter. Now, for the background metric, Zekeres considered this light element, which in general has no symmetries. Now, the Einstein field equations can be solved explicitly, and the solution spacetimes can be categorized in two families of solutions, which are called the Kadowski-Sachs universes, which describe anisotropic spacetimes and homogeneous spacetimes. That's why I like. And the Freeman-Robisch-Walker-like spacetimes, which are inhomogeneous spacetimes but isotropic. Now, the Zekeres spacetime belongs to a more general family of spacetime known as silent universes. My presentation doesn't change, and okay, I think I lost it. Okay. Okay. Zekeres spacetime belongs to a more general family of spacetime known as silent universes. Silent universes are universes where there is no information through sound and gravitational waves. So we will have two different observers, two different work lines. They cannot communicate through, they cannot extract information with sound, since there is no pressure in the fluid, and without, there's no gravitational wave emission, since technically the magnetic part of the wild tensor is zero. There exists a surface of constant curvature, and from a group from UCT published a paper in 2000 that they claim that they are partially locally rotational spacetime. So there exist the LRS symmetries at the asymptotic limit. And I talk about, and there is no gravitational radiation emission from the moving dust. Now, in terms of we can use a kinematic approach to write.
Doesn't change it?
No. Okay. We can use the kinematic formulation of general relativity established by George Ellis from UCT and that group, that period, and write the field equations of Einstein general relativity in terms of fluid dynamics. So again, I'm sure that you will like that form. So rho, the Greek rho is the matter density, and this is the continuous equation conservation law for the matter, which states that the matter is constant. Theta is the expansion rate, depends on the observer. It defines what maybe you have heard as a Hubble function. Sigma is the shear, which corresponds to the anisotropy of the universe. And E is the electric part of the magnetic tensor. Except from these equations, we have also the very important constraint equation. And we have also the constraint equations, which are derivative. These are covariant derivative in terms of the space like coordinates, space coordinates. Now, a dot means a derivative in terms of time. So the complete set of the equations are these, which are derivatives only on time, and these equations, which are partial derivatives in terms of the space coordinates. So these four, this system, form the Zekker system that while we will work out the cities as it is a system of ODEs. However, the digression constants that they have depend on the space variables, and they are just constrained by this set of equations. We don't have to work with these. We can omit them since we just replace and find some constraints for the solution functions. Now, Zekker solved the system of the field equations, and he found that the solutions belongs to two classes. The class A, which are the Kapowski-Sachs-like solutions, anisotropic solutions, where these are the exact forms of the scale factors. And these are functions, homogeneous functions, which they just constrained from the previous equations. So the final space-time is an anisotropic and homogeneous space-time without any symmetry in general. A special case of these spacetimes is LTD metric, the class A LTD metric, which has this explicitly form. And as you can see, it's an homogeneous metric. And this term, for instance, when t is equal to t0, it vanishes. That states that this metric has a singularity, the spacetime has a singularity, but the singularity depends on the position, on x. So if we foliate the spacetime in different planes, the initial cosmological singularity moves not only the work line of time, but also in the space direction of x. The second class of solutions are the Freeman-Robes-Walker-like spacetimes, where the scale factors are described by these expressions, and the final solution is given by this equation. I didn't mention this. This system of second order differential equations is a very well-known integrable system. And also this system, it's known also, it's a well-known integrable system. You can see that these equations are not exactly relevant. This one has a conservation law, this is the Hamiltonian. So I will replace this. This is the Hamiltonian, and the Hamiltonian value, the constant is the energy density of the matter source. So they are not so irrelevant. Now, there are various extensions for the Zekker system, which introduce other matter sources term. Zafron, 2 years later from Zekkeres, introduced a perfect fluid with isotropic homogeneous pressure term instead of dust fluid. John Barrow, who inspired me to do this work, did a study in '84 with a cosmological constant term. Heat flow, electromagnetic fields, viscosity terms introduced much later. Now, in order to understand the general evolution of the universe, we have two branches of solutions. So, how we can consider initial conditions when we solve the system and to see how it will evolve. So we will perform, I will present you a short presentation of the dynamical system analysis for the Zekker system, which states, which give us important information about the evolution of the universe. Now, we introduce some dimension variables known as in the H normalization approach, where the field equations can be written in a much simpler form. We apply Now, we determine the stationary points, and every stationary point we know that it corresponds to a specific asymptotic solution for the system. We can extract very important information from the values of the physical parameters at the asymptotic point. For instance, when parameter sigma vanishes, then we shall say that the solution of the critical point has no anisotropy, so it belongs to the Freeman-Robes-Walker-like spacetime. The value of the spatial curvature is calculated also by the algebraic constraint and give us important information about the spatial curvature of the universe. When sigma is different from 0, the critical point describes the Kadowski-Sachs solution, except when omega r is equal to 0, the spacetime reduced to the Bianchi-1 spacetime. Now, these are the critical points in terms of omega, sigma, and epsilon. And here is the spatial curvature, and from the stationary points we can construct the physical space. Now we have 2 points that they are not physically accepted. These are physical points. However, that give us very important information about the constraints we should apply for the initial conditions of the system. So if we start from, we should take initial conditions for the system where the solution trajectories will not pass around these 2 stationary points. So that gives us extra constraint. Now, we studied the stability of the solution, and also from the stability, we will get this word. Go. Okay, I should press the resolution for that. Now, it has a delay. Now, the first point belongs to the Freeman-Robes-Walker like, it's a Milnor-like universe. So here is the stability properties. These are the stability properties, and we see that the Bianchi-1 space-time, which is a special case of the Kadowski-Sachs universe, where they are anisotropic universes with 0 spatial curvature, are the stable solution. And the Kadowski spacetimes are unstable solutions, and that's a nice result, as we'll see later. And actually, they're not just stable, they are sources. Now, the Zagari system is a system of 4 first-order differential equations. However, we investigate the case that if it was Hamiltonian, since we wanted to apply the quantum cosmology, we would like to quantize and study the effects of gravity near to the singularity. We did that work with Peter Leeds a few years ago, and what we did is that we followed an approach to write the 4 equations into 2 equations of second orders and investigate the connections of the autoparallels. So when we did that, we construct connection components for the autoparallels for the second order differential equations. We studied the geometry of the connection. We found that the connection, because the Riemann tensor of the connection is 0. So we proved that it can be linearized, the term of the connection. We can be eliminated through a point transformation. Indeed, if we apply this change of variables in the original system, we ended with this simple form, second order differential equation. The first one, I'm sure you recognize it as also the second one. Now, the system, you see that it admits a Hamiltonian. This is the Hamiltonian. And we can construct the conservation laws, the Lewis invariant. And however, in the limit that x is 0, that describe, let's say, null geodesics, where the volume of the Liouville space is 0, we have additional conservation laws that they, in general, they are not local symmetries, but in this case, they reduce to local symmetries. We have these extra additional conservation laws, which are important for our analysis later. We have a Hamiltonian, and since we have a Hamiltonian, we can do simple quantization process by replacing following Dirac. We write what we call the Wheeler-DeWitt equation, and this is a mini superspace. This is what we call the mini superspace, which defines the Laplace operator. And we can solve by using the conservation laws, construct from the conservation law quantum operators, or using the Lie symmetries for this equation and applying the Lie invariants or canonical transformations. Any methods from the above will give us similar results. Now, its conservation law, its symmetry can give us a different wave function. We don't have initial conditions here, and that's one of the problems with quantum cosmology. We should define the initial conditions in how we can define the initial conditions in the universe, where is the beginning or where is the end. So in any case, we consider the most simple case, where the function is h is 0. We take this wave function, and we were able to define a probability density, integrate it, and study the evolution of the probability. We found that for I0 is 0, the probability function reaches its minimum. So that extrema for the probability can be related to an asymptotic solution from the previous stationary points that we found. And that is the Kadowski-Sachs solution that we discussed before. So it was a very nice observation to relate the asymptotic solution for the asymptotic solution for the classical system with the extrema of the probability density. That gave us an important hint about that wave function. And most importantly, it was like this extrema is related to an unstable solution, to a source. The equilibrium point that describes the solution is a source. Now, when h is equal 0, when h is equal 0, we can define from the rest of the operators extra wave function. And I would like to focus on the final one and see, actually this wave function, these are the Bernoulli functions, but in the limit that this becomes infinity. And that's a condition that states that it's in the very early stages of the universe. You go in the original variables, and then we can approximate it as this form, the first order approximation, and we can see that the wave function describes oscillation of the polar form of this form, where S is this, and this is the amplitude of the oscillation. Now, that was an important observation, and to go later and apply what we call what we call Bohemian interpretation of quantum theory. So in quantum, consider that we have the classical world that we live, the quantum world, and somewhere between is where Bohemian interpretation is coming from. This is maybe you have heard it as Mandeluk interpretation of quantum mechanics, or fluid-like description of quantum mechanics. Now, what is happening there is like when we have the Schrödinger equation, we apply the WKD approximation and we can construct the Hamilton-Jacobi equation for the semi-classical system, for the classical system. when we do that in the WKB approximation, we eliminate some terms related to, because we assume that they are very small. However, we consider that term, they give us an important term, which is known as a quantum potential or a quantum correction term. Now, omega is the amplitude of the wave function which we wrote before, and for the case of the later wave function, we found the quantum potential which is a non-zero. And that means that we have a correction in the Zekeres system related to the quantum effects of the theory. And we'll go initially, and to understand the physics of these quantum effects, if we go in the right side of the equation, we see that physically we have a new term here that violates many parts. Now, these new terms provides a new asymptotic solution for the physical space, which is an anisotropic solution where we can have a matter source. So this quantum term provides a matter source in the universe, which has mass, which has a non-zero pressure term, and that was an important part here, and it has an anisotropic stress tensor. And so more or less, that source can be used. That source can provide a way to explain as an initial start for the inflation that we found later. And most importantly, we found that the quantum corrections violate the silence property of the Zekeres space. So, and it's clear that quantum effects can play a very important role in the very early stages of the universe. So thank you a lot.
Thank you so much for the presentation. So do we have any questions? Any questions? Yes. Can I give you the questions?
Thank you very much. First question, it is about metric. How do you choose metric? So because there's many functions there, which one to choose and what is property of these functions? That is first question. And second question, actually, maybe it is related. You talked about that some your solutions have no physical meaning. What does it mean?
Yes. Okay. Thank you, Sergey. Thank you. The way that we tried, we consider a general four-dimensional space-time. So we tried to impose constraints on that space-time by having a more simple description of the world that we see today. So in the most simple case, if you take a four-dimensional space-time and admit that it has 1 + 3 violation, and you apply that is maximal symmetric, that's direct constraint. It gives you the Freeman-Robis-Walker geometry. If you, on the other hand, consider that you have, for instance, three-dimensional three symmetries, that problem solved exactly from Yankee, you can have 9 different spacetimes. So that gives you the metric with an arbitrary scale factor, with arbitrary scale factors. So these scale factors are given, satisfy the Einstein field equations. And so that's how you try to extract physics from geometry and etc.
I think we can have, yeah.
For the second question, it's like we have a mathematical construction, but not all solutions are physically accepted. For instance, in the above example, points, negative energy, density for the mass.
Yeah, thank you for that. I think at least that clarifies those points. Is there any other question? Otherwise, we will have discussions over lunch or tea. So thank you very much. Let's clap for him. And then may I ask, thank you very much. So may I ask Professor Mensah to come through? And thank you.
Yes. That's fine. Yes, it's that one. Fully Bechula, but just make the J.
Bechula,
Yeah, yes.
Okay, so our next speaker is Professor Mensa Foley Bechula. He's going to talk about, okay, yeah, we can go on. So he's going to talk about the on a family of higher order difference equations, symmetries, formula solutions, periodicity, and stability analysis. So if you can leave some 5 minutes for discussion in case people want to ask me next
So I have 5
questions.
minutes.
Yes, thank you.
Okay, hi everyone. So yeah, my name is Mensa from the University. So my talk will be on difference equations. Okay, so we'll be looking at symmetries, analytical solutions, periodicity, and stability of a family of difference equations. Okay. So okay, cool. So we just like differential equation, we know that there are different methods for solving differential equations. Okay, so one of them is separation of a variable, like Prof. Moyo mentioned earlier. So there is one of the methods. So sometimes that separation of variables, sometimes it's just a guesswork. Okay, because it's not every time that separation will work. Okay, so when do we know that maybe we have to use separation of methods or any other methods? One of the answers to that question is symmetries, okay? Because it helps us to get the correct change of variable that will allow us to reduce the order or maybe sometimes the number of variables if we are dealing with partial differential equations. So we know, that symmetries is one of the powerful tools for solving differential equations. So what we are trying to do here is to see if we can just use the same tool, okay, and apply the same tool to difference equations, okay, so to difference equations, okay. So again, we'll be looking at symmetries. I remember when we started applying symmetries to difference equations, we were looking at symmetries, things like first integrals, okay, okay, and we also look at the association between the symmetries and first integrals. And we saw that for the case where the symmetries and the first integral are associated, we can perform double reduction. Okay, and we also look at multipliers. Okay, and we saw that multiplier, the same method works for difference equation. I heard Prof. Enko spoke about multipliers method that allows for multiple reductions. We've applied those tools to some of the equations, and we got some interesting results. Okay, so later on, what recently, so when finding an analytical solution, we've noticed that it's not always easy to find analytical solutions. Okay, so I've noticed that people that are working on a difference equation, sometimes they don't know the solution, but they look at the behavior and things like that. So recently I've decided to look at the stability, periodicity, and things like that. So in this talk, I'll be talking about symmetries and the behavior of the solutions. Okay, so of course we apply this to non-difference equations like discrete Penlevé, so many equations we were able to use symmetries to solve this difference equation. But because of the stability aspect of it, I've decided to use one example that I got from a recently published paper, okay, on internet. So this paper one, I'll show the reference when I'm done with the talk. So it's a paper that was published this year. So I'm just using this equation as an example just to illustrate how we can use symmetry to solve difference equations. Okay, so in that paper, the authors considered equation number 1, okay? So obviously we can guess, the change of variable that might help us to solve that type of equations, but we just want to try to and see if symmetry will help. Okay, So they studied the equation 1, okay, and they use plus or minus here. So I was like, okay, let's see if we can use symmetry and try to see what will happen if we replace those plus or minus 1 by maybe sequences, okay, using symmetries, of course. So we'll be considering equation 2, and we'll be applying symmetries to solve that equation. Okay, now that equation that we are trying to look at, you can see that it's coming from this well-known Beaverton models, okay, for a suitable change of variable, we can easily get this previous equation, okay? So this equation is related, okay, to the well-known Beaverton equations. Okay, now, okay, because of the notation that, okay, good. Because of the notation that we'll be using, we decided to shift the equation 2 so that we can use the notation that Haydn, okay, I believe we all know Haydn. So I want to use this notation. So we decided to shift the equation and get something of this form. Okay, so A and B, the two equations are equivalent, they are the same anyway. Okay, so let's say that we know the initial conditions and A and Bn sequences. Okay, so we are trying to apply symmetries to solve this equation number 4 now. Okay, now here, the problem with this type of equation is that we don't have packages, like we don't have things like reduce or Mathematica that can generate these symmetries for us. We have to do everything by hand. Okay? So we know that if the slide is not okay, cool, no problem. So let's say that we have a general difference equation of the 4K. Okay, again, just like for differential equations, okay, we are using this proof of transformation, and we know that we can always find a generator that we are calling here by B. Okay, and Q here is a characteristic, okay, of the generator. Okay, now again, we will need to prolong this generator, the extension. We have to extend so that we cover all the variables that are appearing in the equation that we are studying. So that's why we are using the prolongation, just like what we do for differential equations. Okay. Now here we have to introduce this operator here. It's the shift operator. Okay, that takes n to n plus I. So we know that with this operator, we can easily, it's known anyway that the symmetry condition, okay, the invariance condition is given by equation number 9, okay? Okay, so this is the symmetry condition that we'll be using to get the characteristic. And once we know the characteristic, we can use this characteristic to get the canonical coordinate and do the reduction. Okay, so question number 9 is the invariance condition. Okay, now just the invariance condition. Okay, so here we'll be using the canonical coordinate, okay, given by equation 10. Okay, so this the canonical equation that Maida, okay, is one of the authors that started applying Lie symmetry to difference equation. Okay, so he used this canonical coordinate that we are also going to use in this talk. Okay, but here what Maida and even Haydn did, they just try to find a relation between Cn plus 1 and Cn and use it to get the solution. But in this work, we will use something similar, but not exactly like the way they did it in reference 4. 4 is Haydn. Okay, so now, like I said, we were not just interested in analytical solution of this. We also want to look at stability and all of that. And it's something that we've started looking at recently. Just last year, I've started looking at stability because I was more focused on symmetries and multipliers and things like that, like I said before, okay? Now this is a part that I've decided to look at recently. Okay, so here we'll be looking at the stability of the definition of stability of the equilibrium point. Okay, equilibrium point is when the point is invariant. Okay, so here we are saying that if the equilibrium point is locally stable, okay, for any epsilon, we can always find a delta such that when we have equation number 12, it implies equation number 13. So that's the definition of local stability that we'll be using in this talk. So the equilibrium point, okay, that we are denoting by U bar here, will be said to be a global attractor if we can find the limit of the UN when n goes to infinity, and that limit has to be the equilibrium point. Okay, these are just definitions that maybe I can just skip. And also, there is this thing they call a characteristic equation, okay, about the equilibrium point, okay, that we have tried to adapt to this symmetry part. So the characteristic equation, okay, about the equilibrium point, okay, is given by equation 16, where the coefficients of that polynomial are given by the partial derivative of the right-hand side of the difference equation that we are studying. Okay. Now again, these are just a definition. So when you use that characteristic equation about the equilibrium point, depending on the roots of that characteristic equation about the equilibrium point, you can classify them and say that they are locally stable and things like that. Okay, cool. Okay, now the symmetry part. Like I said, we'll be looking at equation 17. Now we apply the symmetry constraint, okay, to the equation that we are studying. That's equation 17. Okay, so the symmetry condition is given by 18. Now here we have okay, functional equations. Okay, the inputs are not the same, so we need to find a way to solve this characteristic equation without using computer packages. So that's where the calculations sometimes become lengthy, cumbersome, and all of that. Okay, but look, now to get around this, to be able to solve that the symmetry condition, we first try to eliminate some of the variable to make the equation, okay, solvable. So what we started by doing is to apply this operator 19 to the equation that we obtain using the invariance condition. Okay, when we do that, at least we'll be able to eliminate, going back, we'll be able to eliminate, okay, the first term, this because it's a partial derivative, at least with that operator, that one will go, and we'll have something better that we can easily solve. Okay, so when we apply that operator, we obtain an equation 20. Okay, now that we have to solve for Q, Q is the characteristic that we will need to reduce the order. Okay, so after some simplification, I don't think that I do not want to show the details. It was not that important. Okay, so after reduction, we get equation 21, okay, that we need to solve. So from here, now that we know that at least we've eliminated UN plus 4K, we can just differentiate with respect to UN plus 4 twice. We could have done it with respect to UN plus 8 anyway. So we did it with respect to UN plus 4 twice to get equation 22. So now from here, we can easily solve this equation to get the characteristic. Okay, so from 22, we saw that the characteristic has to be of the form this polynomial plus this. Okay. So again, we need to find the constraint, the condition, the equation that alpha n, beta n, and gamma n have to satisfy for us to get the form of the solution. Again, how we substituted back and obtained the alpha n. I'll just keep that part. Okay, so we replace it back in the symmetry condition just like the way we normally do it for differential equations. Okay, so we've noticed that After substituting back and after simplifying, we've noticed that the alpha n, those coefficients have to satisfy equation 25 and 26. Okay, now from here, it's easy to solve for alpha n. Okay, again, we can skip that. And the expression of alpha n that we've obtained, okay, using, these are just basic mathematics that we normally use to solve a difference equation, a linear difference equation. Okay, so we've used that to get the alpha n. Okay, and after getting alpha n, beta n, and gamma n, we were able to write down the symmetries. Okay, again, their point symmetries, the characteristic only depend on un only. That's and they are local, of course. So we've not obtained the symmetries finally using the same method, the same procedure that we normally use for differential equation, and we were able to obtain these symmetries. Now, after obtaining the symmetries, we are going to use the symmetries for reduction. Okay. So again, we introduced the canonical coordinate. Remember, I said that the canonical coordinate was given by the integral of this divided by the characteristic. Okay, so the characteristic and alpha n, I don't have to use this. I can just use the general form of the characteristic here. So we use that to get the canonical coordinates given in equation 31, sorry, okay. Okay, alpha n, we said earlier, the equation that the alpha n must satisfy, okay, must satisfy. Okay, so doing that, now getting the canonical coordinates, now we need to find the invariance, okay. So we derive the invariance by taking, by replacing Cn alpha n in equation 20. Okay, I don't want to go back to 26, but in one of the equations to get the invariance. Again, we have applied the symmetry that we obtained, okay, on this invariant, and we get 0, which means they are, that's to confirm that they are actually invariant, because when we add the symmetries on that new variable, okay, we get 0. Okay, now using the invariance, now we are able to reduce the order of the equation. We went from 4k to order 4, okay? And because we don't want to deal with lane and all of that, we decided to take the exponents of the invariance, okay? So that we don't have to use lane, throughout, okay? So we take exponent of the invariant, and it happened that Rn is also invariant, okay? An invariant of the equation. So using this, now equation 33, of course, looking at the original equation, okay, with experience, one might be able to guess, okay, this change of variable, okay? So this is what we are trying to show here, that, with symmetry, we don't really need to guess the change of variable. The symmetry can lead us to that change of variable that we want. Okay. Now from here, it's just, from here, we are using the invariant now and do the iterations and see how the solutions will look like. Okay, so we iterate so many times, and we saw that the original equation can be written in the form 36. We can iterate 36 to get equation 37. And of course, J has to be from 0 to 3. Okay, and we use the same relation to get a different form, okay, of the equation. Okay, and we again iterate to get something like this, of this form. Now all we need here is to replace this Rj, okay, by the expression given in R, okay, given in equation 37. Okay, so we know what R4n plus something looks like. As long as this something is less than 4, we know how to write it. Now here we have R4k plus I, but this formula says that that thing we're adding has to be from 0 to 3. Okay, it must not be more than this 4. But when we iterated these things, the I, of course, it goes from 0 to 4k minus 1. Okay, it's not just up to 3. So we need to find a way to write this so that what we are adding is one of these, so that we can use this formula. We cannot use this formula if j is more than 4. So we need to find a way to change this relation of 37 into something where what we are adding, okay, is just from 0 to 3. So to do that, we decided to write, to introduce the floor function. Okay, so if we divide by 4, so like I said there, the tau of R is just the remainder. So when we are dividing any number by 4, we are sure that the remainder at least, won't go up to 4. So it will be 0, 1, 2, 3, so that we can use that iteration, that formula that we obtained earlier. So that's what we did here. So we are sure that what we are adding here, okay, is 0, 1, 2, or 3. Okay, so from there, we can just use the iteration to get the solutions. Okay, so again, we were able to write the solution. Okay, that solution is given by equation 41. Okay, and using the floor function, okay, using the floor function, yeah, we are able to write the general solution in terms of the initial conditions. Okay, now the solution, the analytical solution of the equation that we shifted, of course, is given by 42. Now the next equation that I wrote there, remember that I said I picked the equation from a paper, So I shifted, okay, the equation to get the solution. So to go back to, the original equation, we have to shift shift it back again. Okay, the number of exactly the number of times we shifted forward. So we have to shift it back again so that we can get the solution of the equations, the one that was not shifted. So it's given by 43. Okay, now from here, we are just looking at the cases where the sequences AN and BN are constant and things like that, okay? So if AN and BN, the coefficients, okay, in the original equations are constant, we can simplify the formula that we obtained further and get this equation given in 44 and 45. Okay, now this part we just set A and B to be 1 just to see if we can get the results that those authors obtained using, I think they use, I don't know the method that they used to get the solution. They presented the solution and they showed that their solution were correct. So I'm trying to see if using this method, if I can replace the A and B by 1 and simplify, I should be able to get the solutions obtained in that paper. So this is basically special cases, okay, of the solutions, okay, and we did that, and we were able to show that, okay, using this symmetry and invariance, we can get exactly the solutions that those guys obtain for plus or minus 1, okay. So again, these are just computations that I think I can just skip, okay. Okay, yeah, let me get, yes, okay. This one I can just 2 minutes, yes. Okay, this is just but special cases, like I said, I can skip this and maybe say something about stability and periodicity. Okay. Okay, now the good thing with this form of solutions, okay, we can easily use the general form of solution to look at the periodicity, okay, of these solutions, okay? So now using our solutions, we can try to get the condition that will allow us to get the periodic solution. So we found that under this condition here, okay, we found that the solution has to be Fourier periodic, okay? The proof, because of time, I'm not going through the proof. And we plot the solutions and we've seen that, okay, the theory, okay, the graph and the theory, okay, the match, which is what we are showing using this graph. Because of time, I'm skipping this. Okay, again, we've noticed that when A is 1, okay, using the definitions of those stability, we saw that the zero equilibrium point is non-hyperbolic. Okay, these are just based on the roots, like I said, of the characteristic equation around the equilibrium point. Okay. these are just application of the proof. I can skip it because of time. Okay. And again, we look at the asymptotic behavior, and we saw that some of the equilibrium are globally, okay, asymptotically stable. Okay, so the proof again, because of time, I will skip. And yes, and this we also show that the non-zero solutions, they are non-zero equilibrium points, okay, are unstable, and this just application of we just apply the definition that are already known to get that the sum of the points are unstable and stable and things like that. Okay, so yeah, this is almost the end. So this is just the proof of that theorem. Okay, this is just the conclusion. Just like I said, we use symmetry to get the solutions, and we use the solutions to show that for some particular values of A and B, we can get the solutions in the paper that we are looking at, and we were able to get the solution using our solution that we derive using symmetries. Okay, yeah, so because of that, yeah, okay, thank you.
Thank you so much for that presentation. So I don't know if there are any questions, but maybe just one from my side.
Yes.
What does this system represent in terms of, is there some physical interpretation of the problem?
No, yeah, I know the equation. Like, let me just go to. Okay. So, like I said, the equation that we are studying here is coming from the Beaverton holes. It has, you know, some applications. I don't know much about. They were talking about growth rates, how, you know, species are multiplying, things like that. I don't know much about the application, the physical meaning, but we just focus on how to use symmetries to get solutions. Yes, okay. But the application, the meaning, okay, the physical meaning of the solutions. Yeah, okay. I know when we submit papers, I get questions like that from reviewers that I always struggle to answer. Yeah. Okay, the application, yeah.
No, it's fine, because I think with my colleagues, so they do a lot of ecological modeling, looking at populations and how they interact. So I don't know, do you want to ask anything, or you want to speak later? Yes, there's a question here. Thank you.
My question is about the following, that you found generator.
Yes.
After that, did you find group of transformations?
Yes.
And after that, did you check that equation is changed to the same equation?
The equation is changed to something simpler.
You checked it, right?
Yes, something simpler. Okay. Yes, I check. Yes.
There was a hand behind.
Sometimes you write the closed form solution. Why it is called closed form solutions?
Sorry.
You have find the invariant group invariant solutions, and you have write the closed form solution. Why it is called closed form solution?
The closed form solution is when we are solving difference equation, what we are interested in is closed form solution. The closed form solution that we wrote here is just the solution written in terms of initial conditions, basically. That's what we are calling by, we are denoting by closed form solution. So closed form, okay, I can, okay, to explain better, the closed form solution that I'm referring to here is just the analytical solution, written in terms of the initial condition. That close has nothing to do with a group or nothing. The condition.
Are there any conditions why it's called a closed form solution? I think that's
no,
what
I think with difference equation, if you are able to write the solution in terms of initial conditions, that's they call it. It's not, they call it closed form solution. That's the name given to difference equations written in terms of initial conditions.
No, I just give answer.
Yeah.
If you are finding that
just so yeah. Okay. So just take the comment.
Convert it to the infinitesimal generator into the vector form. So the vector forms form the Lie brackets is a commuter table. So commuter tables is under the operation is closed. So that is why we called it as a closed form solution.
Okay. No, but I think, okay, the way I see it, the closed form solution that we are talking about here has nothing to do with the group. Okay, the group. Yes.
Okay.
Yeah. Okay.
So
yes.
can I suggest?
Okay.
Yeah, we pass. Okay.
Yeah.
Thank you. So we
Okay,
can have
cool.
a discussion later
Okay,
anyway
cool,
as well.
okay.
Okay, so thank you so much. Can you give him a hand, please? Thank you very much for the talk.
Cool.
Now we have the next talk, and this is a plenary session. I saw some people were dozing. So do you want to stretch for a second? You can stand and sit down. They do that in Parliament usually to make people awake because this is a plenary and we're approaching lunch. It's day one. I think tomorrow will be stronger. So the talk is on the method of differential constraints, and Professor Meleshko is going to present on that.
It's really very similar. Yeah, so I think you have yeah, thank you.
Okay, that's a new one. Okay, it was upside down. Yes, it was constrained. Thanks, Zurab, for illustrating how you can constrain the presentation. So yeah, so Professor Meleshko is going to talk about the method of differential constraints. So I know that I want to thank you for coming because I know it was a long way, but I'm glad that you enjoyed going through Ethiopia. Yeah. From the okay. Okay. Yeah, we can talk about that at lunchtime. But just to say that, yeah, so thank you for joining. So with Professor Meleshko and I think from DUT and everywhere else, I can't even remember the last time when we met. It was several years ago anyway. So we've done quite a bit of things together. But also to say that I know that he had asked me to also advertise his conference before the conference we are co-hosting again next year. It's competing with us. So we need to just,
I think you're the culprit.
yeah, double dip. Yeah. It's a bit, so, but anyway, so it's the conference is taking place in January 2022 to 2025. And it is on advances in applications of analytical methods for solving differential equations. And there is a special issue and is going to show, yeah. And he is a student, usually the conferences we are done in celebration of Professor Ovsyannikov, who lived from 1919 to 2014 towards the contributions to group theory. So welcome, and we look forward to your talk. Thank you.
Okay, thank you very much for presentation.
When I get it, I'll send it.
Sorry, you need.
Oh, this
That,
So, yeah.
yeah, you stick somewhere first before you start.
Okay, no. Okay, I will put it here. Okay, thank you. My presentation will be not in symmetry analysis, but it is related with symmetry. So the presentation is called On the Method of Differential Constraints. This method actually was developed also a long time, and I will show some history about this. And this method was devoted, actually, this presentation is devoted to my advisor, Professor Yanenko, academician Yanenko, and method was developed in competition with Professor Ovsyannikov, which is related with symmetry. Actually, it will be my outline is method for constructing exact solutions a little bit, and then definitions of method of differential constraints. Actually, very important point, it is theory of compatibility. I will give just a little bit about this one, and then some examples of applications of mass differential constraints, simple waves, generalized simple waves, and 1D gas dynamic equations, and 2-dimensional gas dynamic equations, and so and also magnetic gas dynamic. It will be related on my research. So this is not, I won't talk about other publications. For example, this is my friend from Italy. He is working on this, Natalina Manganaro. So, but I will talk only about my results and so as examples. So this is over there. It's a little bit the delay. So this is example shows that, for example, if you have a very simple equation and wave equation, the wave equation, and it's possible to separate on two equations. And so then we know general solution of this equation and Adamar solution. So then assumptions that, for example, if you use group analysis, then we have scaling and, for example, another one it is scaling and shifting, and then representation of solution after substitution, you will get overdetermined system of equations. Actually, if you use group analysis and if you construct invariant solutions, it's not necessary to study compatibility if system is not overdetermined, of course. Then next, it is represented that most of degenerate hadograph. Hadograph, it means that we consider dependence of dependent variables, or some dependent. In particular, for example, this is V is a function of U. After substitution in equations, we have to do analysis of compatibility. And finally, for example, we will get one of waves. And in method of differential constraints, it was next step that it is considered not such kind of differential constraint. For example, we can include derivatives. And after that, if you consider compatibility, actually, in particular case of compatibility, we ask about involution. So if system is in involution, then we will get the same. So this system of one equation, and it will give something similar like this one solution. So, and here very important that here, if you construct invariant solution, you will get a solution only with constant arbitrariness. But if you use differential constraint, or this is constraint, so you will get solution where we have arbitrary functions. So, and as I told that this method was invented by my advisor, so it is in 1960s. So, and method consists of the following: we have system of equations, original system of equations, and we add additional differential constraints. So here X independent, set of independent variables, U set of dependent variables, and P are set of derivatives. So then of course we need to do some conditions for these differential constraints. So even they can be arbitrary, but any method in this case can be, any method in this case can be described by this, for example, invariant solution. So this is, you have particular class of differential constraints. So, but if you have no any conditions except compatibility, so then any method can be described by such kind of differential constraints. We need something additional, something additional. Very strong condition, it is called involution. So this means that system is does not produce new equations. Later I will show a little bit more. And this method was, as I told, was developed in competition of two great Russian mathematicians, Russian and Soviet mathematicians. So it is Lev Vasilievich Ovsyannikov and Nikolai Nikolaevich Yanenko. I was lucky because I was my advisor Yanenko, but I worked before going to Thailand. I worked with Professor Ovsyannikov on some analysis of gas dynamic equations. So it is called submodels. And you can see that their first publications, it was almost at the same time. So Ovsyannikov, he started applying group analysis to gas dynamic equations and to mechanical problems. And Yanenko, he used method of traveling waves, actually solutions with degenerate Hadograph. He applied to gas dynamic equations. And in this time, Yanenko, he asked Ovsyannikov, can you get my solutions? So for example, solutions which can be described by degenerate Hadograph. Then Ovsyannikov, he started thinking in order to, because they competed in everything, even football and chess, so fast chess, everything. And then Ovsyannikov, he invented so-called partially invariant solutions. So after that, he asked Yanenko, what about my solutions? You cannot get it. And then he invented method of differential constraints. So it was competition. And during this time, so the students and postgraduate students, they were giving seminar. In one of them, he asked, what about my solution? Is it possible? And another one also asked, what about mine? So, but solution is solution, it doesn't matter. So which method did you use? Later, I will show that it is not so simple to do it. So.
Were they both the same institute?
No, they are different. So this is Institute of Hydrodynamics. He was director of Institute of Hydrodynamics long time before he stopped being administrator. And Yanenko, he was Institute of Theoretical Applied Mechanics. And these two institutes were very, very close. And before, when I think that after Second World War, they work in similar areas. So and then they knew of each other before going to academic town. So I want to say a little bit words about academic town. In Novosibirsk, it was developed far from Moscow, 4,000 kilometers. And it was special academic town because many research institutes around small university and no permanent staff. So professors, they go from institute, research institute, they come, give lecture and go back to do research. So, and they were organizers of this university, and so they came in Novosibirsk. So Novosibirsk, if you translate, literally said, is New Siberia. So, yeah, New Siberia.
Where you don't feel so cold.
Skolkovo, you mean? Skolkovo. No, they did not work together. So, but my advisor, he told, go to his seminar. So I must be there. So
As a spy.
no, this is spy.
Oh.
Actually, as I told that after Yanenko, so I worked with Professor Ovsyannikov. He invited me to do. It is called submodels or submodels of gas dynamic equations. It is Lie group admitted by gas dynamic equations. It is and classifications of this Lie group and constructing all invariant solutions. So it is called submodels. So it is presented in 1994. So one more time, this is I will talk about. So this is we have differential equations and added additional differential constraints. And so the main tool for analysis of them, it is compatibility analysis. Mostly it is involutiveness of system. So this is very strong requirement. And as I told that many solutions you can describe by differential constraints. So this is unfortunately in Russian book, it is published method of differential constraints and its applications in gas dynamic equations. And so, and in English, I used some of these results they published. Actually, I was young at this time, and Yanenko, he told that in future, he will write something. So, and he cut me from authors. Because if it is 3 authors, then it will be on title. If it is 4 authors, it will be inside. So, and as I told, practically all methods, they can be constructed by this way. And about compatibility analysis, so this is, there are 2 approaches. One, it is Cartan's approach, and so another approach related with Riquier approach. So Cartan approach related with differential exterior differentials, so exterior differential forms. And actually, if you have partial differential equation, you have to reduce it to differential form. And this is not so simple too. So you need to spend time and to be sure that they are equivalent. So it is, of course, it is preferable to use recur method. And the idea of compatibility analysis can be seen on the following. You have, for example, partial differential equations with one dependent variable, so first order, then this is complete, and then you can get a Poisson bracket. Poisson bracket, it will be also the same form of equation, and the system is called complete system if any Poisson bracket is linearly dependent on equations of the original system. So this means that it doesn't produce new equations. The system is not active. And involutiveness of system, it is something similar. So, and it consists of two steps. So on the first step, it is considered the following space, which is related, this is with this function here. Derivatives can be up to any order. So then it is maximum order considered. So this is such kind of algebraic space. Then there is some Cartan Cartan numbers, and then using Cartan numbers, it is constructed some conditions, and then so this is algebraic part, and this is analysis part. So this means you have to differentiate this, prolong this system of equations according to conditions obtained in algebraic part, and then you have to require that in this case there are no new equations comparing with original system. So details you can see in some books, in particular Koranishi and Pomaré. So and actually I will omit this part because it is related with compatibility. Here I only want to mention that first computer symbolic manipulation for it was by Yanenko. Can you imagine 1961? What kind of computers were there? And of course, it was only like differentiate some form, very simple, and to get these conditions with them. So later, this method for Cartan analysis, it was used, and another one, it was for Riquier analysis. It was also we try to construct. It was not reduced, not maple. It was before this, so some special programming. And here I will give one example. For example, if you consider the following system of differential equations, here L is matrix, and it is non-singular matrix. And then if it is written in this form, then differential constraints can be written in this form. So where B1, it is so you will take a unit matrix, and so then you will take some rows from this matrix, and it will be matrix B1, and other, it will give us B2. So of course, this is determinant is not equal to 0. This is just to say that you will take from matrix L some rows. So, and then by this way, you will multiply these rows, and here another part, it will be moved to function psi. So, and then in particular case, it's possible to show that matrix A, not to show, this is matrix A can be written in this form where lambda, it is diagonal matrix. In particular case, when it is strong hyperbolic system, then this is eigenvalues, it will be arbitrary. And for this case, it is possible, actually, it's possible in general formulation, it's possible to write that this overdetermined system of equations is involutive. Involutive, it means it does not produce new equations. And if we have two parts, one part, this is related with algebraic properties, and another part, it is related that this system is not active. So, And finally, for example, in particular for strictly hyperbolic system, derivatives here not involved. So this means that differential constraints must be quasi-linear. So no derivatives in function psi. In particular, gas dynamic equations are of this form. So this is written about. And now I want to talk about some solutions which are called simple waves. So simple waves in gas dynamics are very well known, the Riemann waves, and they are constructed as the following. So this is dependent variables. All dependent variables depend on one function. And then after substitution in equation, it will be obtained some differential equations. And these differential equations, of course, have to be such that impossible to find this condition. So there exists some rho such that this is not equal to 0. Otherwise, it will be trivial case. So u it will be constant. So then it's possible to reduce, starting from this case, it's possible to reduce that differential constraints of they must be of the following form. So where function, where B1, it is number of rows, the same as number of columns and rows, so but -1. So then in this case, solution has arbitrariness. So it is one arbitrary function. This I wanted to show that simple wave, Riemann wave, can be written in the following as the following differential constraint. So then question is quite opposite. Is it possible to construct so is it possible to construct differential constraints of the following form? And then, yeah, it's possible to go back and to show that if you have such kind of differential constraints, then it will be all functions that will be dependent only one variable. So then this means that such kind of differential constraints gives you similar as a Riemann wave. But Riemann wave, I want to say that this differential constraint here is 0. So this means that homogeneous solution. So and in particular here, then because it was given conditions for existence of such kind, I call it generalized simple waves, when right side is not equal to 0. So then in particular, there's given conditions for such kind. And one of very important properties of these solutions that when you use group analysis, we try to reduce equations, for example, to ODE. And it's very good that if you could reduce it. So, and here the same. But in group analysis, when you reduce to ODE, you will have only constant arbitrariness. But if you consider such kind of solutions, it's possible to reduce to ordinary differential equations. So you can see that this is a long characteristic. And arbitrariness, you have functional arbitrariness. So one function of arbitrary variables. And so then, of course, next question, because in gas dynamics, this is very well known. So rarefaction waves. And it's possible to construct rarefaction waves. Conditions are then you will have this is conditions at one singular point, and so and you have rarefaction waves. This is conditions for given rarefaction wave. So characteristic not crossing. And this is particular case. This is particular case one-dimensional gas flows, and as I told that in this case it is a very well-known simple wave. Simple wave. It is here. U is velocity, rho is density, and P is pressure. So, and this is arbitrary function. Actually, here example is given for polytropic gas. When this function, it is gamma is polytropic exponent. In this case, matrices that I wrote before, they will have the following form. You can see that this is strictly hyperbolic system. Then Riemann wave is defined by the following differential constraints here, 0. So, and question is, what about, is it possible to find generalized simple waves? for generalized simple waves, we need to do that here. It will be not zero. So question is it possible to find such kind of solutions? Actually, here it is given theorem that it's possible. In particular, these right sides here, psi and phi, they are given by this formula. So, and then one more time, solution now it can be found along characteristics. So then it is this type of solutions are reduced to system of ordinary differential equations. And if you consider Riemann wave, so Riemann wave, its solution along characteristic are constants, but here not necessary. So this is condition. So this is reduction to ordinary differential equations, and then it's possible to construct reaffection waves. So then there is a solution of decay of arbitrary discontinuous. So then you need to construct PU diagram. So then in PU diagram for Gursa problem, you have the following conditions. This is conditions at one point. So then it means that it's possible to construct I forgot that in this case, Riemann waves, they are isentropic, entropy is constant, but if you consider such kind of solutions, they give non-isentropic solutions. Unfortunately, I don't know applications of this. So one time I asked a very good scientist in Russia who is working in this area and one of high class scientists, I asked him how to apply such kind of solutions. And he checked all calculations, he found misprints, but he asked me the same question. So where you can find the applications of such kind of solutions? So unfortunately, right now, I don't know. But very important that solution is reduced to ordinary differential equations. So this is one of particular problems when we can join two type of solutions. So this is reaffection wave, I mean the generalized simple wave, and this is generalized simple wave, and here this is shock wave, and it's possible to join two such kind of solutions through shock wave. And it looks like you have two pistons, so and two reaffection waves, they collide, and so after that what you will see. Also, generalized simple waves, it's possible to construct for two-dimensional stationary gas dynamic equations, and then it's possible to consider center wave like Prandtl-Meyer solutions. So that's and this is conditions at one point, so singular point and in corner if you consider Prandtl-Meyer solution. So, but unfortunately, such kind of solutions, so it is there is reduction from non-isentropic solutions to Prim-Munk transformation. It reduces. It's possible to reduce for special type of state equation. It's possible to reduce non-stationary solution to stationary solution. To non-isotropic solution. It's possible to reduce to isentropic solution. So this kind of solutions are reduced by Prim-Munk transformation to Prandtl-Meyer solutions, unfortunately. So, but it's not. It is difficult to start from Prandtl-Meyer and to find such kind of solution. So in one way it's possible, another way it's not so simple. I don't know solution. So then we applied such kind of solutions also for Riemann waves. So this is system of equations written in Riemann waves. Before we studied case when with Natalia Manganara, when this is non-homogeneous part, but the question was, what happens if you have even homogeneous part? Homogeneous system of equations, and is it possible? I use it. It's not for me, it's for you. Okay, thank you. So then it was non-homogeneous party. We tried to consider such kind of solution because we have a big arbitrariness. So then we can manipulate this arbitrariness. For example, like Stefan had told before, that the more arbitrariness, the better, because you can choose after that. So some case that you can manage. So here, but then I decided that, oh, okay, let's do even simpler. So then this one, when it is homogeneous, for this case, it is of course, we know Riemann waves, they are the following. One of these constant. So either R or S is constant. Then you have one Riemann wave or another Riemann wave. So then question is about, we have, for example, these differential constraints, and we require that this system differential constraint together with this original system, it is involutive, and involution gives us the following conditions for function P. So then in this case, it's possible to construct even if you have differential constraints, so it's possible to find solution any Cauchy problem. So because if you have Cauchy initial conditions, then these initial conditions will allow you to construct this function P, because of conditions for function P are the following. So this is several cases of such kind of solutions. So unfortunately, of course, in this case, it is not general case for these functions lambda and mu. They have to satisfy some particular conditions. So and these conditions are written here. So here are several examples. I want, as I told, that if you have initial data, so then this initial data you can invert, and so then you will find, instead of I, you will find C, and then function H, which are involved in this solution for initial conditions. So it will be found from initial conditions, and then it's possible to show that solution must satisfy this differential constraint. Of course, the most important, that differential constraint must be involutive. So this is one of conditions. Then another example was for one-dimensional. This is example for one-dimensional isentropic gas flows. It is isentropic because when you consider Riemann invariant, so then Riemann invariance, it's possible to introduce for gas dynamic equations when solution is isentropic. This is one-dimensional case. So this is given particular cases of sound speed. So if the sound speed has this wave, one of them, so in this case, we have differential constraints. So, and these differential constraints allow us to construct solutions. This is another example for non-linear elastic material. So here we have epsilon is deformation and sigma it is stress. So this is relations for example, if function phi is linear, so then we have Hooke law, but if it is nonlinear, so then this is it can be described as a elastic material, nonlinear elastic material. So then here also given conditions for this function phi, and this system of equations is strictly hyperbolic. It's possible to rewrite it as in Riemann invariants. So then Riemann invariants are given here. So, and then some conditions for system to be involutive with differential constraints, so generalized simple wave. And this is conditions when function phi has the following form. Actually, it is not general, but you know that because this theory is local, then you have some conditions at one point, relation between sigma and epsilon, between deformation and stress. Then it's possible to approximate by using some constant. It's possible to approximate real experiments. So then this is particular cases of solution. And so this is particular cases of Riemann waves and in different spaces. So for example, this is velocity. And it is taking some particular conditions for initial data. So for example, entropy, oh, sorry, not entropy, deformation is constant. So then it's possible to construct such kind of solutions using, wait. Oh, I'm sorry. Okay. Ah, you have to share the Zoom. Okay. So different types of relations, and this is I talked about. It's possible to consider relations between deformation and sigma. So, and it's possible to, if you have some, for example, at some point, it's possible to approximate by using constants which are involved in solution. So this is another example. For example, we have publications with our friend. So this is Gary Webb, who, and Professor Shibushi Samoya. So we had for magneto-gas dynamic equations, when we have this is equations for conservation law of mass, conservation of momentum. So this is energy equation and some relations for magnetic field. So, and here, of course, it is considered, not of course, it is considered case when electrical conductivity is infinite. So in this case, it's possible to construct such kind of solutions. And in one-dimensional case, this system of equations is split. So over there it is changed, but here not changed. Okay. So it is split in two parts. Here B1, it is if you consider one-dimensional case, B1 becomes constant. So because of Faraday law, and so it must be constant. And in particular, we can consider different cases when B1 is 0. If it is 0, then it is considered such kind of system. This part is can be solved later after when we find magnetic field, and so then and velocity, you can find solution for for other cases. So then here it is considered case when B1 is 0. In this case, matrix A has the following form. So this is L lambda. It is diagonal. So this is we have two sound characteristics and three contact characteristics. So and it's possible to do this analysis. So particular cases, I will skip them. And so then in this case, differential constraints, because system is almost strictly hyperbolic. Unfortunately, we have three contact characteristics, but if you consider differential constraints related with to such one characteristic, because overdetermined system also has characteristics. So characteristic, it is meaning that along this curve, derivatives can be discontinuous. So then normal derivatives can be discontinuous, and tangent characteristics are tangent derivatives are continuous, but normal derivatives can be discontinuous, and this gives us characteristics. And then if you consider overdetermined systems, this is the same condition for characteristics. And if you consider generalized simple waves, then in this case, we will have that only one characteristic. And along this characteristic, we can solve this system of equations. So this is ordinary differential equations, which reduce this solution to ODE. So, and here, if you consider that it will be characteristic of system, it will be sound characteristic. So here related with alpha. Alpha here it is used alpha because we have wave moving left and moving right. So then it is possible to write at the same time. So if it will be plus square root, so it will be one characteristic and another one. So this is possible to reduce to the following system of ordinary differential equations along one of sound characteristics. So it is plus or minus, it depends on what kind of characteristics. So this is ordinary differential equations after reduction. If you have if there are some generalized simple waves, so question is it possible to find them? Actually, yeah. So this is for magneto-gas dynamic equations, like for gas dynamic equations, it's possible to find them. So, and here it is given. I won't talk more details because it was done long time ago. It can read in papers. So then here just examples that it's possible to find and what equations are for you need to solve. So then even particular solutions for such kind of function. This is differential constraint. It means that right side of differential constraint. So given are particular cases for functions that it's necessary to solve, and then it's possible to consider when phi1 is 0, phi1 is not 0, some particular cases of this it's possible to find. So then here it is examples, different examples of such kind. So, and in particular, we can see that for particular case, it's possible to construct, if phi3 is equal to 0, it will be entropy is constant, but it does not give simple wave for magneto-gas dynamic equations. For magneto-gas dynamic equations, right side must be 0. But here it is not 0. It is interesting that this part not related with magnetic field. It is like in simple wave. But here, this is combinations of B2 and B3. This is two, they are related with magnetic field. They interfere something, and then it is not Riemann wave. So for Riemann wave, it will be 0 here. So and then I want to say about further studies. And further studies that are related with, of course, applications of higher order. So there are some examples, but not so many. And I wanted to attract attention for audience that this method is still developing. Even it was invented so long time ago, but not so many applications. So it's necessary to have students who can do a lot of calculations. And so this is for higher order and applications for more than 2 independent variables. So, and it's possible to consider development. So it was some opinions that this method is no structure like in group analysis. It's not true, because here there is a method. So you take differential constraint, requires that this system is involutive. So involution gives you immediately very strong conditions. So then you, in group analysis, you have to consider subalgebra, algebra. So then here also you can consider 1 differential constraint, 2 differential constraints, for example, for gas dynamics. So 3 differential constraints, and you will have more arbitrariness. So, and more arbitrariness gives more variety for initial conditions in this case. So, and here I talk mostly about 1 independent variable, but also important that there are some applications for more than 2 independent variables. So then, sorry, I told 1, so 2 independent variables. 1 independent variable is ODE. So then this is for partial differential equations. And for example, one of them, it is interesting that for gas dynamic equations, for example, for isentropic case, 2-dimensional, then it is vertex depends on for example, on temperature. So it is interesting and very simple conditions. So this is like you have a rotational flow, and this is rotational flow, but it is described by special type of differential constraint. So one differential constraint. And so, of course, it is necessary to consider further development of the method. Here, this is some references. I cannot hear, I'm too young.
You have to use the.
As we go about dimension, also in space or space on time
Yes,
already.
there are some applications, but not too many. So then, as I told, I know about one for gas dynamic equations, and it's poisentropic case that I did one differential constraint. So that is, I got that vertex depends on, for two-dimensional case, vertex depends on, for example, on temperature. So, but particular case, it is exponential. So I think that there are many other cases. So this is necessary to have students who can do many calculations, and you don't. This is why I wanted to attract attention for this method, and particular, this is references that I talked about. So I didn't finish yet. So, and then I wanted to give about the conference that we will have in 2024. This conference will be, so this is about Ovsyannikov 105 years anniversary. So then we organize this conference that will be related with Professor Ovsyannikov. So I invite everybody to participate in this conference. Conference is called Symmetry 224. Thank you very much.
Very much. Thank you very much. I just want to check. So do we have any questions? Yes. Yes.
No, it was clear.
Thank you. I just wanted to check whether there's a possibility to develop this method to differential equation that that have randomness. Yes.
No,
Maybe in case we'll talk more about it.
For stochastic equations, I don't know such kind of applications. Why? Because stochastic differential equations, in reality, they are not differential equations. In reality, they are integral equations with special type of integral, for example, eta. So then question is for such kind of equations, how to consider composition, derivative of composition of functions. So group analysis is developed for this. So for example, Faisal Mahomet, so he used this, and some other guys now started. And Sembi, she will give, Sembi Mackenzie, she will give a presentation about this. So then for stochastic equations, I don't know. So.
Thank you very much.
So two questions. So I want to channel Ovsyannikov. So he would ask, do the Riemann invariants, the Riemann simple waves, have a symmetry interpretation?
Oh, yeah. So this is like Riemann waves. They can be considered as partially invariant solutions.
Mm-hmm.
So partially invariant solutions, actually, when you consider partially invariant solutions, one of very important question is compatibility. So then what was competition? Because Yanenko, he was geometer. His PhD and his next degree, it was in geometry. Then he could guess so what to use. So, and then he used this. I think that he listened lectures of Finnikov when he was in university. So, about exterior differential forms, and so and also compatibility and involution. So and then from group analysis, Riemann wave, it is partially invariant solution. So, but from method of differential constraints, it is special type of differential constraint when number for one-dimensional case. For two-dimensional or three-dimensional, this is simple waves. They can be described by another way. So too complicated differential constraints. So I have it in my book. So if you, okay.
Thank you. Second question. So in general, the differential constraint, can it be viewed as a non-classical solution?
This, you know, that this is the same question as Ovsyannikov and Yanenko they had. So if you got some solutions, it's a solution. So, and I started talking about this. So because Ovsyannikov, he asked, what about solutions that you could describe by method of differential constraints, for example, generalized simple wave? It's possible to construct, to give answer. What happened for stationary solutions? So then what I did, I prolonged space. And in prolonged space, I found what kind of group I have to consider. It was partially invariant solution, but in prolonged space, and it was several steps. So, but if you consider method of differential involution, so, and if you consider partial invariant solutions, you need to study compatibility. Why not from beginning study, use compatibility, and you can get something. So thank you for question.
So just a final comment. So I guess Ovsyannikov would say, but you can't handle systems with dispersion, whereas Lie symmetry can.
You mean for stochastic equation?
No, just with the dispersion like KdV.
It's possible. There are some examples for
Yeah.
KdV also, so it's possible.
But all your examples, there was no dispersion.
I don't know. So I don't know. I think that my friend from Oleg Kaptsov, he and Tishukov, they did some applications for KdV. So, but they considered, so I got used to initial data, but they considered differential constraints a little bit in different form and long time ago. So yeah, it was some applications. We need students who can do it.
Okay, there's an appeal for students and researchers and people to do it. So any other questions from the floor? Okay, so you were right, it was very clear, except for the questions. So.
Oh, this is a joke. So I want to say that we had one visitor from Louisiana, and he gave talk. And in this talk, he told, after talk, he asked students, do you have questions? So it was silence. He told, okay, this means that you understood. If you understood, this means that my lecture was very clear, very good. I feel very good. So, but if you don't understood, so did not understood, understand, this means that also it's very good because I can continue my job.
It was, yeah.
I hope it was clear.
No, not good outcomes both ways. But okay, so let's just give him a clap again. Thank you so much. Just some announcements. So we've already got some names of volunteers for chairing. That's one. And then two, there is lunch. And then the lunch, where are the people who are helping us? They seem to disappear. Yes. Yes, people, come tell us lunch.
Lunch is by.
Oh, no, the people online don't need to.
Oh,
know.
yeah. Lunch is by reception.
Okay, so make sure that you are back here. We are starting at exactly 2 o'clock. It's a very interesting session, which we have in the afternoon. So thank you to the speakers who have done the first sessions. And then the chairperson for that session is, has it disappeared as well? Oh, yeah, Dr. Robert Bogari, and he's going to, the people need to talk in the next session. Before you go to lunch, make sure your talk is there. and then you can go and have lunch, and make sure you're here 5 minutes before. Thank you very much. Just one thing I want to know, is this room going to be locked, or do we carry our laptops? No, but then you can have lunch. Are you sure? Ideally, if you have a laptop, there are no guarantees. You can carry your laptop, okay? Yeah, so, but Sibu will be here if you want to leave your stuff, some of your stuff, but yeah, okay. All right, let's go then. Thank you very much. I wanted to ask you, are you able to do this session for us tomorrow, to be the chair for this session with Evan Nelson and Away? Okay, there is some information that yeah, is that okay? Thank you so much. But I don't understand, Sibu, can't you get a log? Can't you get a log? Thank you.
copied, so I could take
Okay.
it out. You probably have to do full screen before.
Yeah.
Or- So there'll be a bit of introductions before.
Okay.
we begin.
Perfect. And then also if you go
So we'll have a long series of introductions. So you can hand over to me, and then I'll hand over to Karen, and Karen then will announce. And you can just say that this is the Unitex session, and then you can hand over to me. I'll take the other. Yeah, you should read that. You can read that if you want. Yeah, sure. All good on your side.
All good. It's ready to go. 6 people online at the moment.
We'll arrange it.
My name is like a German name almost.
Yeah, exactly. But South Africans normally can't pronounce it at all. Yeah, they try to pronounce every letter.
Want to make sure that the screen gets recorded full.
And the people on Zoom, will they only see this?
They see this, they also see you.
They also see me.
Through that camera.
Okay.
Um,
But I think on the recording, it will mostly be this. There are not many, not too many online participants either. Okay. You don't have to worry about.
Yes.
How do I? Right, so I need to.
Maybe it's good. I don't know. It's not my computer.
No problem.
I just want to put another file.
Maybe we can do it later. if that's already-
Oh, okay.
Yeah, this is a lot of people here. This is wonderful. So many people. Yes.
And please use this. And then
That's great. Did you put it?
Okay, welcome back. Everyone can settle down for the afternoon session. Okay, so it's just on 2 o'clock now. So we now have the NETEC session. And this session is dedicated to a discussion about development of research skills in undergraduate students, organized by the Future Mathematicians Program, a mathematics engagement project of the Mathematical Structures and Modeling Research Program at NETEX. Professor Zurab Yanelidze is based at Stellenbosch University in the Department of Mathematical Sciences. He is a principal investigator in the Mathematical Structures and Modeling Research Program and serves as the president of the South African Mathematical Society. We also have Professor Nancy Ann Neudawa, and she is based at the Pacific University, Oregon, United States of America. She is a co-director of the Center of Undergraduate Research in Mathematics and Undergraduate Mathematical Sciences Research Skills Development Program, founded by a grant from the National Science Foundation. Professor Neudawa holds an extraordinary appointment in the Department of Mathematical Sciences of Stellenbosch University. And I shall now hand over to Prof. Zurab.
Thank you very much. I'm going to tell you about the Mathematical Structures and Modeling Research Program at NETEX later, after this hour. So that will be at 3 o'clock. Now, I would like to invite Professor Howell to introduce our very, very special guest who will tell you about undergraduate research.
Super, thank you, Zura. So it's my great pleasure to introduce Nancy, Professor Neudawa, who is visiting us at the moment. She's a research visitor, but she's also recently been appointed as an extraordinary professor in our division and department. She has several collaborative projects going. We met in 2018 at a workshop in discrete mathematics that she organized at the African Institute of Mathematical Sciences. And I gave a talk, and at the end of it, I said, I have always been interested in matroids, and if anyone is interested in exploring this problem with me, let's talk. And Nancy was the person who was working in matroids, so our paths crossed, and it's been a fabulous collaboration. We have been collaborating on women in mathematics initiatives, and we organized in 2019 the first African Women in Maths conference, which was hosted at Stellenbosch University, and subsequently now has been morphed into the establishment of the Women in Mathematics division under SAMS, which is something that we're very proud of. Nancy and I have also co-authored a number of articles about female mathematicians, but also about building community in mathematics. So it's my great pleasure to introduce her to you. And she's spoken about her initiatives in undergraduate research before, and I really enjoyed hearing about it. And I know it's something that Zurab with the South African Mathematical Society, Professor Jan Litzer, sorry, is very passionate about. So we're very grateful to have Nancy here to share expertise. Good. Hand over to you. Okay.
Thank you, Karen. And thank you, Zurab, for the invitation to come and talk to this group as part of NITEX. I'm really pleased to be here. I'm pleased to be back in Stellenbosch and back in South Africa, and some really wonderful opportunities here. So Karen didn't say much about the research that we're doing together. We're also doing mathematical research together in addition to trying to build this community of women mathematicians. And I hope you get a chance to learn about that sometime. But today, I've been asked to talk about a model of undergraduate research in mathematics, and this is just one of many models in the United States. I will say that when I finished my PhD, undergraduate research in mathematics was not very common. It had become somewhat common in chemistry, biology, maybe put students in a lab or take them into a field, but there was a strong feeling that undergraduates weren't ready to do research in mathematics. And so just in the time since I finished my PhD, there's been a huge shift in this in the US nationwide. And part of that is due to this Center for Undergraduate Research in Mathematics, which I'll tell you about this model in particular. So we have several models that are common now, and one is to have a thesis or a capstone in the final year of your undergraduate studies. And for us, that's in the fourth year. I think here, maybe that would be the third year, and I know that you have a fourth year honors. And these often consist of some sort of literature review or summary of an article or students learning new topics, but doing this all independently. We also have summer research programs. These are called often REU, or Research Experience for Undergraduates. And these tend to be groups tackling accessible problem 8 to 10 weeks. So for the entire summer, they go to another university. So they don't stay at their own university. The idea is students from across the country come together from all different universities, work with a professor they haven't met before for this intensive summer program. And this works great for the lab sciences, but if you've ever tried to work all day on mathematics, after a while, maybe you need a break, and, you can sit in a lab and titrate for 8 hours, but I can't think about mathematics for 8 hours. So the third model is what I want to talk about more, which is academic year research. And in this case, if we spread the research over an entire academic year, we have more time between meetings. We can work on a more abstract problem maybe, and these still can be collaborative group projects. So the Center for Research in Undergraduate Mathematics, well, first of all, I'll say it's funded by the National Science Foundation, and it's been funded by 4 or 5 year grants. And sometimes we have extra money, so it goes into a 6-year. So we just last month got our 4th grant, $1.6 million for the next 5 years. And these were the PIs, the principal investigators, for the last 5-year period. The goal is to promote undergraduate research in mathematics. Sorry, there's a delay in the.
Sorry, Nancy, there is indeed a short delay because it's going.
I see, yeah. And these are the PIs for the new grant. And including me, I didn't put my own picture there because you can see me here. And so, like I said, it's to promote undergraduate research in mathematics. How? Well, one way is training professors as mentors for undergraduate research projects. Just try to get we have an arrow on there too. And providing funds to professors to establish undergraduate research student groups at their own institutions during the academic year. A few things I want to point out here. One is that you might notice that the middle three principal investigators on the grants all have Hispanic names. And so we do reach a lot of minority communities through this grant, or minoritized communities of mathematics, I should say. And you also notice that Catherine is from a community college, so a two-year college, as is Mercedes. And so we have some of the PIs on this grant are from two-year colleges. And then the rest of us, even though this says college, we use the word college equivalent with university in the US. So Occidental College is a highly selective, prestigious four-year liberal arts college. And so, but we do have two people from two-year colleges, and you'll see why in a minute. So in addition to this, we also work on advising professors how to organize and continue to operate undergraduate research projects. So how to keep it going, and then how to prepare undergraduate students to succeed in graduate studies in mathematics. So this is the undergraduate research model we have. We want students working on journal quality open problems that are accessible to undergraduates. So this isn't a situation that students are just reading an existing paper and presenting it, or learning some mathematics that's new to them. Maybe they didn't have a course in it, but actually working on journal quality problems. And they work collaboratively in groups for an entire year. We, throughout that year, try to teach them how to read mathematics, write mathematics, and present mathematics. We'd like them to start early. So we don't really want them to start in their final year of undergraduate, but earlier, so that they can work on this over the course of maybe more than 1 year, and then possibly become mentors to younger students. Like I said, in the US, it's becoming more common, and it's required by many programs. My university requires every undergraduate to do some sort of senior project or last year project in order to graduate. It's become expected for graduate school admission. And one thing we found through this program is it really helps students from underrepresented groups see early that graduate school is a possibility. So if you come from a family where your parents didn't go to university and things like this, you might not even come into university thinking about going beyond that. You might think of it as preparing you for a job. And so this is what the grant does. So we have this massive grant. We have $1.6 million for the next 5 years. And we provide mini grants to faculty, so lecturers and professors, and we use the words interchangeably also in the US, who apply for these. And so what we support is pairs of research groups from 2 institutions in the same geographic region. So if I'm at a university, I must find someone at a 2-year college that I'm going to work with. And I will have a group of students, and they will have a group of students. Each research group has 3 to 5 undergraduate students and 1 faculty mentor. This is the sort of benefits you get from the grant. We used to give all students a $3,000 stipend. We've more recently found that students often need course credit for graduation. So now the default is course credit, but sometimes they get a stipend. We give $7,000 to the university And that is so that each faculty mentor does this research instead of teaching one of their courses. So they get one course release, it's typical. We give some additional funding for supplies. We bring all the lecturers and professors to a 3-day summer professional development workshop. And then at the end of the year, the academic year, the students and faculty mentor go to a conference to present the results. If you have any questions, you can ask at any time. I know it's harder for the Zoom members, but they might be chatting to each other in the background.
Sorry,
Yeah.
unless you say, you may ask or interrupt.
Yeah.
The point is, when they're presenting, is it usually original publishable work, or it could be any project that they've been working on?
So in order to get this grant, you have to propose 2 projects that you want students to work on. So you would apply to us for funding and you would have an idea of 2 different projects. And these would be projects that you think could lead to journal quality research. Is it always publishable? No. Sometimes you've made advancements that'll later be publishable, but yes, they're working on some sort of original work.
And the presentation need not be original.
The presentation will be what they have done. Yeah, yeah. And what they have done is working on something that the mentor thinks, you know.
May lead to something.
Well, what they do will be original, but the question is always, is it enough to publish? You know, maybe your next group of students the following year will continue it, and after 2 years, it'll be publishable, which is one reason to start the students young in their first or second year. So maybe they can work on it for a couple of years, and all that work they put into getting the background down, they continue with. So here's a little bit about, might answer one of your questions here. So like I said, it was founded in 2007. It's probably now supported about 450 students. I was trying to get the new number, but I don't have the exact data today, but this is, you know, as of a year ago. 50% female, 29% minority, 4% with disabilities, and 27% are first generation college students, which means their parents didn't go to university or college. Been mentored by over 110 professors, over 84 universities and colleges nationwide. And this number means that 21% of those were either Hispanic serving or historically Black colleges and universities. The current students have written over 168 research papers and given over 360 conference presentations. And then from the students who participate in this program, about 63% go to graduate school. Of our math majors nationwide, about 18% go to graduate school. When we look at our trends in undergraduate research, we can also look at our trends in undergraduate teaching. And these have been some of our big trends. We've moved a lot more towards inquiry-based learning. This is a modified version of what we used to call the Moore method, but leaving open the classroom to a lot of inquiry and students discovering, improving things. So sometimes we refer to this as discovery-based learning or active learning, or process-oriented guided inquiry learning. In other words, a lot of our teaching has moved to minimal lecture, and in the same way, we're trying to get our students actively doing research early. So this is a discussion question for all of you to think about. What kind of undergraduate research do you currently have here? And how could it be expanded or succeed here? And what obstacles or challenges do you think you have amongst your own departments or divisions or across universities? Yes.
Yeah, so I was trying to.
So I was trying to understand in terms of, so in this case, we are bringing the research component into the undergraduate levels. And I'm trying to look at the workload analysis possibly for the current staff members that we have in different departments. And also looking at the fact that at the moment, we also have some huge numbers in our honors program, in our master's and doctoral programs, where most of our researchers are involved in supervision. And I'm also trying to look at the numbers that we then have in our undergraduate programs, and where and how to fit this research in the undergraduate level. I'm not so sure, maybe in the US, maybe if you also could have shared with us the numbers in terms of the undergraduate levels, and maybe also the numbers in the postgraduate levels. And so here I'm trying to look at the feasibility in terms of how we can also try to implement these models in our teaching. Thank you.
Yeah, I mean, it is so our numbers vary quite a bit. I can say at my university, we all supervise undergraduate research in the final year of undergraduate. And there's no course credit or anything given for that. It's just an expectation, you just do this. Similarly, when I was a PhD student, my PhD supervisor had 10 PhD students at the same time, and he was the head of the department, and he didn't get any, I guess, workload release for having 10 PhD students. It would have been the same if he had one. So in that sense, some people just take on more students than others. But the idea of this grant, this mini grant, is that you don't have to do that. If you get one of these, your university gets money, so you teach one fewer course. So in the US, maybe we usually teach between 5 and 7 courses a year. Well, then maybe I would only teach 4 instead of 5. And so that's the staffing hope for this. And then beyond that, after you get one of these mini grants, the hope is that your university will institutionalize academic year undergraduate research and have a mechanism for this. I'm not sure that completely answers the question, but
I want to ask you, do you know about Soviet Union system? Because in my university, Novosibirsk State University, we had 4 years to study. It was subjects and so on, lectures and exams. But last year, 5. So 5th year, usually we had research. So after that, we had to defend thesis. It's like this system.
I think that corresponds to masters now.
Oh,
That's 5th year, yeah. Yeah.
Now this American system, we have bachelor, but Russia now going back to the same system as 5 years.
We have depends in Greece. In Greece, we have depends.
For the undergraduate students, we will defend our study, and it can be tough. But my question is, sorry, but really, your supervisor had 10 PhD students in a time? How was that possible?
That's a good question.
I know supervisors who maybe have less PhD students in their whole life, academic career, successfully, but then in a period, PhD students, I think this in the same time.
At the same time?
At the same time?
In some cases.
I mean, I would discourage it. No way that's a typical example.
no, it's not typical. No, that was my experience.
So mathematical department.
Yeah.
You're almost presenting it as if, okay, that's the one, it's not, it's far away from the land.
No, more common was probably to have 4 PhD students.
And that's far.
My PhD, where I did my PhD, we had 250 PhD students total in the university when I was there.
In fact, I would be encouraged not to sort of promote that, because I have Samira, there was Mensa, there were about 2-3 PhDs I had at the same time, right? In fact, so it confused me. It's like sometimes you come to my office and say, like, what are you here for? Like, you asked me to come here. It's difficult to now coordinate the things. So
I think if we have undergraduate research, then by the time students arrive to PhD level, they will be much more independent.
Hopefully.
And the supervisor will have to spend a bit less time, and then they can have more students.
So can I?
No, you can ask if you want to ask. Then I will.
Say about what this was going.
Yeah.
Going
Remember that.
across the world. Okay, so I think the question here for us would be, what define undergraduate? So let me. You probably know the structure of our program. We've got a BSc that is usually 3 years, if it's done in minimum time. And then we've got honors before the master's. The honors is single year where you do only one course, mathematics or physics or something. So it's an honors in math or honors in physics. Now, I think if you regard that program, including the honors, as undergraduate, which is becoming more and more common, then yes, we do have some research component in the undergraduate, including that honors program. Right. So there was a time when at honors you would do at least 10 courses. Most students would be doing like 12, 13, up to 14, and then they only write exams and they graduate with the honors. Now, of course, one has there's increased number of lectures per course, but the number of courses is just 7 usually. And then you do a research component. So now there is a research component in there, which counts an equivalent of 3 courses. Now, so every student have to do that. But the problem is exactly what was mentioned, the staffing regarding that. So by and large, you can do it at the graduate. I mean, Samira will actually tell this. Any person who is running the graduate program in the particular department would now try to encourage people to supervise this, what we call honors projects, which is the equivalent of what you're talking.
It's not, because honors project doesn't have to be original.
But
The understanding is that it's not original.
Which hopefully leads to, we're assuming it's a similar thing. But even at that level, to get staff to volunteer to supervise that is another story. So you always end up with getting 1 or 2 people supervising 3 or 4 honors projects. There are many that shy away and hope that the head never sees them. You can do what you like. We'll encourage you. We'll give you less grading, what you call grading, marking. We'll give you some sort of credit, but it's always a small subgroup that's usually doing a lot of the supervision. So you see that, and we can't encourage this with $3,000. We don't have $3,000 to give you. Those are the kind of problems we experience.
I can answer part of that question. I could say something about how my university distributes the undergraduates, and let's say the 4th year students. So our undergraduate program is 4 years, and our students in their 4th year are all required to do, a senior thesis or senior capstone or whatever the university calls it. And so we get as a department, we get a list of all the students. We give them a survey to try to gauge their interests, their favorite courses, of course, they really didn't care for, things like that. And then we distribute them equally amongst the staff. So everyone gets the same number.
Really?
Yeah. And if I have 3 1 year and someone only has 2, then we balance it the following year. So we distribute the students.
You see, in that case, we have an additional problem. And that is that our staffing goes like this. You have a lecturer level. We have then the senior lecturer, which is the equivalent of your assistant professor, and then we have associate and full professor. Now, at the lecturer level, these are what you would say are new graduate PhDs and so on that are now teaching the normal loads and so on. And you don't want to put that sort of condition on those early staff academics and so on. So and the number, that means in theory, the professors and the associate professors should be forced to do that kind of thing. And
So
even that doesn't.
we might take this into account and give fewer to the newer people, but the newer people might also need to have some projects they supervise with students. So it depends.
Sorry, Siba, keep taking the question.
It's fine. You also took the actual question. Thank you. No, that's okay. Thank you so much for this. So I just wanted to check the first part on the funding, how this is funded. I know you said that you got a grant, but I wonder if that grant allows for collaboration with other institutions outside the US at all. And then the second part is, I know that there's one program here in microbiology, and I know that also Zuraban team do something similar, where the students actually get these projects when they come in the microbiology class. They part of the enrollment on the module is to choose a research area which they will do. So it's part of the curriculum. At the end of that, so it's done over the whole year. At the end of that, they have to present. So then we get invited for these poster sessions and then judgment of that. Some of the work is publishable. But what we're trying to do there is to try and encourage other programs as well to embed the research in undergraduate programs. But those classes are smaller, but I think the challenge is how to deal with 200 or 300 in a class and how to embed that as part of the program.
Yeah, I agree. It is a challenge with those kind of numbers. Yeah, and so one thing in thinking about this is, you know, what benefits are there and what barriers are there? And you've pointed out many, and so it's hard, and it's different to institute in different places. The grant we have, the National Science Foundation funding can only be spent in the US. The one benefit I will say that it also gives course credit is when we paid students $3,000, those could only be US citizens or permanent residents. The course credit can go to any student. So we can have international students benefiting from this, which is new. So a little bit more about this summer workshop. So we have the professors and lecturers attend a summer workshop. This is a 3-day workshop. Many of these people who apply for this grant and who get the grant are newer PhDs. So this is something, you know, towards the start of their career that they might want to do. But we also try to have a good mix in this group each year, where we have some more experienced faculty with undergraduate research and some very experienced faculty with undergraduate research. So I got one of these mini grants in 2015-16, and at that point I had already supervised over 15 undergraduate projects, maybe more than that. So I think I was selected as one of the more experienced people. So we want to train these professors and lecturers as mentors and advise them on how to organize and continue to operate this at their own institution after the grant ends, because this grant is for 1 year. And so the sorts of things we talk about in terms of mentoring is to get them to really think deeply. What do you know about research that your students don't? Some of them who are new, just recently finished their PhDs, haven't put this into context, but even more senior faculty haven't always. Effective collaboration strategies. How to find a good problem and what is a good problem for undergraduates. How to give a good presentation. In terms of finding a good problem, you'll notice that now we require one of the institutions in each pairing to be a 2-year college. So none of these students are doing a project in their 4th year or their 3rd year because they are 2-year colleges. So they're doing a project in their 1st or 2nd year of college now. And we're also trying to have the same at the universities. Where to publish, especially if these are not groundbreaking results that move forward the frontier of the field, which you're probably not going to have with undergraduates, but they're finding small original results. Where are good places to publish? And we do have some undergraduate research journals and things like that, where there are original results, but maybe not a huge result. And then just how all of this helps us with our own research as well. These are all good questions for us to reflect on. When we also spend a lot of time talking about how to get started with students at the beginning of the academic year. So setting expectations, models of groups, and starting the project. Handling difficult situations that arise throughout the year. And supporting the students during the research process and beyond. So in this program, we expect the students to work 10 hours per week. And so at the beginning, we encourage them to put it on their calendar when they're meeting as a group, when they're meeting with the faculty member, and when they're going to work on their own. And then they have to have a plan for making up hours if one week they missed something, they had an exam or something else. Many of our students work other jobs because our university is expensive, really expensive. And so how do you make up the hours if you didn't fulfill your 10 hours in 1 week? And then on the very first day we meet them, we give them something to do, not something to read, not go read this article, but something to do mathematically, a problem to work on. And so this is now my model of how I meet with my students. And there's, of course, many variations on this. So I have sometime early in the week, Monday or Tuesday, the students meet together. Without the professor. So they meet just the student group and they go to the board and they present their work to each other. So they give each other a research update. And going to the board and presenting is important. At the beginning, they might just be learning some definitions, but they often feel like they understand a definition that they don't. And when they try to present it, another student says, well, what about this? You know, they really work through a lot of problems. And this is great because it makes them much more prepared for when they meet with me. And it's also a much lower stakes way to do it, just in front of other students instead of in front of the professor or lecturer. Students can work through details and explanations and really iron out a lot of things. And so they meet with each other for about 90 minutes. And then later in the week, they meet with me. Again, I have them go to the board and present their work, because if we sit and they just point to things, it often doesn't go as well. So having these little, I did a project with a biology lab, and they would have these weekly lab updates where everyone working on different projects would just spend 5 minutes telling everyone what they had done, and then people would toss around ideas. And it was this really collaborative environment that even if you weren't working on the project, you could still contribute something. And so I try to encourage that with my students as well, kind of have a research update each week. And it makes sure they're all engaged and they understand. So no one can sit in the background in this group of 3 to 5. I also always have them bring something written to the meeting. It could be a list of questions for future investigation. Maybe I have them actually type out a bibliography so I know they're using LaTeX properly, summary of results of a paper they've been reading, things like this. Each week I have them bring 2 to 5 mathematical questions, and I have them all put it on the board simultaneously. If they get there early, they're already writing on the board. So when I arrive in the room, we've got just this whole massive chalkboard of questions, and then we can discuss them together, look for patterns, group them into types of questions if there are similar ones, and divide them up for investigation for the next week. And maybe we'll say, oh, we think these are a couple that we could knock off this week, and we think these are big questions that we want to build up to over the course of, the next month or so. And so having them build the skill of coming up with questions themselves is, for me, an important part of what they do. So the other thing I have them do is, when they have this meeting with me, 48 hours beforehand, they must email me with a summary of their week's progress and any questions they have. And I tell them that's to help me prepare, but it's actually so that I know kind of where they are 48 hours in advance, and they're not just thinking about this the night before they meet with me. So this summarizes the early meeting with the other students. It'll say, well, we ran into this question and I can think about it a bit, but this helps spread out the work throughout the week, because I'm only going to meet with them once a week usually. So early in the week, they meet together. Later in the week, they meet with me. So they have 2 to 3 hours of meetings and then 7 to 8 hours of working alone on the project. I've kept track of this in different ways. Sometimes we've had a common blog where they each log their hours, say what they worked on, and then other students will comment on it and give hints and things like that. So different ways of keeping the conversation going even when they're not together. The very first meeting, you know, there's different ways people handle this, present the problem in problem domains. Sometimes we give them notes to read before the first day or some problems to do before we meet for the first time. And then in general, have them pick their problem they want to work on before the end of the third week and start digging deeper into it. So instead of having them read a lot of background at first, presenting background as it's needed. So some of the common mistakes people point out is presenting for 3 to 4 weeks before having students start doing research, as opposed to presenting material as it's needed. Go home and read a paper and come back with questions. This tends to be too general for my undergraduates. They will go try to read a paper, get stuck, come back, and you know, it doesn't get very far. Or overestimate what can be done in undergraduate research. I mean, unless you have a really spectacular student, you have to think about what's going to be possible here. So some of the questions we discuss as we get started as a group are, you know, who are you as a researcher? Get the students to think about this. They've never done research before, but they can think about how they approach problems, how they approach studies, how they approach their classes, what they like and what they don't like. We talk about group roles. If we have something that we're going to publish, how do we decide authorship? How are we going to resolve disputes? What pet peeves do they have? Do they hate when someone says trivially or clearly or things like this, right? What strengths do they think they're bringing to the project or to a collaboration? And establish what our group norms and behaviors are going to be. And if you do this all in this first meeting, you have this to come back to. As conflicts arise, you can go back and say, well, remember we said this is how we would resolve disputes, or these were pet peeves we were going to try to avoid, or things like this. So some of the roles we talk about, and often if we run workshops just on collaboration, we would put you all into groups and assign one of these roles to you and have you act this out for different problems. And it's very effective to think about how each of us does this ourselves. So you might have the silent expert in your group who knows the answer but doesn't speak up. So think about what the problem with the silent expert is, or the doubter. So even after the group's been working a long time, they cast doubt on the problem. Airtime dominator, interrupter, the glory hog, claims ideas of others as their own. The naysayer, or the note taker. The note taker, when we run these groups, we have one person not say anything and keep track of how much time each other person speaks. Does anyone have an idea who they are themselves? Yeah. So we could look at a few of these. The airtime dominator. Well, there's a lot of research that shows in collaboration, airtime matters. And in fact, in a group of 8 people, 3 people tend to speak 67% of the time. Well, what does that leave for the other 5? Yeah. So this is a real problem, right? You have 5 people in your group who typically don't really get their voices heard. And airtime does not equal influence, but it's perceived as influence. So the loudest voice can be seen as the most influential, even if that person did not contribute the most. So thinking about airtime dominator, are you an airtime dominator, or do you have an airtime dominator in your group? And then how to moderate this is effective for collaboration. The doubter. Well, research shows that women are the target of more doubt-raising questions than men. So in other words, often when a man presents statements, they're more likely to be accepted. When a woman presents statements, they're more likely to be questioned or scrutinized.
I don't know if that's true.
You don't know if that's true? You get bonus points for that. minus 10 points.
You've been stared.
So, and this is not just in mathematics, of course. You see this in other, many, many other places. The interrupter. Research also shows that men interrupt women significantly more than they interrupt other men.
I don't know.
Women are the target of interruption. Also not only true in mathematics, but you can see in mathematics, I mean, I look around this room and I'm a little surprised how few women there are here. And I know at least 3 over here came just for this talk. So when I take them out, we're getting even smaller. This sort of gets amplified when we have a field that has so few women already. And the silent expert. I didn't realize there was such a problem with the silent expert. You know, I just kind of thought, well, maybe they're just afraid to speak up. But we have this common knowledge effect, or what we often call groupthink, where groups will focus on the shared information as opposed to maybe the correct information of someone who's, you know, doesn't speak up for whatever reason. And so pulling that person out of their silence is important to the progress of a project as well. Because it might seem less important when you have all this shared information. Research shows women have less influence in team meetings, so good ideas are less likely to be credited to them, even if they make the point first. Do you have something to say? Why stereotypes and bias? I mean, I can stand here and just tell you stories for the whole time about people coming to my office to ask for a stapler or a pen or scissors. And I say like, well, who's your professor? And they're like, oh, I don't want to interrupt him. What is that? Yeah. So we're not perceived as experts. We're not perceived as professors, and especially in traditionally non-feminine domains. So our ideas can be overlooked. And when a woman makes a suggestion in a group, people are often less likely to go with that suggestion. So remember, I'm making the suggestion for undergraduate research. Let's go with it. So these are the roles. Again, I didn't talk about all of them, but I just talked about a few of these. And you probably know one of each type at least, right? So if you want to build the best group, what do you think is the most important or effective? Yeah.
Say you've got a silent expert, can't you group all the silent experts together? So you effectively, you force someone to speak up, or if you've got those that want to speak all the time, group all of them together. See what happens. You know,
The problem is for the silent experts is you don't know the silent experts because they're silent.
It is true. The silent expert you might not know.
What you're saying is put all the silent together.
At least the ones that want to speak all the time. Those guys, you know.
Yeah, put the silent lot and the.
You have to figure it out.
So imagine now you're forming a research group in your own research area. How many people are in it? 3, 4, 5? You can't have all just silent experts or all airtime dominators. So there's been a lot of research done on this about like what makes the best groups. And you would think, I don't know, do we need one of each type? Do we need to balance these somehow? And what the research says is that even speaking turns, everyone speaking the same amount makes the best group. And social sensitivity, being sensitive to each other's background. And so at my university, my department has adopted this, where we go around and take even speaking times, because we found if we didn't do that, 3 of the 8 people or whatever would take 67% of the airtime. And so there were people sitting silently who didn't feel comfortable interrupting or jumping into that fray. And so we just deliberately take even speaking turns so that everyone has a chance to speak and is required to speak, so they can't be the silent expert. So this is what the research on building good collaborative groups says. And so then you want to think about the benefits of undergraduate research. How do you measure it? How do you convince your administrators of its value? And what funding opportunities are there? Can you get external grants or institutional support for this? And so I also mentioned at the beginning, we provide funding for travel to a regional meeting in spring. We used to bring everyone to a national meeting. And then we decided, well, that's not that important for undergraduates. If they don't have to travel so far to still have a really important and formative conference experience. So we suggested, well, maybe funding for travel would be a bit less if we went to regional meetings. Now, you all know the size of the United States, so a region can still be massive. All students who get these grants are required to present their work at a conference, and we do have regional undergraduate focus conferences. Give a few examples. So the Mathematical Association of America is our national society that is most concerned with the first 4 years of university. It goes beyond that, of course, as well, but there are section meetings. There are 29 sections, and the spring meetings almost always involve students. We have regional undergraduate mathematics conferences and national conferences on undergraduate research. I live in the Pacific Northwest. I live in Portland, Oregon, which is not like a 3-hour drive from Seattle. So we have a Pacific Northwest MAA meeting. We have the Northwest Undergraduate Math Symposium, which is going to be Saturday, November 4th online. So if any of you want to go, you can go and see what these students have done. And the Pacific Inland Mathematics Conference.
Will you share the link with us?
Yeah.
We should share it.
Yeah. I will find the invitation. You'll have to register, but it's free. And let me show you what these sections look like so you get an idea of what I mean by these 29 sections. So here's a map of the US and Canada. People in Florida think that it's really big and like they have to drive so far to drive across Florida to go to a meeting. And then the people in Texas say, oh, no, Florida's not big, Texas is big. But I live in number 20, this big red one up here, and this is my section. So driving 12 or 14 hours to our regional meeting is not uncommon. But this next spring, our meeting's going to be here in Anchorage. So I'm not driving, I'm flying. So even though we're saying regional, this region is, massive. And many of these regions are quite big.
But that includes all of Canada.
This includes all of Canada.
Okay.
20 includes 2 provinces and 3 territories in Canada. Yeah.
BC.
This is BC, Alberta, Northwest Territory, the Yukon, and Nunavut. Yeah. So we have 5 parts of Canada. And this is Alaska. And then we have 5 states and 5 provinces and territories. And then you see we also have, of course, Puerto Rico and the US territories. So these are regional meetings, but the region's big. I mean, South Africa is smaller than many of our regions.
So Stephen here got a complaint.
Sorry. So we talked a little bit about how undergraduate research could succeed here, benefits and barriers, and staffing is an issue. The number of students is an issue. This is one reason we apply for this funding and provide these grants to try to encourage universities to support this and to institutionalize it. One question I brought up before is, what do you know about research that your students don't? We can discuss this in our group, but let me show you some of the things that our groups have come up with. So here's a good quote to keep in mind. If we knew what we were doing, it wouldn't be called research. It's challenging but rewarding. You need to be patient, especially with learning background information. And this is, you know, students aren't used to learning at this pace, especially if they're in their first or second year of university. It's okay if you don't understand an idea the first time, or the second time, or third time. Karen and I are having that experience right now, so she's nodding a lot. Didn't we just talk about this? Yes, but I still don't get it. We all get stuck and frustrated. I was on a Fulbright review committee and with a historian, and someone was proposing a project, and he said, but what are you going to do if you get stuck? Like if you go to France and you're researching this history and then you get stuck with what you're doing. And I was like, wait, isn't research just being stuck? So like mathematicians think being stuck on a problem is a normal state of being, whereas apparently other academics from other fields maybe don't think about it in the same way. So it's a good thing to keep in mind and to advertise to our colleagues from other fields. Take a break, explain it to someone, even someone, you know, who's not mathematically trained. Review the background, and sometimes it becomes unstuck. See if the problem can be modified. This is one thing that students don't see at first. They think the problem they start it with is the problem they must do. But of course, the problems that are effective for undergraduates have lots of small successes along the way and can also pivot, and you have to be ready for that.
So you see, that condition, see if the problem can be modified, you know, about students giving their opinion. I usually tell the students, whatever you do, don't use your brains. Just do what I tell you to do.
Well, I'm
just joking.
So I have the students choose their own problem. I think it's difficult to come up with a good problem. Yeah. Don't use your brain. And so a few more ideas for this. Share your ideas, be open to different ideas and approaches, and follow through. Know that it's time consuming. And keep going. And with students especially, but I think with yourself as well, celebrate every success, no matter how big or small. And so here's another quote that this group who came up with that list, particularly like those who achieve the most are not necessarily the most skilled, but those who concentrate it long after others have given up. So this was compiled at one of these summer workshops. And I just wanted to point out this book finally, just in case you're looking for ideas for questions. This is the first in a series of books called The Foundations of Undergraduate Research in Mathematics. I think there's about 4 books now. So that's it.
Very much to Professor Moinara, and I guess you answered all the questions in the progress of the talks. I'm not sure if our next speaker is there. Yeah, so I'll put it up to there's no, all right, there's no problem. Yes. Okay. Okay, sorry, I was just can we send you more follow-up questions? We get questions.
So my session is in conjunction with this, so we can use some of the time for questions.
That's what you said.
Would you like to
interactive, that's fine.
Would you like to ask questions, sir?
Oh, are we gonna have a question?
No.
Karen, can you pass these around?
We can have a chance.
Okay,
if we're gonna
thank you.
open for the questions.
Sure, sure, yeah.
What are we just asking? There's no way I'll- Well, I have one.
Yes.
question. So. My question is there a single problem so it's a group working on a single problem, or is it sort of a set of shared interconnected problems and each person is responsible for a part? Like, what is the
Yeah.
actual research model?
I think this can vary quite a bit. The question is if it's one group working on a single question or if a bunch of interrelated questions. So when I had one of these grants, several of my students were in their 4th year, so they were required to do independent projects. So what happened was the 5 of them learned the background together in the first semester and then split into separate problems. And so, but it can work both ways. What also happened during that year is after about 3 or 4 weeks, 2 problems arose that the groups really liked, and they split in a group of 2 and a group of 3 for a long time. And so they kind of went 2 different directions early, and then they each had something independent to present in the end, by the end of the year. So that's a great question. I think some other groups continue working on the same thing. And it also depends on, are the students in the 1st and 2nd year, or are they in the 3rd and 4th year for that?
Okay. Yeah, I think that's it. I also just had one brief comment. I think in South Africa, I can say safely that, you know, in our undergraduate, we do sort of have research in physics and chemistry, because I know even in our 3rd year, usually there are projects that students get involved in, but it seems like in mathematics, that's something fairly new here. We're not used to that. So yeah.
Same happened with us. I think, you know, I remember when I finished my PhD and I had an undergraduate who said he wanted to do research with me on matroids, which is a bit, you know, abstract. And I emailed my PhD supervisor. I said, I have a student who wants to work on matroids. And he wrote back 1 sentence, undergraduates can't work on matroids. But 20 minutes later, he sent me a question. He goes, maybe they could try this. So we tried that. The student answered it within a week. So, you know, it was a pretty straightforward question. But then we built a new question out of it and we published. So the first student that worked with me published. But at the time, it was really pretty uncommon. And it was much more common in chemistry, biology, maybe physics as well, you know, experimental physics at least. And so we went through the same growing pains, I would say. And now we've gone from requiring all 4th year students and many 3rd year students to do research to starting to institutionalize it into the 1st and 2nd year. So very early research.
All right, thank you. Can I hand over to Professor Yanel? I'm gonna get it right. Professor.
You can put it in Latin. So
all right.
Thank you.
And hand over. Thank you.
Thank you very much, Professor Naudauer, for this absolutely fantastic overview of undergraduate research in USA. In this half an hour, we're not going to go away from that topic. We're going to stay with that topic. I want to tell you a few things in South Africa, which could suggest that maybe this could work here, and also how specifically it should work and could work. So before I do that, I want to first show you a page of the kind of introductory page for the Mathematical Structures and Modeling Research Program, in which we are, through which we are developing some ideas about undergraduate research. The program itself is a research program of the National Institute of Theoretical and Computational Sciences. You see here Professor Francesco Petruccione, who unfortunately couldn't make it for this session. He wanted to come, but he got busy. It has a lot of nodes around the country, and we recently, the Stellenbosch University was awarded as the leading node, if I'm not mistaken, thanks to the leadership of Professor Patriciani and also Professor Moyo. It was a great thing, but it doesn't mean that Stellenbosch University is any superior to any of the other nodes in terms of utilizing the resources of the institute. There are also some graduate coursework that's offered under the institute. I'm not going to stop on that too much. These are some pictures, photos of some of the members of the research program of the mathematical structures and modeling research program. We've got quite a diverse representation of subjects of mathematical research topics and collaborations. Also, there are new collaborations that have arisen through this program. And then there is the Future Mathematicians program, which was conceptualized within this research program. And this is what I want to tell you about. And to do that, I'm going to actually go to the page of the Future Mathematicians program. So in South Africa, the school learners, their parents, and even undergraduate students do not know that you can do research in mathematics, that there is such a thing as exploring mathematics. And most of them think that mathematics has already been discovered, and the only thing you can do is just to use it for various purposes. They don't know that you can make input into discovering new mathematics. So the profession of a mathematician is something that people do not know about. The teachers, the school teachers, when they identify a talented mathematics student, they would tell that school learner that they should study either engineering or actual science. The teachers do not know that the student, such a talented student, can actually study mathematics at the university and become a mathematician and then get a job even in actual science area or engineering area. And I know this because I've talked to such teachers. They really do not know. So the idea of this, one of the ideas of this program is to bring this awareness, but also to bring this awareness not just as some theoretical awareness, but actual experience. Now the question is, can a primary school child experience mathematical research? And if yes, what does that mean? So one of the things we do here, this is actually a work of a PhD student in math education that's co-supervised by myself and a colleague in the Faculty of Education. We have exploratory activities where a primary school kid is given a theorem that they have to prove. But now it's not formulated in this language. So there is some discussion which involves some assumptions and a certain conclusion that's drawn from these assumptions. And then we ask the children to convince themselves and others that the conclusion that's drawn is the correct conclusion, that they're certain that this conclusion is a consequence, is a logical consequence of the assumptions. It's a group work. It was experimented in environment of mathematics clubs. So this PhD student I'm referring to, Noluntu Bart, she is actually subject advisor. 70 schools are in her under her responsibility in Port Elizabeth area. And these primary school kids love doing these kinds of things. Not just that, they can come up with very, very good stories of why certain conclusion is a valid conclusion based on certain assumptions. We also experimented the same set of problems we experimented with high school learners. And one of the example schools where we went to was Durban Star College. So we had a class. This is how the cover page of that little booklet containing mathematical exploration activities looks like. You'll see it on the screen just now. And we had approximately 20 students. They were from grades 8 to 12. They were together working in the range of these grades. They were divided into 4 or 5 groups. And they had to prove some theorem about area of a rectangle which is being tiled with tiles. So the problem statement was in a very much real life scenario. So they could relate to what the problem is asking. But the problem wasn't to find the area. The problem was to explain why the given area is the correct answer. And out of the 5 groups, 3 groups out of the 5 gave perfect proofs. These proofs could have been, I mean, they were at the master's level, maybe even PhD level written out proofs. That they even presented them and it was perfect. And each of them had a different strategy to proving the same thing. It was quite spectacular, and they enjoyed it tremendously. There was a Facebook post they made after this about their experience. So far, there's a feeling that if it's done the right way, research at undergraduate or school level opens up passion for mathematics. It unlocks mathematical passion. One of the feedbacks we received from a teacher was that those kids who usually struggle in mathematics, who usually are silent in math classes, now they were active in that group work and they were flourishing there. Of course, I agree with Farai, Professor Mlanga, that if we take our 300 students in the undergraduate course and we force all of them to do research in their second year or third year, this is going to be a complete failure. I personally think that mathematical research should only be available to those who express interest in it, who express passion for mathematics. And that does mean that we should not restrict students by their marks. I think for this kind of activity, we should open it to anyone, irrespective of their marks, as an opportunity perhaps to become better at mathematics. And then when they go back to usual classrooms, they can then, their marks could improve. Now, it is very important in a research environment, at least when you're still developing your research, it's very important not to be afraid of being criticized. Now, you talked about in a collaborative environment, you might be stuck with something. And I imagine the head of a department comes in and tells you, oh, so you haven't made enough progress. We cancel your collaboration. You should have had results by 11 o'clock. So this idea of undergraduate or school research, it cannot work with marks or examination. It should be something that's free. It shouldn't be something that's confined with performance. So it will never be, it shouldn't become a subject or a course that has a mark attached to this, where this mark is determined by procedures that many of the courses today have, which in many cases demotivate students, to be honest. A lot of students get demotivated when they have to write that mathematics exam and they forgot something, or maybe they were nervous on that day, and then they feel that they cannot accomplish in mathematics just because of that accidental psychological state they might have been in during the exam. So the idea is to kind of complement all of these things. I see that you wanted to ask something halfway, so can I give you my microphone?
Yeah, I think one other challenge, I think, is is to have good problems to be solved. I mean, the formulation of that, in as much as, I mean, I understand the issue of, I mean, taking down even to the school level. But I think the other challenge that we may have is, I mean, do we have, I mean, the problem formulators because it doesn't help to just give some problems which are not worth of, I mean, which are researchable, something like that. Thank you.
Absolutely. I completely agree with that. And let me also maybe make a remark or two about the process of formulating problems. So together with Sirin Ratilal, you've seen her picture by now. She's actually the director of the Future Mathematicians program. We've made a kind of a mapping out of the entire process, starting from developing the problem. So this is how it looks like. So the first step is the mapping step. You see on the left side there. Every mathematical, we call these things, each such session we call a mathematical expedition. It has a map that is designed by an architect. Now, for the kind of problems that we experimented at school, these were not research problems in the sense that they wouldn't arrive to new results, but they were research problems in the sense that the result would have been new for them, for whoever is discovering. It's not like they had to apply existing technique to prove a theorem. In the beginning, it was challenging. And that's exactly what my PhD student is actually doing now. She's developing ideas on what kind of, her PhD topic is in fact task design aspects for stimulating curiosity, creativity, and other mathematical skills. But in the end, after overcoming a few challenges, we came up with this idea that actually it's very easy. With a few examples, then you can start to see that it can be very easy to create problems. But now creating problems that are original, let's say for undergraduate level, if you want to, later undergraduate level, if you want to really students get original results. One methodology that we've tried, so this was a methodology that I discovered with my topology class in the third year, a couple of years ago. So step number one, you make a list of 3 concepts. It could be that you have a list of 15 concepts and students choose 3 out of the 15, or the group comes up with 3 concepts, different person for each concept. You make a list of 3 or 4 concepts. That's step one. Step two, you have group discussions where you try to relate these concepts with each other. Step three, based on the relationships you might have noticed among these concepts, you start formulating a research question. Step 4, you start solving the research question. And I've tried this method a few times and it works. You can give it a try. You end up coming up with questions that you haven't thought before. And that I would imagine that's largely due to the fact that I think it's also why concepts are important in mathematics. When a concept is formulated, then a lot of times idea for mathematical research emerges as a consequence of noticing a relationship between concepts. So if you randomly take a list of concepts and you randomize that part of the process, but then you still reflect on them, then you start noticing some relationships which you wouldn't have noticed because previously those concepts would never been placed next to each other. So this could be one method, and another maybe would be to read that book. Nancy told us that it's already a few volumes of that book, and I would guess that after some experience, one will notice some kind of pattern of how can questions be easily produced in some sense. But I agree, it's in general. I think one of the things that makes mathematics special is that the research questions are not too many. It's like gold. If it was too many, it would be too. It wouldn't have too much value, right? So it's always a nice feeling when you discover an interesting new research question. So one other thing I wanted to say is that somebody mentioned the Russian system. Well, I come from Georgia, and the system in Georgia was, I would imagine, yes. So the Soviet system. I come from Georgia, which was one of the countries of the Soviet Union. When I was an undergraduate student, every year we had an undergraduate research conference, a national one. First, winners were selected at each university, and then they were competed across the university. So there were 2 events. And it wasn't compulsory, but we had quite a lot of participants each year. They had supervisors, and usually
very small.
very small, yeah. They had supervisors, and those who would show themselves in these conferences usually were also the ones who would have continued with mathematics afterwards. But in many cases, students would have been inspired to continue with mathematics after experiencing undergraduate research. I myself would have given talk at every year, first year, second year, third year, fourth year. We also had fourth year. Yeah, so I also gave that one. None of that ended up being published. There were new results there, but not worthy of publication. Maybe I'll publish them at some point in the future. But then when I started with masters, I was able to come up on my own with research questions right at the beginning of my master's studies because of having that experience in research in the previous 4 years. And that gave me a huge advantage because now I finished my master's with completely original work that even the supervisor wasn't involved in coming up with a problem for masters. So that's one thing I wanted to say. The other thing is that passion for mathematical exploration is really, and passion for mathematics is really one of the reasons we might want to implement this kind of things at undergraduate or school level, because we have a huge problem with that. Mathematics makes people scared. I was once invited in a radio interview about the topic that mathematics is scary. And what can we do in South Africa to make it less scary? And I think that, okay, now I'm going to make a specific suggestion, which it's the first, so this is an idea I got a few days ago and I didn't tell it to anyone. So it's the first time I'm sharing it with you. So yeah, it was secret until the next 2 minutes. I learned through my daughters that are going to school in Stellenbosch. I learned that children here can choose subjects that they want to study in high school. Now, which subjects can they choose? Whichever the school offers. Which subject can a school offer? Whichever the government formulated as a valid subject to be offered. And if you look at those subjects that can be potentially offered in a school, there's a big variety, all sorts of subjects there. So why not having a subject on mathematical exploration? Not to replace any of the existing mathematics subjects, but as an elective, an additional subject that a kid could get. In fact, my daughter was quite sure about all of her subjects except the last one. And so she chose consumer studies because she felt that it would have been the easiest among all the, she wasn't interested in any of the other available options anyway. And I thought in that moment, okay, but if there was an additional mathematics subject, she would have probably chosen that one. She's interested in mathematics so far. So that's an opportunity how one can embed this, that if the government formalizes such a course as an additional subject, then we can slowly implement it in various schools and kids can start taking them. And then the spirit of that would be to ignite the passion for mathematics. So it should do all the things that the usual math subjects are not able to do because of various limitations, including the curriculum that needs to be covered. I think this is where I'd like to end. I also would like to have some discussions before we finish off the session. So any questions? Yep. All right.
Thank you, Zurab, for the presentation. So this is, so it might be related to this, but I also saw that, so apart from the work you're doing with the schools, there is work with other institutions where you bring also undergraduate students together Are you able to say anything around, because I know I attended one competition you had on a Sunday. Was it a Sunday?
Thank
so
you.
I don't know if it's
Yeah, thank you,
something that
Professor Moyo. So we have had since 2011 second and third year courses called Foundations of Abstract Mathematics, which are very much based on this Moore method type of thing, except that we didn't know about Moore method when we started those courses. So all the assignments are for the students to work out problems on their own and solve them on their own, and even sometimes come up with theorems on their own. Then in August, we also had what we called Exploration Olympiad. This was for undergraduate students. We had 4 teams, 2 from Stellenbosch, 2 from UCT. And we followed that method I told you about with, we begin with 3 concepts, and then they discuss and so on. It was an interesting experience. We felt that we wanted to have a bit more time because of the other subjects students had. We didn't have full day. It was more like 3/4 of the day. But the students continued working on the topics they came up with on that day, and some of them have made good progress. And in fact, the UCT group will now be joining our NITHEX research project because they, on that day, happened to rediscover one of the research topics we're working on in NITHEX. So it was quite successful. But thanks for allowing me to say. And I also want to say one other thing is that when I first found out that Professor Moyo is joining Stellenbosch University, I discovered that she's interested in undergraduate research. So I quickly tried to send her a message, but how do I send a message to such an important person? So then I discovered that she was on LinkedIn. So I wrote a message to her that I know that, well, first of all, welcome. And I know that you're interested in undergraduate research, and I'd love to collaborate on that. And she kindly replied almost immediately. So that was nice.
Any other questions?
Maybe you could also tell us, Professor Moy, about your
So maybe I can ask about whether there has been some inroads already, maybe here at Stellenbosch, in terms of trying to implement this kind of a model to the undergraduate research. Yeah.
So I'll say yes. In some parts we are building, but I think with the work that Zurab is doing, we've already started. And then also in some of the groups, like the microbiology, because of the resources, but don't record me on this one. I think that because the DVC was, from that faculty, so they got a lot of resources. So they have actually a program where it's embedded in part of the curricula. So when you come as part of your course for that module, or at registration, you already are put into groups, and you're given some funding actually for your research. It's a small grant, and then they have to be resourceful. Sometimes they have to approach industry partners, but at the end of that, there are presentations, and also the industry partners come and so forth. Some of it is very interesting, quite innovative. But as you know, so we've got some who are able to start up companies. So each of the labs have got companies linked to them. So it's a big enterprise in that area. But I wish we could do the same, of course, in mathematics, for especially the applied side, in terms of trying to, because we rely heavily on external grants, but obviously not everything lends itself into that. But obviously we are trying. So I think that we are making some progress. This is part of it. And we are open to collaboration because we are also experimenting. So we want our students also to interact with other students. So if you have a great idea and you want to, so Zurab is the president for the South African Mathematical Society. Nobody introduced you, right? I think we didn't do. Oh yes, my chairperson. Yeah.
Sorry, I don't think I did my job too well.
So he's doing many things, the mathematics, but also trying to promote mathematics in the country, and also for other universities. And I think also Abdul, because of the Center for Excellence for the mathematical sciences as well. It's part of the collaboration. So it's just open to discussion. I just wanted to say, so in this group, we've got a number of students who've asked, and this is for Professor Meleshko and others who have a bit of time. So there's a group of also, as you know, our colleagues and students who are also staff students who want to do a bit of programming during these 3 days before we leave. I think I've had a request from a few colleagues. So if there's programming for reduce, yes. So I'm just highlighting that if there are people feel that they have some time, an hour, or even if it's in the evening, today might not be possible, but before Friday. So I think that is a need. The big need we have is to help our staff also to accelerate their skills that they need for research. Because of the education system, our system typically in many of these areas starts from the middle without really a lot of the stuff that is needed before. And that's why maybe we have, so it's both ways. Thank you.
Sorry, can I just add one more comment? So, of course, one of the purposes of presenting this session at the Symmetry conference is that to invite you to think of how you could introduce your research at the undergraduate level. And if you've got some ideas, let me know, and we can develop them and experiment them with undergraduate students. And thank you very much for listening.
I forgot to get your picture. Sorry, but I know it's recorded, but okay, so it's just a pause. I'm sorry, I'm taking your time for the next.
Oh, this is something different.
Okay, cool. Okay, done.
Thank you.
You never thought of producing
Okay, I think we have a break because the next speaker is, yeah.
Oh, really? Okay. And then we are leaving after that, right? Or
And
is
then
it
there's
still
one
not?
more speaker.
One more, okay.
So you can have a half-hour break and then come back at
Fantastic.
4 o'clock.
Okay, but maybe you should tell them, please. Yeah.
Okay, can we have a short break and then be back at 4 o'clock for the last speaker? So
present speaker
it looks like it's Dr. Tanki Motsepa. No,
yeah, he's not
it's not here. So the next session will be in half an hour, 4 o'clock. Oh, we have to.
Yeah, so if the next speaker is the next speaker there.
Tembi, then after that's Tembi.
Yeah, so we finish and then because you do need to rest before the next session to take a break, so we can finish.
Is Tembi?
Tembi is here, yeah.
Yeah, it's already
You mind presenting your
yeah.
Did you? Okay.
So that will be the last speaker of the day.
Yeah. And then you rest a bit before the back comes. You can leave your stuff in the room. Drink water, make sure you have enough water.
Thank you. I just clip this on.
So click
I clip it on here.
yeah,
Thank you.
you can.
Thank you so much.
So you show me how to move this.
Just want to get your file.
Okay.
Give it a beat now.
No, I'll be fine. I'll be fine. Thanks. And let's look at this.
This one.
Let's check.
Kingston.
Yeah.
Oh yes. This one.
Yeah. So, but now how to close this? Because I need this to be bigger. You can close all of this. Close this.
You got it?
I don't know how to do it. Yeah, I think we need to close this here. We need to close this here. I think so. Yeah. I don't know. And then what I want to do, Simo, how to move this? Is it as if it's got a problem? How to move like to the next slide?
Oh, there's arrow.
Oh, there's arrow. Oh. Oh, this one. This one. Oh, okay. Yeah, but we have to
Need them out, not PowerPoint.
Can you make it bigger? You can't fit it into the screen.
I switched off my
Okay, thank you.
And how to go, you know how to go to the next one.
You said I must use arrows. Yeah.
Just use the arrows.
Okay.
You got it. All right. Okay, so next presentation is by Tembi Mkhize from Durban University of Technology. Be talking about linearization of a system of second order stochastic ordinary differential equations and their applications. Thank you.
Okay, Chris, you all. My research is on stochastic differential equations. Maybe a person will ask a question, why necessarily stochastic differential equations? We encounter every day in our lives. So we cannot just ignore them and pretend as if they don't exist. They do exist. So I know that the community that deal with this stochastic differential equation is very small, and the theory is still developing because people are trying to ignore this kind of equations. These equations, okay, let's see. Okay, so here they just include, right? This one is faster than this one. Okay. So this one, they include the stochastic component. Okay, they include the stochastic component, which means there's a random factor, which is also included in these equations. And they have found so many applications, like in engineering, where we look at the theory of lasers, and in physics, and in finance, the stock market, because this kind of equations, they are not like smooth. They fluctuate all the time. So we have to deal with the fluctuation here. So I think that's why some people, they just run away from this because they are used to all those smooth functions. And here, this one is not smooth. It's full of fluctuation. And these ones, they play a role similar to that of linear equation in just a classical theory of ODEs. So, and most of those stochastic differential equations are nonlinear. So most of them are nonlinear. So my research is to look at the linearization criteria. And then from there, can I use the theory that is already developed, like a Lie group theory, to find the solution for these equations? Okay, that is my research today. Okay. It is my talk. Okay, so those are people. Okay, this is slow. Those are people that already tried the linearization criteria for those point symmetries. We've got all those people that have done a lot of work, and then they extended that to the second order system. We see that Mohammed and Moleshko, and then we see this one here. This one look at a linearization of system of second order without the stochastic component. Here is this transformation. So my next slide will be where we look at the stochastic component, where we are going to use the similar transformation and see whether can we find the linearization criteria. So I'm not going to bother this. Okay. So my interest is here. This is low. Okay. So that's my interest here. So this one is an example of a stochastic differential equations. Okay. So you can see that this one is just this component, it doesn't have a stochastic, but this one, you've got a stochastic, this part here, it's catered for a stochastic differential. Okay, so how do you deal with this? Okay, so it all started in, I think is it 1827? So when a prominent just observed there was a suspended pollen that were suspended under the water. And then you just imagine that these are, they form irregular parts. Okay. So he also, he died in, I think he died in 1858 without proving any theory of what he has observed. But he observed that those, they fall, they just randomly, you see. And then he died in 1958. And then his work was extended by, is it Louis Pasteur, where he tried to price the stock price mathematically using this concept. Okay, so he tried to do that. He used this concept of Brownian motion, because remember that Brownie died in 1858 without proving anything, but he just observed those observations that those things are random, but he couldn't put the theory in it. Okay, then in 19 he tried to do that, and then in his research he connected a lot of things. Basole, he connected the semi-groups as well as the Markov chain, Markov property. Those of you that have done statistics, they know that the Markov property, they've got those excellent properties. And then he connected also with his reasoning to try and figure out, because remember here, they are trying to develop a theory so that they can use it to analyze this system of equation or this type of equations. And then he just managed to link, to connect Brownian motion as well as the heat equation. That was Barcelo in 1900s. And then his work was extended by Albert Einstein. Okay, that was in, I think in 1905. His work was also extended by him. And then he tried to analyze the work of Brown. And then in his analysis, okay, he was able to describe those type of movement as the random processes. So it was only Albert Einstein who just described this as a random processes. And then from there, he managed to write a paper in 1905. He produced a paper which is mostly referenced even today. Okay, his work was proved and extended by, is it Paul, French scientist? So managed to invent the law of stochastic physics. So that one, he managed to correct what was done by Albert Einstein, and he continued the research. Okay, those two papers are well referenced even today. People are they reference those kind of research that was done by Einstein and Lagrange. And then in 1921, okay, I think in 1921, that is when the Wiener tried to find the mathematical properties, or he tried to describe these random processes, and he was able to describe it mathematically. He was successfully managed to describe it mathematically, and that's why sometimes this Brownian motion are also referred to as the Wiener process. So in my research, because it was according to his honor, he was honored because of he managed to do that. And then I think because I'm just jumping a lot of research, but those ones are the main one. And then in 1944, that's when we find somebody called K. Ito. Okay, so this one, you use all those theories, and then you come up with a theory which is called the Ito calculus. So which means when we analyze these situations here, we use Ito calculus, which is totally different from the classical calculus of ODE. Okay, the only thing that is different, we've got this extra term here. Let me write S here. Don't know whether we're going to see this. I don't know, can I put a plus C or minus half? Okay. So you see in classical calculus, if you integrate this, the answer is here, taking in account that this one equals to 0. Okay. So, but in stochastic, we also got this term here. There's this term here. Okay. Where does this term come from? Yes?
I don't want to interrupt and
yes.
Kill your flow, but so you mentioned these are important in applications. Everyone
Yes.
should know about them. So someone like me, I don't really understand anything that you're talking about. Can you just help us, those members of the audience like me, to just clue in like what is going on? What is X of T is not a function, it's something else. What is the W sub T?
Okay,
Just
okay.
With simple physical example, where I can understand.
Okay,
what these
this
things
one
mean.
is just a function. It depends on T and X.
Sure.
Okay.
What is
And
the
then
X?
Hmm?
The capital X, what is it?
This one is just an Ito process.
What is an Ito process? That's just a name.
It's just X is just a function.
It's a function.
X of T is.
And the W?
Yes, different variables, yes.
The W?
W, this one is a Brownian motion, the Wiener process. It's because I was going to explain because I still have another slide. Okay, at the moment here, I was just talking about yes. No, it's fine. So here, the only difference to see here, these two terms. This one appear only in a Taylor series, just a Taylor series, okay? But here we add this term, which is a second order term. Okay, here we need a second order term. So which means we can't ignore the second order term. Okay, so that's the only difference. Yes.
What does it mean, this equation? Equation is integral differential, actually. And the first part, it is right side, so it is differential. So what you will take integral, and actually x at some point t minus x at point t0, right? Equal to, and then integral, Riemann integral. First part it is Riemann integral, and second part it is Ito integral. Is related with Brownian motion. The Ito integral is special because Brownian motion, if you take normal integral, it is divergent. So, but you have to take special type and special definition.
Okay, now this is my research now. Sorry. So we've got these two, a system of equation. Here I just explain what is F, what is G. Okay, so that's an explanation. And this one here, it's a Wiener process. Okay. So then the aim of this project here is to find this transformation, which is going to transform this equation into a linear second order. Remember that I said most of these are nonlinear. Okay. So this one, we are going to regard this as our linear system. Okay, so this one is our linear system. We've got all the alphas and all the betas, okay? So we've got alphas and betas for the first, and then we've got these alphas. Okay, and then we can represent this system here in the form of second order stochastic ordinary differential equation, which means this one we represent as the form of the first order. This one is the first order. Okay, and we've got the representative of all your A, your B, and your P's, and the matrices and vectors. Now, what happens if you use this transformation? If you use this transformation, then that system, the first order system, becomes this, where you know what is your B here. So using this transformation, you've got all of this. So our aim here is to eliminate some of the alphas. Okay, using that. That's why we have to use this transformation, is to eliminate some of the alphas. Okay, from here, if you choose your C and A such that we've got that, then for solving this, you've got your B and your A equals to 0, then all these alphas become 0. Okay, so which means all these alphas now are 0. Okay, after using the Ito formula, then we're using the Ito formula and separating this equation, we find this linearization, which is necessary in sufficient conditions. This is after using the Ito formula. So I didn't show here, but it's after using the Ito formula. But remember, we need to use the Ito formula in order to find these sufficient and necessary and sufficient conditions. Okay, then what do you do from here? Now we need the representatives of all the F's and the G's. So we just represented them like this. And the coefficients of A and B are functions of X, Y, and T. Okay. Then after separation of this, and we find this over the determined system of equations. We've got these systems. And we have to make some assumption that those coefficients are given, and we need to look at the condition for the coefficients which are sufficient and linearization. Okay, after that, we need to compare all the mixed derivative of the third order. So we look at mixed derivatives of the third order, and then we have to compare them. And then after that, we lead up into these equations here. So after comparing all the third order mixed derivatives. Okay, so then we can rewrite this like that. And you can write this in a form of a matrix. Okay, so you can write this in a form of a matrix where we end up with number 13. Then if delta is not equal to 0, then we've got this necessary and sufficient conditions that other one, that this part number 14 must be equals to 0. Then the representative of alphas, now you've got, remember, now we've got only 4 alphas. It was reduced to 4 alphas. We don't have maybe 8 alphas, we've got only 4. So those are the representative of alpha. So we need to differentiate all the alphas. Remember, they also depend on X and Y. We have to differentiate that with respect to X and Y. We have these conditions. So these ones are the conditions from 15 up to 22. These ones are the conditions that they need to meet. And then similar to beta, okay? So we have these conditions. So we still got other betas here. Remember, I've got a lot of betas. We've got also beta 10 and beta 20. Okay, after checking all these conditions, we end up with this theorem here that this is the system is this kind of system it can linearize via invertible point transformation if these conditions are satisfied. So this is sufficient and necessary conditions. Okay, so that is the theorem. So all these conditions, I have to squash all of them. This is too slow. Okay, I have to squash all of them in the same page. Okay, so all these conditions are met. Okay. So somehow there's no example. I don't know what's happening. Okay, so remember that I've just looked at sufficient. I've just linearized this. Okay, now I need to use the Lie group. Can I use a Lie group analysis to find the solution? Because most of these equations, they are numerically solved. So they are not analytically solved. So can I use this method to solve? So I'll just look at some of the people that they've already done these parts of work. So those are the people that have already done it. So I was just looking at whether can I take my system now, use this method, find the solution, or can I find the symmetries? Okay. Okay, this is this same system. So I just write this same system. So it's still the same system. Okay, so then you can change it to a linear system. It's still the same system. I'm not gonna bother that. Okay, so then this one, I decided to rewrite this in the form of a first order. Okay, then I introduced the F1, which is X2. Remember that this G1 here, there's no G here. G stands for the, there's no G. This one stands for F, and there's no G here, which means there is no stochastic component because we write this in the form of first order. Okay. Then the generator. Okay, so we consider this one. This one is the Lie group. Admittedly, a group of equation can consider of this form. So we use this one. Okay, this one is for these equations. So here you've got your H is described. You've got your Xi1 and Xi3. Okay. Then these coefficients are obtained from the the Xi2 and Xi4 in 26 are obtained from the prolongation formula. So you've got these two, okay, which is 24. Okay, just for simplicity, we just mention this. This is for simplicity or just for us to be easy to use the formula. So we write this in a more compact form, okay, using the determining equations. Then here are the equations now. This one are determining equations. This one is from a theory here. So now let's look at our own. Okay, using the 28 and 29, you come up with this linear system of determining equation. From 28 and 29, we've got these determining equations. Okay, so this is 38 to 30F. And then from the prolongation formula, you've got other equation from 31A to D1. You see, there's a lot of equations here. Okay. And then we need to classify. Okay, 25 like this. Okay, so remember that we've got all these alphas and all these betas. Okay, same thing here. I just mentioned here, but it's the same like previously, where we rewrite this in the form and then use this equivalent transformation. But here, this part is going to be 0, and this part is going to be 0 if we use the equivalent transformation, the next one. Okay, I'm not going to mention it. Okay, because I've already talked about it. Okay, there it is. So using that transformation, you find these ones as zeros, all of them. So which means it make our calculation a little bit easier when we deal with alphas. Okay, here. So we consider this linear with a constant coefficient. So then we've got this equivalent transformation now. So remember that other alphas are now equals to 0. So we've got about 2, 2 instead of 4, 4. But the betas, they still remain the same. Okay, when we substitute this into our determining equations, now we've got this type of equations now. Okay, because some of the alphas are now equals to 0. Okay, now we need to split this with respect to those two, and we find those results, which is 38 and 39. Okay, so we find those results. We find what is xi1, UH prime, xi2, xi3, and xi4. So we've got these conditions. So remember, all of these are constant. Okay, substitution of 38. Now you've got these conditions. Okay, so you've got condition 42 to 40, 42A to 42C, and splitting 37. Then we have this condition 43 up to 43A to 43C. Okay, so that's something to note, that 42A and 43B are solutions of the system of linear second order. So we find number 44. When we look at that one, we find that condition number 44. Okay, and then we also look at other equation like 42B and 43C, and then we've got these conditions, which is 45A and 45B. Okay. Okay, it's time for us to look at the Jordan form, and then it's time for us to analyze and look at different conditions for this constant. But before we start the cases of A, it's worth listening to the determining equation of beta. Remember, this one is only for alpha, but we also need beta component. Okay, but it's better for us to list it. Okay, remember, after analyzing those questions, we still need to analyze this. So we still need to analyze the beta component, okay, which was that part of a stochastic. Okay, so using the condition, those one Jordan. So we took the case 1 where your A equals to J1. From that, we have the following conditions to study. Okay, so from those Jordan, we take your J1 and we have these conditions to study. Okay, so from 47, you can see that there are 2 cases. It's either your B minus A equals to 0 or your B minus A equals to 0. It's not equals to 0. So what happens if you study those 2 cases? Okay, so for this case, it's B minus A equals to 0. Then we've got this general solution with 3 cases. That is A is 0, A greater than 0, and A less than 0. So by using that, you find that you end up with this generator, okay, for this condition. Okay, for this condition, we end up with this generator or these symmetries for that condition. Next. For this condition, we substituted, and then we find these generators. Okay, this is for this condition. I'm not going to go through all the conditions. I've just selected few. Okay, then for this one, we find this generated. This was obtained from all those conditions. And then we look at I'm not gonna go through, then your J2. So your J2, you have this system to analyze. Okay, so I'm just going to go through. And then for J3, A equals to J3. Okay, so we've got this system also to analyze. Okay, so for A equals to J3. So we've got different cases. Okay, so now the beta component. So that was the most challenging one because we've got a lot of betas, we've got a lot of calculations, we've got a lot of analysis. So this one was very challenging for me. So there were so many betas and there were so many conditions. Remember here, we didn't have any transformation or any equivalent transformation that can reduce the number of betas. So this one was most challenging and I ended up with not all conditions, but only few conditions because I couldn't continue because I was also confused myself. Okay, so this one was the most challenging one for me. Okay, so but I look at those conditions. Okay, so I've looked at only few cases for beta. Okay, so although I've looked at those other cases, but I still want to look at other betas, what happened, because this one is, once we look at this one, you look at K, then we have to look at beta as well, the condition for beta. And then there are so many beta it's about 8844. No, 88. So there are so many betas. Then we have to look at this bit. What happened to this bit? What happened to K at the same time? What happened to beta? So it was the most challenging one. Okay, you see, I've only tried to look at small cases, not all the cases. Okay, so that's the conclusion. And thank you, because I have to write the time. Okay, any questions?
Yeah, thanks, Dembi. Any short questions?
Yes.
So in each of the cases, you're looking at the linearizable cases, right?
Yes.
So in the different cases, you're getting different algebras each time.
No,
so actually, in the one case, you got like 10 symmetries.
Yes. But yeah, with betas, I find that there are some other symmetries that are more or less the same, which is different from these alphas.
Okay, the reason I'm asking is that for a single scalar second order, it's a simple case. That if you found the linearizable case, you always get 8 symmetries, algebra symmetries, the SL3 algebra, no matter what. So like, so it's all linearizable. Yeah, it's not a standard result. So you could be, even though it's linearizable, you get different options.
Yeah, that's what I was trying to say, that those ones are sometimes very, very difficult to analyze. So that's why some people, they just resort to numerical analysis instead of this. So that's why I was like, if I find solution, maybe I can check working with a person who's doing numerical analysis. Because I've got different cases, I've got this different, but with betas, it was a little bit, there's somehow that they link to one another, the symmetries. But with these alphas, they were like this. Yes. Yes.
I guess these are more comments. The first one is in terms of all the cases, for example, in Maple, there's a package that will automatically take your system and do all the case splittings for you. So you don't have to do it manually.
Okay.
And then for each case, you can just integrate. And so you could essentially automate the production of all cases. The output would be the generators in each case. My main comment is in Lee's symmetry analysis, the main thing we're interested in are what are the non-obvious symmetries. So if we just look at the general form of your system, there's going to be some symmetries that are obvious, like time translation, interchanging the different x's. And so, yes, it's nice to see all these long tables, but what's interesting to the audience, to readers of your paper, is going to be what's unexpected. Because, sometimes, not in your case, but we see simple papers where all we find is sort of the obvious symmetries, translations, scalings. Okay, so who cares? We could have, the result is at best, there's nothing unexpected. So I'm just wondering if, can you just say in a couple of sentences, what's unexpected here? And also for people like me who know nothing about these stochastic processes, if we just turned off, decoupled the random motion, then we should be in the case Professor Kara was talking about. And so just, what is new that the stochasticity is added to this problem that we don't see in the classical case? Thank you.
My supervisor is here. Prof, can you answer?
I want to say that I was involved in this research, but then I was disappointed. Why? Because we started applying for gas dynamic equations. First, I will say what is the problem. Problem is that when you do change of variables, then composition of functions, differentiation of composition of function is different. So this is the problem. One. Second problem, but this is not differential equation, it is integral equation, second problem. Third problem, that the integral involved is there, is not Riemann integral, it is Brownian motion, and this is more definitions about this. Either it is Ito integral or Stratanovich integral, for example, but now it is, I know that my friend.
But somehow you're just treating it with some formal calculus, like you don't need to know the exact form.
Exactly so, but this, when you,
treating it as an extra variable.
when you try to do transformation, so this is, now it is one approach, for example, Fezel, and so this is his student, yeah. So they did the following, they did not change Brownian motion. What happens if Brownian motion is not changed? So then you lose something that related with change of variables. So we try to involve it, but then when you try to consider some solutions, for example, invariant solutions for gas dynamics, so stochastic gas dynamic equations, then for different solutions, different Brownian motion, you know that. It is not good in some sense, right? So.
I was just asking about the symmetries themselves.
Oh, this is, yeah, this is.
What's new? What's unexpected?
Symmetries are almost similar, so like in gas dynamics. But after when you try to construct invariant solutions, so Brownian motion must be involved. So in transformation, this is looks like unusual, that you change equations in this case. So, and this is new. And another thing, Sembische talked about linearization. First problem, it was done by Lee, right? So for second order equation.
Yeah.
So, yeah, but now this is involved also Brownian motion. So then integral equation. So then question is, what happens in this case? So, and she did about this one. So she found conditions when equations can be linearizable. So, okay.
But there was no simple
What about,
interpretation like in the classical case.
no, this
Like a total
calculations are very complicated. I mean that this is many equations, even for second order equations, you can see, then she used reduce for this. So, yeah, but there are no program. So general programs that, like, for example, in Maple, you have already for finding Lie group analysis. So to using Lie group analysis, there is a program, right? So, but for this one, right now, there is no.
It's
So
easy to program, just to change it.
It is not easy. I want to say why it is not easy.
So why is it not easy?
Because Brownian motion, so this theory is still developing. So these guys from Gaeta and Roman Kozlov, they try to to involve in transformation. So like we have transformation and then we construct determinant equations.
Well, I would propose it would be interesting just to have a session where we can just like in the Russian style, just interact directly, because I don't understand any of what you're saying. I don't see why.
Can I suggest that we have, no, I totally agree that we should have a session. So, but maybe we should make time on, we can see sometime tomorrow, Friday, when we get a block, because I think it's interesting to look at, the biggest challenge, of course, was as you saw, many variables, and then there's the probability part because of the Brownian motion, which comes in. Yep. Integral equations, but I can also see that, yeah, so if there's a way in which we can try to find a way forward to help, because that's the point where we are stuck.
Yeah, so my main point is just from what I saw on the slides,
yeah,
I'm not seeing any hard obstacles. So obviously,
Stefan, I want to answer these questions that you are right. So, but nobody is doing this. Who will do it? Yes. Right?
we can do it in a second.
Yeah, it's possible to do. Of course, because formula programming is no problem. So you can use it. So after that, you need to solve determinant equations. But this is also can be done because determinant equations you reduce to differential equations.
Yeah.
Even here, this is a problem because if you start using, I will explain it. Because if you start transforming Brownian motion, equation will be not differential.
Right.
It will be still stochastic equation. Right. Yeah. How you will work with stochastic equation? How do you find solution of a determined system with stochastic part? This is not so simple.
I need to understand more details.
Yeah, I want to say that for integral differential equation, because this is integral differential equation.
But there was no...
for each equation, you have to use own way how to find solution of determinant.
I'm just saying that in the talk, an integral sign never appears.
Oh, because
so all of the
this is, I want to say, this is, yeah. So this is part related with Brownian motion is moved. So, but if you include it, so then it will be.
We need to see. I'm just saying for an audience.
Okay.
Yes, I support that.
We need to see.
No, it's fine because it's just a presentation. But if nobody is doing it, we have to do it.
Okay, thank you so much. No. Yeah.
I want to say that, you know, that Stellenbosch started saying that we need to use nonlinear equations. We need to start working on, and linear equations, it was used, you know, that Nobel Prize, Black-Scholes equation, it was for linear equation. After that, we had one visitor from this part, they used stochastic differential equations for financial mathematics. I asked them, do you have nonlinear equation? No, we just change parameters. So this is, and there are some nonlinear equations, but they have properties of linear equation, and she is doing this.
Excellent. Thank you so much. I think that was an interesting engagement. I just want to check. So we didn't have the previous speaker, so it's done. Okay, so I want to thank our chairperson. Thank you so much, Robert, for an excellent job and also for stimulating discussion at the end. But I also see that Thembi, at least you now have, it's nice to have someone to challenge what is happening, and also I think to have a discussion around that. So if you can take advantage of that tomorrow, Friday as well. And then I think, so for now, this brings us to the end.